And have still not understood this WaveX thing, we are starting without it for the time being. Correct? Okay, so this day has four oral sessions and one poster session. Poster 26 through 45 will be evaluated today, but we request all the presenters for 1 to 25 also to be near their poster boards at the time of the poster session. So we'll start this first first oral session, and this session is going to be chaired by Professor S. Kannan from BARC. His present affiliation include an outstanding scientist and director, radiochemistry and isotope group, BARC. He is also a senior professor and convener, Board of Studies, Chemical Sciences, Homi Bhabha National Institute, Mumbai. Also, he is visiting professor to CEBS, Mumbai. He has obtained his PhD from Mumbai University in 1992, and then he moved to for postdoctoral work to University of Guelph, Ontario, Canada in 1995 to 96. 96 to 97, he was in University of Missouri, Columbia, USA for a postdoc, and then he visited the same lab again in 2005 and 2006. His area of specialization primarily is complex chemistry of actinides and lanthanides. In the 35 years of his professional career, he has published more than 120 journal papers and 40 conference papers. He has got Homi Bhabha Science and Technology Award in 2011. He is a fellow of National Academy of Sciences, India. Previously, he was the president of Indian Thermal Analysis Society in from 2015 to 2021. He is vice president of Indian Association of Nuclear Chemists and Allied Scientists, and also vice president, he was in Association for Separation Scientists and Technologists. With this short introduction, now may I invite Professor S. Kannan to take over and chair this session. Thank you.
Thank you for your nice introduction. Good morning to all. Welcome for the second day of first HBNI interaction meeting in chemical sciences. Yesterday, my observation was when the CA, that is faculty from CA, is presenting, other faculty from other CA institute, they ask the question. Today, I want most of the questions from the student side, because the interaction between the faculty-student interaction. So I am expecting that today, I expect that is 1 or 2 questions from the students to the faculties. So in this session, we have 3 speakers, and each speaker is allotted 30 minutes. So 25 minutes for the presentation, followed by 5 minutes for the question and answer. So the first speaker of today's this session is Dr. Timpul Datta. He is currently a scientific officer G in Chemistry Division, BARC. He joined BARC in 1996 after obtaining her MSc from IIT Kanpur. She did her postdoctoral work at University of Heidelberg, Germany during 2001 to 2002. And she is having so many number of publications, and she has written several books, chapters with international reputation. He received prestigious bronze medal from CRSI, that is Chemical Research Society of India, in 2021, and DAE's Scientific and Technical Excellence Award in 2020. And she is a fellow of Maharashtra Academy of Science in 2016. He has been awarded membership of National Academy of Science, thus India, and also a recipient of DAE SSPS Young Achiever Award. He received the ACS Award from American Chemical Society. Dr. Datta also served as a reviewer for more than 30 international journals, and she is an associate editor for International Journal of Applied Ceramic Technology. With this introduction, I request Dr. Datta to give her talk on battery storage technologies for India's green push. Dr. Datta, please.
Okay. Thank you, sir, for your very kind words of introduction. And good morning to all my respected seniors, my colleagues, my friends, and dear students. So, as you can see today from my title slide, that I will be talking on battery storage technologies for India's green push. But before I actually move into the topic, let me first give you an overview of the place I come from, because generally not much is known about the kind of work we do. So let me give you an idea about our group. So our group, as you can see, is working on nuclear and functional materials. So in the last span of almost 20 years of my career, we have worked on a host of different functional materials. So we have become from chemists, we have become now material scientists. So the span of work includes luminescent materials. You have materials for environmental remediation. We also work on nucleus-based vitrification matrix. We also work a lot on multiferroics. And presently, the youngest baby in this group is the materials for electrochemical energy storage. So now, as what happens, in a family, the youngest one gets the most amount of, I can say, your attention. So at present, 75% of my time as well as my group's time is invested in electrochemical energy storage. So why is it so? So let's look into what is the Indian scenario for energy storage at present and why it is so important. So gradually, as you can see, we are moving from fossil fuel to non-fossil fuel type of energy. And that is more and more important because we are moving towards a carbon-free society. We want less and less of carbon emission. And India has a target that by 2070, we want to go net carbon zero. That emission should be zero. So for that, there are a few stages in which this entire process has been, visualized by Government of India. And from the Niti Aayog, the targets which has been set are that we need around 500 gigawatt of non-fossil fuel-based energy generation in India by 2030. And also by that time, we need to reduce the total projected carbon emissions by 1 billion tons. So now if we want to go into such kind of a target, then we need a significant amount of grid storage. Why grid storage? Because when we talk about non-fossil fuel type of energy, we are talking mostly about solar and wind energy. And, they have an intermittency in their supply. So sometimes it is in the peak hours, you can transfer directly whatever you're getting to the grid. But during the off-peak hours, what happens is you need to store that energy. So for storing that, you need some storage technology to come. And also for green push, rather than having vehicles which are running on fossil fuels, we are moving more and more towards electric vehicles. So these are the two prime reasons why, our storage technologies need to improve. And for that, we need a mature domestic battery manufacturing ecosystem, which will give a competitive advantage to India and really contribute to the energy security. So now if we move ahead, we know that when we talk about battery technology, the most established technology is anyway lithium-ion battery. The research started way back in 1967, and by 1990, Sony had actually come into the market with the commercial technology. Last 2, 3 decades, we have seen where this particular technology has put our lifestyle into. So all the portable electronic market has been kind of completely taken over by lithium-ion battery, and this work has been vetted by the Nobel Prize Committee by giving the Nobel Prize in 2019 to 3 eminent scientists who had actually worked on lithium-ion battery technology. So this technology is well established. So you may now ask that, okay, if this battery technology is established, then why are we still, having this kind of thing that we need to develop a mature battery technology in India? Now the problem lies with the material which we are using, which is lithium. Lithium, basically, it has only 20 ppm of lithium in the Earth's crust, and then the geographical distribution of lithium is also very skewed, in the sense that you don't have lithium reserves equally distributed in the Earth's crust. So what happens is a few countries has a lot of lithium reserves and some doesn't have it at all. So India falls in that have not group. So even if we are moving to non-fossil fuel based energy, so we will, though we have a lot of potential for solar energy, potential for wind energy, but if the battery storage technology is constricted by lithium supply, we really have to look into alternate battery storage technology. And this is where basically sodium comes into the picture. Lithium-ion battery established technology. It has cathodes as lithium cobalt oxide, or currently it is NMC, which is nickel manganese cobalt, and the anode is graphite. You have established set of electrolytes also, where it is lithium salt in ethylene carbonate or diethyl carbonate kind of solvents. But if you're looking into an alternate technology which is going to fit in very nicely with this lithium-ion battery is sodium-ion battery. Why? Because sodium has many chemical properties, obviously, which is same to that of lithium. So, and it's abundantly available. Its distribution in the Earth's crust is around 23,000 ppm. So you can imagine, even there's a lot of reserve. So definitely this is going to put in into a cost reduction. So a kind of cost reduction is expected when you move into sodium, and obviously due to the availability factor, this becomes the technology to move into, at least from Indian scenario. So is that's so easy that, okay, we have an established technology, lithium, and we just put in the sodium? It doesn't work that way. Why it doesn't work that way is because you see lithium and sodium have some inherent differences. One is the heavier, the mass of sodium and its larger size. So the kinetics inside the battery, it's going to be very sluggish. So you have to find materials which is going to kind of overcome that kind of sluggish kinetics. So we can see that the price factor and from the availability, definitely sodium is a very good choice, but materials, we really have to work on it. So what are the advantages? As I said, low cost, environmental friendly. It is a reduced supply risk, but the disadvantages is going to be low gravimetric and volumetric energy densities and difficulty in achieving broader voltage windows. So these are the areas where material scientists like us can really contribute, and this is where we have tried to up the game. So before moving into the materials which we have synthesized, let me just show you how the battery cell for the students, how this generally works. So if I look into the battery cell, you can see what happens is while charging, you're having a movement of the sodium ions. You can see the green ones, that the sodium ion, it is basically moving in from the cathode. It travels to the anode. So this is what happens when you are charging a particular battery. Whereas the moment this entire charge process is over at around 4.1, 4.2 volts, then what happens is when you start the discharging process, then again this sodium ion, it starts moving back to the cathode. So what is the idea? You need an anode which is able to take in the sodium, and you need a cathode which can give away the sodium, but when it takes back the sodium, it is stable enough to take it back in the same structure. The structure doesn't disintegrate. And here, basically, the anode and the cathode material, they are very important for us to find out the right kind of cathode and the anode material. So now when we look into the theoretical capacity of a battery, as you can see over here, theoretical capacity is mostly dependent on that N factor, which is the number of reactive electrons per formula unit. And this basically gives you, if the N factor is more, then you will get more specific capacity. And another important factor is the working voltage, as you can see over here. So with the energy density, it is basically a factor of your specific capacity and working voltage. So if the working voltage is more, the energy density of a battery is more. So now concept-wise, please understand that the working voltage for a sodium-ion battery is only 2.7 volt compared to that of lithium, which is 3 volt. So anyway, the energy density is going to be low. So if it is having a low energy density, obviously the lithium-ion battery is useful for portable electronics. Sodium-ion battery probably will never have that state where it can replace lithium-ion battery in portable electronics. But where it can replace is places where energy density is not a big factor. And so this is generally very useful for grid level energy storage, and where you can free away the lithium from being applicable to that kind of thing, and you can use the lithium for other important technologies. So this is where you can kind of contribute to the energy security of the country. So in our group, we work a lot on these materials, as I said, and this particular slide gives you, in one nutshell, about the thousands of materials we have screened, and this work we have started way back, recently in 2018, in Jan or Feb, and we have screened almost thousands of materials, and this is basically the nutshell of what we think are very good materials for sodium-ion batteries. So among the cathodes, you find on the right-hand side, I've given you sodium vanadium phosphate and sodium vanadium fluorophosphate. These are the cathode materials of choice. So we work a lot on other transition metal oxides, but I think this particular vanadium phosphate definitely has a lot of potential. Then on the anode side, we work a lot on biomass-derived carbon. We also work on chalcogenide composites, which can be used as anode materials, and binder-free CNT sheets, where we are getting rid of the binder, so we are trying to improve the energy density of this particular material. In electrolytes, we also work on different kinds of, normally in LIB, you are using a carbonate-based electrolyte. But when we move to sodium-ion batteries, what we have found out is these electrolytes work better, and that we have proved in, I'll come to those slides later on. And on the bottom side, if you see what we have worked is something which is very built-like currently. It is a solid-state sodium-ion battery, where we work a lot on ceramic cathodes, gel polymer, nasican, as well as glass and glass ceramic electrolyte, and we also work a lot on glassy anode kind of systems. So all these different systems we have developed. So a lot of work is going on, but it's not possible for me to discuss everything. So a little bit of highlight I will give of each of the work we have done. So coming to cathode, the choice of cathode materials is basically P2 transition metal oxides, or the O3 transition metal oxides, O3 type transition metal oxides. You have polyanion type of oxides, and then you have Prussian blue anions. So out of these four, our group is mostly involved in the first three, that is A, B, and C. But if you might ask me that, okay, fine, these materials are already established. No, it is not, because they have a lot of problems. You have problems of inferior conductivity, sluggish kinetics, severe volume alterations during the intercalation and deintercalation cycling. So we have to keep on modifying these materials so that you get better and better electrochemical performance. So you can do structural modulation. We do a lot of surface modification. We do a lot of elemental doping. So as I said, I work on A, B, and C, not on D, Prussian blue analog, because organic chemistry is not my forte. I'm more of an inorganic chemist. So then coming to the cathode materials, I'll discuss only one over here, sodium vanadium fluorophosphate. Why? Because why the fluoride is added? Fluoride is added because, it helps in expanding your operational voltage. Once you have the fluoride with the sodium vanadium phosphate, it helps in expanding your operational voltage. And if the voltage is more, the energy density definitely more, apart from the stability factor, which is K. So here, if you see, we have two electrons. This particular electrochemical reaction has that N equal to 2. And here the active element is your vanadium, vanadium 3 plus 4 plus, that is typically the active material. And the theoretical specific capacity of this is 128 milliampere hour per gram. So what is the problem with this particular material? The problem over here is the inferior electronic conductivity. You have an electronic conductivity of 10 to the power minus 12 sieverts per centimeter. And if the conductivity is so low, then obviously it is going to have a terribly sluggish kinetics. So it is very stable. To take out the sodium and put it back in, it maintains the structure. But the problem is that the electronic conductivity is not good. So we thought that how we can improve it. And so for that, we went into some kind of heteroatom doping. So we checked literature, we found that, yeah, people have tried out, they have used aluminium as a dopant, then they have also used, I think, it was chromium as a dopant. So they have used these kind of dopants, all 3+ dopants. And then we saw one particular paper where they have reported that there was a titanium 2+, 3+ kind of doping was done. And they showed that when the valency is different, then probably there is an increase in the conductivity. So this kind of struck me that we can use this as the starting point and try and modify this particular compound. And for that, what we did is we did some tungsten doping in this NPPS. And what we saw is really a very nice, improvement in the properties. As you can see, if you look into B, that is graph B, and you can look into the graph E, you can see the specific capacity has improved considerably when you have done a tungsten doping in that. The best would be graph H. As you can see, the black one is basically your NPPF with carbon. Carbon is obviously added to improve improve the conductivity. And with the tungsten doping, you see the amount of increase in the specific capacity of this particular material. So we kind of found out that when you are doing an alluvial doping in this particular compound, at least when you are moving from tungsten's with a tungsten which is 6 plus and vanadium which is 3 plus over here. So definitely there is some kind of thing which is happening which is improving the capacity of this particular material. Now, one more thing we have to understand is for these kind of materials, your morphology is also very important, because according to the morphology, that sodium, giving up and taking back that sodium also helps. So if your electrode is getting disintegrated in the deintercalation process, then your cyclability is going to be very poor. So this particular tungsten doping we found, you can see from the graph D. C and D are basically the tungsten dope one. You can see that after the 100 cycles also, you can see this post-mortem analysis shows that it is maintaining, and not only that, it is adhering very nicely onto the copper foils. So that was a very interesting study, and we also did some theoretical study for it, and we found out the reason why basically tungsten doped this particular system was giving a much better result. So now this work is continuing, and we are now moving into other kind of dopants, where instead of going into more electropositive ones, we are going into less electropositive ones and trying and see what is going to be the effect, so that whether a clear picture comes out or not. And some very good work is done with some zirconium dopants. We have also done some good work with cobalt dopants. Not much time here to show, but these are the kind of work which is going on in the lab with the NPPS cathode. Now coming to the anodes, the problem is you cannot use metallic sodium as anode for sodium-ion battery. Why? Because it is dendrite due to the sodium metal deposition. And it also has a very low melting point. So if it has a low melting point, then safety becomes an issue. So we have many different anode materials which has been tested for sodium-ion battery. So among these anode materials, why you cannot use graphite? It's a very simple question. Why you cannot use graphite? Graphite is used in lithium-ion battery and it has space. Why it can't take in the sodium? But size is not an issue over here. Graphite gives a very less specific capacity of 35 milliampere hour per gram. We can't use graphite. The problem is not with the size, because it does take in potassium. The problem is with the thermodynamic parameters. It is not sustainable for it to form a sodium and a graphite composition. So that's why graphite is ruled out. So what can be used in place of that? What was found out is that you can use different kinds of other carbonaceous materials for that. So if you look into it, some desirable anode material characteristics are there. Obviously, it needs to have low atomic weight and density. Then you should accommodate more and more sodium ions. So I'll not read into this, but just go into the literature and see how it is. It obviously has to have low cost, environmentally friendly, high electronic and ionic conductivity. These are the ideal things, but practically it doesn't match. So we have to look into the choice of anode materials which we have. So we have insertion reaction materials where you have carbonaceous as well as titanium-based compounds. You have conversion reaction materials, which is from sugar oxides and sulfides. You also have alloying materials like silicon, germanium, tin. They all form alloys with sodium. So these are also very good materials. So as you move down the group, what happens is you find that the N value increases. So your specific capacity keeps on increasing. But the problem is you see the volume changes. When you are with carbon, the N value is 1, but the volume change is very less. So that's a very good material. It gives a lot of cyclability. But the moment you go to alloying and conversion, there's a huge volume change, 400% volume change. It will just come out of your copper foil. So within like 10 or 15 cycles, you'll find it is moving out of the copper. So every material over here, it has a positive as well as a little bit of negative. And our duty as material scientists is to reduce the negative parts. So now we work on all these systems. Obviously, I will not be discussing everything, but I will discuss something which is very close to my heart, which is basically the carbonaceous materials, that is hard carbon. Hard carbon is nothing but non-graphitizable carbon. At 3000 degrees centigrade or 60 degrees, it doesn't give you the graphitized structure. So it is non-graphitizable carbon. The thing is that it is highly disordered. It has the spacing is more, and it definitely provides much smoother pathway for the sodium ions to go and sit inside it when the process of charging happens. But hard carbons, they are generally prepared by high temperature thermal treatment of organic polymer carbon. This makes the process very energy intensive and also very expensive. So when we are trying to give a technology to any kind of first thing they ask is the vitality. So then for that, what we did is we went to the biomass kind of thing, the inexpensive source, it is less energy intensive, and it is in various types of land structured carbon. So we moved into biomass kind of thing. And ultimately, what we found out is a very simple method of treating bio waste and getting these kind of disordered lithophorous carbon, which actually proves to be very good anode materials for sodium ion batteries. So we have done this particular work, and this started with a history. We actually were preparing carbon for something else, and for that we required something with a high surface area. We were dabbling with these leafy seeds, and we found that we are getting a carbon with a relatively much lower surface area, which was of absolutely no use to us. And this was the first material we tested, and we found that, okay, this is the material which is actually giving us a very good carbon anode for sodium ion batteries. So this particular work, you see what we did is, the synthesis method is very important for this. In all other bio-based derived carbon, you will find you use inert gas carbon. So we have developed a method by which without inert gas carbon, you can get this carbon at a very low temperature. So we did all these different, experiments, electrochemical things. Let me tell you the electrochemical experiments you need to do for these kind of studies. One is CDU, then there is galvanostatic charge discharge. You also need to do cyclability studies, and you need to do the rate capability measurements to see that if you're increasing the rate, how your battery is responding to it. And when you again bring up the rate, whether it is able to immediately kick back into its original form. So that gives you how much good your material is. So we did this work, and this was one of our first work in this particular area. And then after that, this was a half cell we did. Then obviously you have to use that anode in a full cell. So we fabricated this full cell, and with the full cell we have used NVP as the cathode, not NVCS. We used our first material, which is sodium vanadium phosphate, as the cathode, and this particular bio-derived carbon is the anode, and we could actually make this particular cell. And this is a standard thing. You show an LED lab which is lighting using these kind of point cells. So this patent was applied in 2018 December, and December 22, second week of December 22, we have been granted a patent for this. So it took us some 3-4 years, but we now got a patent for this. So once this was done, we wanted to see that, okay, whether this biocarbon, normally when you're preparing any anode, what you do is you use the active material with some carbon to improve the conductivity. So we wanted to see whether this biocarbon can improve the conductivity of normal anode material. So we used NTO. We studied with NTO. We made a particular biocarbon which was from tamarind seeds, and we could do half and full cell with this biocarbon anode, and we found that there was a very nice battery capacity coming up for this material. And for this also, we have applied for a patent for this particular work. That was in 21. I don't know when the patent is going to be approved, but yeah, we are for this one. And then we did some electrochemical studies on the composite of NTO with this biocarbon, and we observed a very beautiful thing. NTO normally, if you see, when you are heating at 700 degrees centigrade, it's monoclinic. If you want to go to triclinic, then it is 1000 degrees centigrade. So it's a very high temperature. What we did is, when we were using our process and we were kind of grinding it with our carbon, what we saw is that we are getting a very good capacity, and we couldn't really find out why in NTO, just because of this increase in conductivity, we should get that much more of capacity. So we went back to the table, and what we found out that the monoclinic form of NTO, it has changed to triclinic, and the temperature was only around 700. So we are grinding it, and we are actually being able to change the phase from the monoclinic to triclinic. And why triclinic is important? Because it provides easier channel for the sodium to move in. So we improved the conductivity of this particular material, the ionic conductivity, and it gave very good results. So this was one of the work. So we found that biocarbon has many other applications also when you're adding it. So obviously, we did a lot of study in that, a lot of experience study, and that all these are available in the publication. You can check it out later on at your own time if you are interested. So we can see the diffusion coefficients also we have calculated and show the remarkable difference. Then another thing what we tested is how the electrolyte affects. So here we have used biocarbon. This is from mango seeds, and we tried, exploring that what happens if you change the solvent from a normal ester to ether. And this is what we observed in this case. So the blue line is basically for ether. That graph H, you can see the blue line is for ether, and whereas the green one is for the ester kind of solvent. So we saw that when we are using ether as an electrolyte solvent in sodium-ion batteries with our biocarbon, there is an improved specific capacity. And the reason for this, we have done very detailed EIS measurements. We have done a lot of post-mortem HRTM and all. And what we found out is that the SCI layer formation, you lose some sodium due to the formation of that SCI layer between the anode and the electrolyte. So that SCI layer formation when we are using ether is much less compared to when we are using ether. And that basically is improving the capacity of this material. So we are trying and doing it with other materials and seeing that whether this is the reason for this improvement we are seeing in all the different biocarbon. And so now we have done a full cell with a ether-based electrolyte also, and these are the full cell results. But obviously, as you can see, we have run a 50 cell. If you look into graph D, you can see that the capacity is very strong. So now we have to improve on this. So what is going on that? So we are trying and finding out how we can improve, the stability factor for this using ether electrolyte in the full cell. Half cell it is working very well. Then, of course, we have come to conversion reaction materials. Conversion is basically the halides, the sulfurs and selenides we use a lot. Advantages, the end value is very high, so capacity is very high. But disadvantages, you have large irreversible capacity loss, which leads to low initial coulombic efficiencies and swelling upon cycling. So use any sulfide, it's going to swell with the intercalation, deintercalation, and then it is going to come off, pull off your copper foil, and it is going to just drop your cyclobratic charges like anything. So you need to work on that. So at that time I was working on a review article on graphitic carbon nitride. And a lot of work has been done on photocatalysis and all. So I was just wondering that the graphitic carbon nitride has so much of application in catalysis. So why can't I just find out that whether this can be one good support material for these kind of sulfides? And so this was one of the first works which was reported using GC3N4 and ZNS from our group, where we use the GC3N4 as a support material for ZNS and see that whether it can contain the volume, the alteration, what happens. And graphitic carbon nitride has a good conductivity provided you are altering, from bulk you are doing some modification to the GC3N4. We did all those modifications, and what we found out is definitely there is a lot of improvement. The biggest thing to take away from this is because we started with a lot of work. We did ZNS, we did CUS, we did IN2S3. So all these different kinds of sulfides we tested. We did a lot of work on this particular material. ZNS, of course, is my favorite. So the first work which showed that this kind of thing happens. And now many groups, particularly in China, they have completely taken over this work and find we are working on selenide, sulfides, all with graphitic carbon nitride currently. So this particular, what we found out is it prevents the polysulfide leaching. That is one of the biggest point of capacity loss. So when you are using graphitic carbon nitride, this polysulfide leaching, it stops. So these are all the different kinds of work, the copper sulfide work as I'm showing you over here, you can see. And then of course, your morphology also, it helps in the morphology, it helps in containing the volume, the changes and all. So we have done a full cell with copper sulfide and graphitic carbon nitride composite anode, and we could actually show that, you can use that cell that you can see over here. It is writing out all these small labs. So this is so, if you look into the timeline of LIB and SIB, as you can see that lithium-ion battery since 2009, it has gone into the acceleration maturity stage. But it will never reach a saturation because every time we find a new application for lithium-ion battery. But sodium-ion battery, it is only the takeoff stage that started from 2018. It is a field, it has a lot of applications in coming years. This technology needs to accelerate. This technology also probably come to some stabilization at some point, but currently it is in the growth. Highly nice field to work on where you can do a lot of material science, where you have on-spot application. So it's a very good field to pursue. So all this work, what I said, has resulted in many of these publications that just come out in 2022. And I have a very small team, but a very dedicated team of people who work. Abhinanda, who has worked on this kind of material. Anish has worked on carbon. Bhavna is working on all these electrolytes. Akhilesh is doing some wonderful work on sulfide. Somewhere. So he's doing some very good work on sulfide materials. He has worked on lithium sulfide. He's working something on bismuth sulfide, though not with carbon. He's studying some other property with bismuth sulfide. Brishti is preparing all the pouch cells, which we are now making for NPPS. So Priya is working on electrolytes. Deepa and Manas, they are my pillars. They really, I mean, put in a lot of effort in all these ideas. I put bouncing of my ideas to them. Professor Sagan Mitra and Professor Balakiram Ravuri from Geetam, Hyderabad are my collaborators. I thank them. And my greatest thanks to my guru, Dr. Tyagi, who has been instrumental in shaping whatever I am doing.
Thank you, Dr. Datta. Now the talk is open for the discussion. I want the questions from the student side, today at least. Now, some students. Otherwise, I will blame the students. Anybody from student side? Yeah.
Hello. Yeah, nice talk. So could you explain why the putting tungsten into your material increases the
Yeah, the thing is that what we found out is it improves the conductivity of the material. So when you have that, you are actually replacing the vanadium 3 plus with W6. W6 plus is occupying the vanadium sites with the sodium vanadium fluorophosphate. So once it goes over there, what is happening is we see a change in the conduction band and the valence band. The difference it gets kind of reduced from the theoretical studies, is what we found out. And what we see is the band gap is reduced. So the band gap is reduced as obviously the conductivity. Not only that, what we found out is even your sodium ion conductivity also improves. These are the two reasons why that improves. But as I said in the paper, titanium 2 plus and titanium 3 plus, this paper had come out in energy storage material, where they had done it using NPP, not NPPS. So we found that they have said that, when you are having titanium 3 plus, there is no change. With 2 plus, there is a change. So that means that, that changing that vanadium 3 plus to some other kind of dopant, where there is annuvalent doping, it is creating some kind of changes over it. But it is very difficult to pinpoint unless and until you screen a lot of materials. You can't really get into a theory because many factors affect your battery performance.
For that carbon material, what we choose for sodium ion battery, why that less surface area is preferable?
Yeah, less surface area. See, now in carbon, one of the most, any material in battery, what happens is, see, we have a theoretical capacity. Why we say it is theoretical? You can never get the full capacity back. Because that sodium, the moment it moves into the anode, it will form a STI layer. It's like, that layer forms. And it traps a little bit of the sodium. So the entire sodium will not come. So you lose the capacity. If you're having a higher surface area, definitely your electrolyte penetration is going to be more, but that STI layer formation is also more. So the IC value is going to be very less. And that kills your sodium ion battery. So what we found is if you need to have, whether if it is a very small surface area, then the penetration is very less. So you will, then obviously your capacity is not more. But if you have a very high surface area, then IC value will drop. So you have to have a balance.
Thank you. Any other question? I think now faculty can ask them one question. Anybody from front side? Yeah.
Yeah, good talk. See this, most of these your sodium ion battery, the cyclic stability I could see on this like 600 to 700 cycles, they're still. You compare with others, carbonaceous material or lithium ion battery, they goes down to 10,000 cycles.
The technical supercapacitor, the 10,000 cycles and all you will see for supercapacitor. For battery, generally we cannot go to 12. You can try for 10,000
That-
cycles, but that particular cycle will run for 3 years.
But you stop there in around.
If we stop it,
Yeah.
stop it by
Without seeing-
1,000. Stop it by 1,000 because it takes time for it to charge.
Yeah, and you said that Crucian blue are organic. They are actually not organic.
I mean, it's kind of for the structure. Yeah, we don't go the analog. Mostly, we are using many kind of organic foods.
Thank you. So if no more question, we'll thank Dr. Datta once again. And on the behalf of organizer, I would like to, it is my pleasure to give a small momentum.
Here, I will say that sir has been my guru.
Our next speaker is Dr. Raghumani Singh from BARG. He is a scientific officer G. He did PhD from IIT Kanpur in chemical science and postdoctoral fellowship at University of Victoria, Canada. His area of research includes luminescence and magnetic nanomaterials and their applications. He received many awards and recognition. Some of them are, he is a fellow of National Academy of Sciences, India 2016, fellow Maharashtra Academy of Sciences 2013, and Scientific and Technical Excellence Award 2012 by DAE. And he is also inclusion of name of top 2% scientists in 2020, 21 and 22. And he is a TRSI bronze medal 2022 and MRSI medal 2022. Of course, he have around 165 papers with high repute journals. And he is a reviewer for many journals like JACS, ACS Nano, Journal of Physical Chemistry Letter, etc. With this introduction, I request Dr. Raghumani Singh to deliver his talk. Dr. Raghumani Singh.
Mornings. Thanks, conveners, for inviting me here. And this is, I think, third time came to the NICERS. I think even 10, 11, I came to the IEP. So, and also, communities for research and many is nice senior colleagues and many faculties, students. I'm so happy that I will give some small work for BRC. The pattern of my work is actually this. I draw force for the light making display and light harvesting and biosynthesis. So this is particularly today because this is they said that HBNI student meeting some. So I thought it may be particularly student may benefit some. Just 5 minutes I talk about the what luminescence because maybe some maybe knowing somebody, but I think particularly students may be benefited. Luminescence is the process of emission and ultraviolet or visible or represent or speakable light or other force or like this obtained. Depending on the source of light or force determined by the point. One is bioluminescence. Some living organisms source the luminescence. Fireflies, starfish, jellyfish, you can see the examples. Bioluminescence, it has happened during the chemical reaction. In electrochemical reaction, it is named electrochemical luminescence, electrochemical luminescence. Many organic reactions you can see. Luminescence, it is produced during the castration. The precipitation, castration, or sodium chloride, potassium chloride, you can see some of them. And the electroluminescence, it is related to the response to electrical current passed to the phosphor, the emitter light is coming out. Like electroluminescence, a beam of electron, high energetic electrons coming out from the electron gulls when the applied voltage is about 10 kilo One is provided the rays of electrons is not catalase. If the catalase is used to excite the luminescence mechanism such that possible light will be emitted, and this is the non-cataloluminescence. So mechanical luminescence it is designed for any mechanical force or pressure, which is one mechanical luminescence. The photoluminescence today I am most discussing photoluminescence in this year. But photoluminescence, that's when the source is electromagnetic light, emitted process is called a photoluminescence. Okay. The absorption of the photon or light makes the excitation electron at a higher energy event and on at the ground state. When the source is removed, the whole equation occurs leading to the emission. Emission may be of the two types, delay and the fast process, depending on the spin around or spin orbitals. So luminescence bombardment of ionizing radiation such as gamma ray or beta ray or X-ray is one method for luminescence. And sonar luminescence, this is produced from the converting bubbles in a liquid when excited by this with sound wave, and thermoluminescence which is related to the draft balance this coming off from insulator or semiconductor or surface heating. So two types of photoluminescence you can see. Most luminescence, one is the down conversion or up conversion. This down conversion, what is this? They have the excited ground state excited state level. So sufficient energy given here, energy of the gap, its electron goes from the ground state excited state, the hole formation here, the electron is coming here. So electron hole information gives you emission. But most of the times what it is, this excited electron goes to the trap event because of the tracks or other properties, and they come back to the emission occurs. Another was that up conversion. This is again different from it. Here, energy of the emission energy is less than of the absorption energy. Here, down conversion is opposite. In down conversion, the electron goes from the ground state to the excited state E1, and here stays for more time. It doesn't take less than minus 15 seconds, but the excited state is longer lifetime is there. So another, because we are continuous, force was given, this another electron hit again under this electron. So this goes again excited state. So it means some of the metastable state they can stay for more time and then emission occur for the excited state event. This emission energy is more than the proportion energy. This is called up conversion. This type like that global indication per minutes. So frequency down conversion, I already told you, in down conversion, high frequency light source UV or visible or light is used to get the visible or near light. Some excited state energy get losses. This loss gives like a non-energy process or hit to the surrounding light at a longer wavelength occurs. Okay. In the DC down conversion, there is another term quantum cutting. In this process, one light with the wavelength would push a 2 lambda or 3 lambda. But something you can see, but I will not discuss about down conversion. Okay. But this one particular quantum one, I will not explain this here. So it is most of the in the case of the luminescence, EBC, organic, inorganic, all the time sensitizer and activator, or donor or acceptor. This is the concept always happens. Just only this one. So take a sensitizer or donor that absorb light. Okay, sufficient as absorb and emitted here. Then activator produce emission. Or what we do? Emitted light is absorbed by this activator and produce the emission. So this is one sensitive activator energy transfer because absorbed light and emitted light is here from the sensitizer is absorbed by the activator and this emission over from the activator. This is what sometimes donor acceptor concept. So you can see many things. Most of the in the luminescence we can see, the two types of energy transfer, or the texture, electron energy transfer or post energy transfer here. Okay. Post energy transfer most organic chemistry or biomatrix, bioproteins, those DNA works is mostly. But the texture energy transfer also most working for material science mostly. Okay. But what are working in material science? So this some of the you see here. Post energy transfer is that is proportional to this distance of the R. Okay. Whereas the distance or 6. Okay. So this means this radius is more means your radius is not decreasing. This is the one. Okay. And this energy transfer is very this transfer is actually here for 0.65 it is not 50% finish. But the initial force energy transfer around 3 nanometer, we can do it is around because image transfer then occurs. This first image transfer is longer. You can do more donor filter, longer you can do. So my today topic is why we need to then tonight there are both this is one importance. So rentonite compounds, if you take an example, some of the compounds, European bauxite as person carbonate and sodium nitrate and sodium bauxite, carbon nitrate, and is the topic, the photoluminescent intensity in the visible nearlight reason due to the low absorption process. So they are photoluminescence. The photoluminescence is from the forbidden nature of the air transition ability structure. The air transition is very soft due to the negligent effect on the surrounding organs by presence of the outermost shell, IS to 5P6, whereas 3D transit is broad due to the precipitation effect from the surrounding organs. So similar to, then why you are dropping similar to this? Why this is? So in addition, that ions in the above retinal compound have the photoluminescence because of the cross section among the retinal ions, known as the plasma we have. However, this forbidden nature of ever transit can be reduced by the precipitation by the retinal ions, such as the inhibitor occupied the solid site. Therefore, few amounts of parentalite, 1 to 2%, drop the simulator in order to reduce the cross section. The range of simulator must be very large, otherwise, this will not absorb visible light because one luminance in the visible light is not absorbed. This like range is really for the compound. Advantage of the side of the simulator is a large number of photons can be absorbed by the band gap of the simulator because simulator has an around transition. And doing this, many electrons from the valence band can be brought to the superconduction band. Many holes are trapped in the valence band. Neutron hole redemption may give rise to emission. The emitted light from simulator could be absorbed by the nearby dopant ions, and the emission intensity is very high, because of image transfer, because of image transfer from simulator force. So this is one of the example I give you that electrons 4F6. You see how absorption occurs at 395, 7F0 to 5N6. Emission occurs, for 5G0 to 7F1, 592 in rated upon transients. The entry time potential 5G to 7F2, 650 rated upon. You see here this 4F6 system. This is usually the Coulomb interaction. They give you, 7F ground state and the 5D and the 5N6. You can see that, you can see many others, because of the Coulomb interaction. And this between Coulomb interaction, there's a spin orbit coupling. They give you 7Fj, give you 0, 1, 2, 3, you can see. And 5G also 5G 0, 1, 5G 4. Why did they have the spin orbit coupling? But again we have the strike splitting because of this because of the component from crystallography, and you can see in structure splitting. So this energy diagram, you can see this all energy diagram of this group. So is it for learning from how to generate this the term symbol. You can see that how that term symbol comes. You can see here. Suppose if I do this first arrangement of this one, you can see this. Okay, 7F. So there you can produce the term symbol different orientation because this reference, the reference can go to health such that then happen this consumes and follow this right there. The arrangement of the energy. This you can see here. Many energy that you can see here because of this retractions. So you see that if you see glass that electron a few examples of the SPGF, you see S is a lithium, you see 1s to 2s1, and E block you can see boron, manganese you see 3d5, 1s2, and but manganese 2 plus is that 3d5, it doesn't have surrounding. So all this time began attacking. And there's a broad peak in the manganese peak, for instance. Okay, broad peak as well. The transition of peak is shifted, but airborne do not shift in the transition. Except 1 or 2 nanometers. So this is European, you see it from 3 plus set is 5S2, 5P6 is surrounded in this way. The electron transit is soft and it doesn't have so much. So this is the using manganese emission as a typical illustration only. You can see the broad peak or the European or West Coast and chromium, they very soft peak because of the just around the ever transition. And if the transit, positive transit, if the transit, okay, occurs or mechanical transit can occur here, okay. So this Nobel Prize given to 14 in the physics, Akashi 91, it is no more like guy, and the student Amano and Nakamura is another group. How they started on price actually this, and he started, but he used to, Mano joined 1990, and they started getting back formation. After 20 people getting back, they use ammonia to beat him. But when this, when they were hitting or irradiation something, luminance improvement. Why this improvement coming because of irradiation hitting? This explained that actually because when they are hitting ammonia, the ammonia compose nitrogen hydrogen, green nitrogen interact and green nitrogen formation, but hydrogen goes into the side. This is 1990 years expanded mechanism. What are has shared the known price. This is the known price index. This is the only known price with physics for the invention of the activity. But question is like that, whether only green nitrogen best solve the light emitting there. Oh, because it need error. Because only blue light is the blue light emitting very important because this will shape any energy. So if we have the yellow emitter, it can get fine emission. So this actually, in the time, I think this one paper, but before we are submitted, I think 14, submitted in 14 in the February. And then happened is we saw that green matter important. So in the time, September announcement came on price announcement and how the green matter is useful. So that you can see more progress mentioned science for this month. You can see more detail of the how the price comes in this green matter. So I already told you there are block materials is here. You see here the valence band, connection band and valence electron goes to this connection band. The electron only comes text stress. But if we have the electron ions having absorption process and this energy is most energy transfer of this. Okay, so you can see very good emission from the this electron. So if example you see the electron oxide you see here. This is one almost energy, but it's the absorption spectrum. You can see this. You see absorption spectrum here. You see here is around 20 orbital unit. But if we here, in the case of S0 European, we can get around more than around 100. So if we drop European and we get a enhancement here, we take this from the process for the European here. So this is one of the why we're talking this. So this we are we publish as photonic this important this how this you see here I told you that this sensitive to the active energy transfer. Now serum absorb light here around 280 here around 280 absorb and the energy transfer to the serum absorption processing here very high and the we get here around 10 and the serum is very weak. But this can be energy transfer here. So we found it using serum emissions, the serum emission from that is dropped by the terbium emission enhanced because T55 is because of terbium saturation and 2IT is because of serum. So it enhancement in the C. So this lot of we have done experiment and how one example one is why this coming here. We can use for other sensing. So we use the sensing for the glucose and the scobic acid and isotope. One example like the serum 3 is suppose with reaction with the proton permanganate, the serum 3 plus the serum 4 state. When serum 3 4 plus state when ascorbic acid interact serum 3 plus state. How to prove this luminescence? This is the question. Here is the luminescence of this serum terbium one compound here. We do the luminescence, when you put the potassium permanganate luminescence almost pointing. But when you put the ascorbic acid luminescence because of the serum plus 3 state, we convert the serum 4 plus state. Now serum is no longer for protons. This side luminescence not seen. Okay. But when the serum 4 plus state, when the scope is putting with the global serum plus 3 state, we put a luminescence. This on off you can do luminescence. Right. Another was what we do actually what is this good. We're talking European system and Bernadette. What we do to happen is this actually many people said that Bernadette is mostly monophase or tetragonal some reported. Okay. So here, what happened is if most of people is that tetragonal phase is more of tetragonal phase luminescence more than one. Many people written, many books written. But we thought why this happened is so this is that increasing the luminescence when the ratio of molecule to tetragonal phase. So now we are opposite way of doing this. We found it all the molecule phase is more But Tinago plays more, but when the molecular force is more in this mode, still we have got luminous pathway. So nothing to do in the petrography. This because this would absorb the this UV light here, absorb from the innocent the image transfer. Nothing to do with petrography. It's improved in the chemistry. And this is one of this what for this this we see the previous source, right? That freedom is a very good image transfer, exposure, image transfer. Yes, you do in the white people system. But in the case of serum, we are dropping the white people European. What about the dominance and again points? It's to the opposite cases. How to explain this question, right? Then then one hit it. Around 100 degrees centigrade dominance and again come back. So this apartment is this one how to explain because the European Y is ionized and the serum ionized more than of the Y. This is happening because of this data this compound white people data going case come to the historical case. Okay. In the historical case, there is a like a zeolite type structure. They have the water is sitting in the pore, and because of the water is the quenching. This way this happens. Okay. Because the compound when you put the serum ionized more, is coming to the horizontal phase and luminescence quenching. When heated again, the horizontal phase from the general phase, luminescence recover. This is the one. This is the water is. In this we prove we have explained here that water is limited to aggregate is again. And then something we do the bismuth again. What happened to this? Because already we the bismuth very good sensitizer. And this is same thing happened. This will dropping again, luminescence again, quenching, again heated, again luminescence come back around 500. And we prove how this happened. Water is responsible because we do that this compound preparation G2 around 2 liters we use for the compound preparation. And when people in G2 media for the luminescence again better. Why? Because of the G2 vibration of G2 is less than the water vibration. Okay. This happens because of the luminescence is the response to water. This try to how to explain this actually. When what European is absorbed by G95 absorption, second or bottom of the water again messing with this luminescence because of the quality. And this how to prove again something because we are very I find how to explain this immediately. We thought it. Okay, we know that any compound, prepare any compound, what is the surface water is there? You know, down the water. But now this water is where coming water? This is there. This water actually this microsystem in external phase. You see water in the compound region around 7 angstrom, and this is the example. Okay, another also here water. Okay, they can see. And surface water you have 400 burning, and compound water then over burning. This is how to explain this. So I did want to explain it in the GFR one explain I done in the GFR one I myself did. What happened is when I explained to room temperature this compound, we do this we can find the room temperature we found that water is sitting here, water is we see here. We go spinning, we have to do magic otherwise you cannot see it. Okay. So this when you do that when the temperature decreasing, we found another extract here. But maybe this restrict, this animal is not spinning, and this, because of this this surface water is quenched, okay, and this cold water is mined. This we prove this that how the confined water and the surface water proved by this one. I hope this is it. I have then proved this. So this then I thought that how why it extended here another extension. Another was what in this, we have in the US, we have neutral facility. This neutral facility we can use the proving of the water, but we cannot use water because getting intensity very process very high. We sense water depression in D2. Around 5 liters used for this compound by the D2 people have to feed minutes. So then what do we do? The first solution, like more water, how does this neutral person speak like that? And water in triangular regions like that, or horizontal pole, this one, okay? And then when water is poured in triangular, how to make it fix, okay? This one, I showed one because we have the many temperature depending, we have that how to put this. Just 300 degrees centigrade, we do with the river analysis, it's not fitting well. But when the water is fitting well, this is the one of the we prove what you for and phosphate. Two compound we prove. We publish in the letters. Now, how we can again you see here, here, water here, another water here. Okay. So this group, this is mass specifically also, this here also. This is surface water is removed, and the two is water is coming out. Okay. This is the very stable. By this analysis, this is mass specifically. And this I want original work from the PRC. I can talk about lot reported in this system. This is finding water molecule in the core of the natural first by TG marker. And the distributed water molecule in the core and surface water by sustained mark. And stability water molecule up to 100 again. The case of phase that up to minus 50 degrees, we go to minus 50 degrees negative and never 12 doesn't work. And finding water molecule in the core and triangular surface, then it's get. So now, just some of them we prepared this in a system for the bioimaging and film for the bioimaging. This I will not explain too much, but because time is limited, I was upcompensation luminescence. In case of upcompensation luminescence, excited energy or frequency less than of the emitted energy. Okay, it means the wavelength excitation is more than of the emitted energy. This is started as for 5 years back. So this upcompensation process, just the first person is joined. Is actually started like in France. They started the upcompensation first. Okay. Here, see this here. This is APT effect. Such as that absorption here. They start. You see there, two photon absorb and then energy transfer here. Okay. This point. This is the highest the system YBRL system. YM3 is force. And it's constant right, RBM talking, two-step absorption here. And under property sensors, already YB type of dropping, the two ions absorb and emitted transfer to the terbium to be emission. So there are many way of the process. So the internet-based frequency of conversion, beneath here, because of the due to presence of metastasizing element in the higher excited state, due to the spin of the coupling, new transits, absorption, emission can check that such metastasizing state level can be used for the upconverting process. Okay, example is a sodium sulfide system. But anyway, today I only use the inhalation, something I will talk about later, and the system also was but the ever transfer is the best. It will upconvert. This we published first report in the world paper published now that the near-infrared imaging is responsive to the infrared, and that this the most modern composed for the hyperthermia depression induced by the fluorescent radiance transfer is will upconvert this for me. And this here, this particularly student infrared, this YBRB, there's one green and the red. You can see here. This green red you see here, but it is normally not excited. You don't see any, it's almost transparent. This compound transparent. But when actually you can see green emission. Okay. This green energy is the how coming this actually two photon this absorption occurs and this excited state energy there is a process some green emission as well as red emission here. Okay. This green emission can be used for the photothermal heating. What happens is outer snow parting, there's the surface particle resonance. Okay, yeah, sure. The surface particle resonance absorb this, that heating focus. Okay. And this can be again this process of these two processes can be used to the temperature sensor. So I got to explain this. Now whether pressure coinciding effects useful in the case of this one. Yes, it is useful in getting the high luminance intensity point such as photon intensity is more than of the critical photon evidence. Gaussian structure can improve luminance intensity through the image transfer, image bias, and image transfer. So another what paper will be 21, the super bright conversion this system into contributing and the you see here one of the first report I want telling that here in green emission now you will see any green emission. Any times on any paper I found that some green emission is here, but we don't find green emission now. This is the first report in support this paper. Around 40 citations came from the 2021. And all over the many people has cited. I can explain this work. And then we had the bioimaging system by the down conversion, up conversion, performing system. And we do again smart methods for optical heating, hypertrophic cancer, neurotherapy, like this will have done many effort, many purposes. And I was seeking sensing with the kind of strength. Another was to 22, we come out the Mesopress, this system of partner potent system. We do this partner with the Mesopress silicon wave, and for the imaging and drug loading, the therapy system for this power. We have done production with the SPEC studies and with the SPECs, imaging we have that. And the conclusion of my talk is this is the use of radar talk in different areas are mentioned briefly. Means of difficulty in down conversion and up conversion processes are provided. Display light harvesting and luminance on off switching. Stable water up to iron degrees indicate. Degrees of freezing temperature up to minus 50 up to 58. The temperature sensor and diagnosis and therapy, imaging through the up conversion process improve the diagnosis therapy. And thanks Jackie for expression. We have some our second head here. He's sitting here and then Sujita, yes, the couple my experiments on my responsibility, my students. Most occupying position in India. They are working with me and coaches very well. I perhaps with him last around more than 10 years. Thank you for your support and thank you for your presence.
Hello, the talk is open for the discussion. So once again, question from the student side. That is 2 questions.
So any questions? So otherwise, I'm not giving. Okay.
In the luminescence process, you have shown two processes. One is uphill process and one is downhill process. In the case of downhill process, we saw that when in the case of emission, first from the E1 excited level, it is coming to a E2 level, which is a kind of metastable state.
Yes.
So my query is that that E0 level and this E2 level, they have the same spin multiplicity or different?
Yeah. So but yes, this spin is maintained. Sige.
Any other question?
But it's not be compulsory, huh? It's maybe compulsory. Difference also can still, yeah. It also. You can also take that. One more question. Yes.
Dr. Ragumani,
Yes.
see, you were talking about this up conversion. What is typically the efficiency of up conversion?
See, this conversion so far, I can see it's quantum gene dot 1-2% not already.
So what is the strategy you should have so that you have a much higher quantum gain?
Yeah.
So
this is
depending on the up
another one.
conversion efficiency, if it can increase it, then I will find better applications. What
Yeah,
should
this
be
is
the
the one of
strategy?
these, but one to the photo evidences. Photo evidences, people working more than use photo evidences. This is I think they have no reports from us because the compression is not switching, it's a quantum mechanics compression. So, but it's can be improved by photo evidences. You can use this thing.
Some people have gone up to even 7 to 8%.
Many people reported, but see, energy losses so much, See, people talking, say 7, 8, something. I don't think, because if you see for the Gen himself, he knows something, But people written, many people, this paper, I don't think so, because energy losses so much.
Thank you.
Hi, sir. I want to know about which method you have been used to synthesize yttrium phosphate nanocrystal.
Which one?
Yttrium phosphate.
Yeah, okay.
Which method you have been used?
Oh, this is white paper or sodium fluoride?
YPO.
Oh, this is a coarse precision method. You use the Y ions, use the ammonium hydroxide, okay, put the hydrogen is medium, heat around 120, 130 degrees.
And also regarding that up conversion, it is a 2 photon or more than 2 photon.
Also 2-3 photons. Sometimes 3 photons also occurs. Sometimes I found 6-7 photons.
Hi, Professor Ragumani, I have just one question.
Exactly. Yeah.
So this is this upconversion part.
Yeah.
So what laser you used?
Oh, either we use a 980 laser or I08 laser.
So is it the photon density is very high or is it just normal?
Yeah, this we do around 1 watt, 2 watts, depending upon how this is.
Okay, so you focus it tightly on the sample with some
Oh,
objective.
do you have that this web guiding? We have one. Okay. Yes. What is the up to bringing web guiding? Okay. We are using that.
Okay, so
Otherwise, you can bring together also. It's no problem.
any problem with photo bleaching at that high
No, no.
photon density?
Photo bracing is like a photo bracing is organic chemistry, but it's inorganic chemistry. Inorganic compound. Photo bracing will not come here.
Okay.
Raghuvan, you mentioned about that water cluster in that hexagonal pores, where they remain liquid water even at very high temperature as well as very low temperature. So what is the size of that
Pore.
not the pore, the how many water clusters?
Water clusters per molecule or white paper because we all the two.
So in
Clusters,
one pore there are,
one cluster is cell.
yeah, so in one pore there are two water molecules.
The one,
That's what you're
one emission, the one emission of the white paper has a one, two molecule water is there.
So in that case, can we say these two molecules of water as liquid water or anything?
This actually, this maybe, in the form of gas, because
Yeah.
it cannot be hydrogen bond,
Yeah.
Otherwise, just, see, how we do NMR? NMR is not also brown molecule, right?
Money. For one molecule, there are two water molecules.
Yeah.
For one molecule.
Yeah, so in that case, if in one pore if there are two molecules, can we say it is liquid or it is not free?
No, I want to say, one question of the mission has been two molecules. So this, you can say, around gas. Maybe this, maybe
So it
gas,
is a kind of trapped
some trap
water molecules.
Yeah.
So it is difficult to say it is liquid
Yes.
or it is not freezing.
Yeah, not
because-
freezing. Maybe this.
Because two water molecule, no matter what will be the
No.
temperature,
See, actually, they have
not the ice.
this was of this two water molecule maybe in the elongated way of interest.
I think,
Okay.
I think we can discuss during the lunch time. Okay? If no more question, Ajay, you want question?
Yeah, just 30 seconds. No, I'm responding to Dr. Alam's. That see, oxygen distance in case of drinking water, ice, it is 2.75 angstrom around that border. But if it is gaseous, then it is your around 3 angstrom distance. So from the distance, if it is possible to get the measure of distance, then it is possible to get whether it is in the ice condition or in the water liquid condition.
And, I think no more question. I will thank once again Dr. Raghuvan Singh on the behalf of the organizer. My pleasure. So the next speaker of the session is Professor Paranappa Nembena. He did his master degree in chemistry from Karnataka University, Dharwad in 1999. He obtained his doctoral degree from Göttingen University, Germany, under the guidance of Professor Gerbert Rosaki. He worked as a postdoctoral research in School of Chemistry, Monash University, Melbourne. From 2008 to 2010, he joined as an assistant professor at School of Chemical Science, Mysore, Bhubaneswar, in 2010, and he was promoted to associate professor in 2018. His research interests include synthesis and reactivity studies of complexes with low valence and or low oxidation state metals and main group metal catalyzed organic transformation. Professor Paranappa, please.
Morning, everyone. Thank you, Professor Ripana, for this introduction. Next 25 minutes, I'm going to talk about unusual in-one chemistry, two synthesis and catalytic studies. So actually, we're working on main group chemistry. Our main objective of our group to design ligand system by taking those ligand systems to construct metal complexes
across the periodic table, in particularly S and elements. And then after preparing metal complexes, we can use those main group metal complexes for various catalytic applications. In this talk, I'm going to talk about only this area. These are the recently published research articles on zinc, unusual zinc chemistry and application of molecular zinc catalysis. So outline of my talk, first I will brief about how we developed ligand system that is conjugated bisguanidinate ligand. It is analog of popularly known as NAC ligand. By taking that ligand, how we can construct metal complexes, then also what are the bonding modes of those ligand, and then I will talk about how we can isolate unusual deep complex, and then I will move to the synthesis of anhydride and catalytic applications of anhydrides. So here is this is simple guanidine molecule. Many natural products, and drug molecules containing this guanidine core. You can see the central sp2 hybridized carbon atom, which is connected to one amino nitrogen and two amino nitrogen atoms. So when two guanidine units connected to each other with common nitrogen atom, there will be a bi-1-ide, or if you find a conjugation, then you can call it as conjugated bisguanidine, start to abbreviated as CBG. So how we can access CBG? Actually, unsubstituted CBG synthesis is known in the literature. As far as the tetraaryl substituted guanidine molecule is concerned, for the first time we developed in our laboratory by taking aryl carbodiamides, two equivalents of aryl carbodiamide that is treated with ammonium chloride and triethylamine in ethanol. Okay, the in situ generated ammonia adds to the two equivalents of carbodiamide that leads to the formation of conjugated bisguanidine. We can see basically this tetraaryl substituted CBG molecule. It is a combination of two CDI and one ammonia molecule. Right? So this way we constructed the CBG ligand. Here the various less bulky to more bulky CBG ligands can be synthesized by using the appropriate carbodiamide precursor. More interestingly, we found 5 different bonding modes for this CBG ligand. Here you see LX type, L2X type, X type, LX, and L2. In each case, we isolated the crystal structure, okay, that you can see here. So now I will see synthesis of first examples of zinc 1 and magnesium 1 diamonds. We know that the chemistry of group 2 metals is dominated by the plus 2 oxidation state, and those metals are in non-redox in nature. Similarly, zinc is stable in plus 2 oxidation state and non-redox in nature. The question comes, is this possible to isolate the magnesium 1 compounds and zinc 1 compounds in plus 1 oxidation state or not? So, for example, magnesium dichloride, magnesium dibromide, these reagents are commercially available. Then you think about Mg2Cl2, which is not stable. Why? When this Mg2Cl2 immediately undergoes disproportionation that leads to stable magnesium dichloride and elemental magnesium chloride, where the magnesium oxidation state is plus 2. So one can replace just the serial allied ligand, small ligand, into bulky, and chelated ligand. Thereby, one can kinetically stabilize the magnesium 1 dimer. It ceases the disproportionation reaction. Thereby, the isolation of magnesium 1 is possible. So, keeping that in mind, the Jones group first they reported NAC stabilized magnesium halide upon reduction with potassium that led to the formation of dimeric magnesium 1 compound, which is the first example reported in the literature where the magnesium oxidation state is. As far as the zinc chemistry is concerned, the Pomona reported unexpectedly they got this dizincosine molecule where the zinc oxidation state is +1. How they achieved the thick strong zinc, the treated with commercially available diethyl zinc, instead of heteroleptic CP star zinc ethyl, unexpectedly they got CP star 2 zinc 2, where the zinc oxidation state is +1. So later, by taking this LZNPR, they treated with Mesnet and magnesium 1 dimer, they got LZNMG, and the LZNMG, if you treat with ZNPR2, even not only +1 oxidation state, it recent reports suggest that zinc existed in 0 oxidation state. Here, here the mixed oxidation state zinc complex. Okay, central zinc atom will have 0 oxidation state, and side 2 zinc atoms are having 1 oxidation state. So these are the literature report. So what is our contribution in this area? As I mentioned earlier, we developed the ligand system. By taking that ligand system, our goal was whether is it possible to make zinc complex in the +1 oxidation state. That was the our problem. So we choose this as the precursor. There are drawbacks of the CP star zinc 2 complex because this molecule is thermally unstable. So above the -10 degree, it decomposes. It gives to elemental C. So it hampers the further reactivity of this molecule. So considering that one, in situ we prepared this CP star zinc molecule. When you treat with one equivalent of our ligand, then we got zinc 1 complex, heteroleptic zinc 1 complex. There are 2 methods we employed. On the other hand, CP star 2 zinc 2, when you treat with zinc hydride, we got the same molecule, where the zinc oxidation state is +1. So further, this one, if you treat with another equivalent of ligand, then we got the CpG supported zinc complex. This is thermally stable molecule. Okay. So alternatively, this homoleptic zinc 1 dimer can be accessed by the treatment of this one two equivalents of ligand to got the same molecule. More importantly, which is confirmed by executive structure, you can see here the zinc zinc bond distance is 2.40. So now we used that the zinc 1 dimer as a pre-catalyst for the dehydrogenative borylation of terminal alkynes. When terminal alkynes we treat with phenol borane in the presence of zinc 1 dimer, we got this product. You can see, and moreover, we have done the several stoichiometric reactions to understand the reaction mechanism. So here, the heteroleptic zinc 1 dimer, when we treat with terminal alkyne in the presence of toluene, we got this zinc acetylide complex. Similarly, the zinc 1 dimer, when you treat with terminal alkyne, we got this zinc 2 acetylide complex, which is conformed by the crystal structure. Also, when this zinc acetylide, you treat with two equivalents of HB, then zinc hydride and this product in 25% conversion. And to that mixture, we had further terminal alkyne in the benzene disease. We got zinc acetylide and this alkyne boron product. So based on these stoichiometric, several stoichiometric reactions, we established the reaction mechanism. You see, the heteroleptic zinc 1 dimer, when you treat with the terminal alkyne, we got this zinc acetylide complex, which is the actual catalyst. Okay, here the zinc 1 dimer acts as a pre-catalyst. On the other hand, this homoleptic zinc 1 dimer, when you treat with terminal alkyne, dehydrogenation occurs that leads to the formation of zinc acetylide complex. So then when zinc acetylide reacts with HBC, there will be a ZNC BH bond sigma bond metathesis that is in equilibrium that leads to the LZNHN product. To this mixture, when you add another equivalent of terminal alkyne, there will be elimination of hydrogen gas and regeneration of the zinc acetylide complex, then closes the catalytic cycle. So next I will move to the zinc hydride. So ZnH2 is a polymeric in nature. The first time when you take Schinger and co-workers reported the preparation of ZnH2 polymeric zinc hydride. So lithium aluminum hydride, when you treat with the dimethyl zinc,
then they got polymeric ZNH2. Very recently, Okuda group reported when you treat dimethyl zinc with the alane, they got this polymeric zinc dihydride. There are several drawbacks of zinc dihydride. Insoluble in organic solvents, thermally unstable, polymeric in nature, pyrophoric, and difficult to crystallize. So, overall, it is very difficult to do the further chemistry by taking this polymeric zinc dihydride from. So, now question is, by taking this CBG ligand, whether is it possible to synthesize, CBG ligated zinc hydride? One thing I want to mention, the synthesis of heteroleptic, alkaline earth metal complexes and zinc complexes is always challenging because most of the time undergoes blank equilibrium that leads to the formation of homoleptic complexes. So here we took our CBG ligand. When you treat with dialkyl zinc, the deprotonation of this more acidic proton, the formation of CBG ligated zinc alkyl complex. Then this zinc alkyl complex, further when you treat with two equivalents of hydrogen, there will be an alkyl halide exchange reaction that leads to formation of CBG ligated zinc iodide complex. This CBG zinc iodide, when you treat with potassium amidoborane, that is the hydride source, then we got the CBG stabilized zinc hydride, which is dimeric in nature. You can see in this annotated NMR spectra, proton NMR spectra, this is the NMR spectrum of this CBG ligand. There is a characteristic peak at the downfield region that corresponds to this NH. When you convert this ligand into, CBG supported alkyl complex, there is a complete disappearance of that NH proton. In the upfield, you can see two resonances that correspond to ethyl. Right. When this molecule converts into iodine, right, then there is the absence of these, resonances in this region. Further, when you convert this CBG zinc halide into hydride molecule, there is a signature peak for this ZNH resonance in this. So now, if we have this heteroleptic, CBG zinc hydride in our hand, so then we decided to do some catalysis reactions such as hydroboration and hydroxylation reaction. What is meant by hydroboration? Addition of BH1 to unsaturated bond, we can call it as hydroboration reaction. Hydroxylation reaction is the one. Addition of SiH bond to the unsaturated bond, that we call it as hydroxylation reaction. So, here the isocyanate, when you treat with two equivalents of HBP, then they got diboryl bisphenol amina by Wakoda group by using the magnesium and the catalyst. Then isocyanate, when you treat with two equivalents of HBP, they got mixture of products, one is hydrodeactivated product by taking back and into alcohol. But by using our zinc hydride catalyst, so we got exclusively selective synthesis of N-boryl formamide, this boryl hemiamina, and N-boryl methylamina, depending upon the stoichiometric amount of HB. For the first time, we converted isocyanate into N-boryl formamide by using our zinc hydride catalyst. So here various substrate scope we have performed, but I'm not going in detail due to time restriction. But you can see here how we can convert isocyanate when you treat with one equivalent of HBP in the presence of zinc hydride cation, we got a quantitative conversion of N-boryl formamide. On the other hand, isocyanate when you treat with three equivalents of HBP, there will be a hydrodeoxygenated product, H2O product, that is N-boryl butene. So, to understand the reaction mechanism, we have done several stoichiometric reactions. You see, the zinc hydride, when you treat with, dip NCO, then we got the zinc formamidinate complex, where the signature peak of this 4.52 of zinc hydride is completely vanished. Then we observed that this NCH4 resonance at 7.3 ppm and 172 this corresponds to 13 kmol of this carbon. Okay. And in addition to that, further, when you react this zinc formamidinate complex with another equivalent of HPP, we got the zinc hydride and N-boryl formamide. Right. Moreover, the CBG zinc formamide complex which is performed by extracrystal structure. So this zinc formamidinate complex, when you treat with 2 units of HBP, we got the zinc hydride and this hemiaminol product. This zinc formamidinate complex, when you treat with 2 units of HBP, instead of room temperature, you heat at around 70 degrees centigrade for 2 days. That leads to the formation of zinc boryl oxide and hydrodeoxygenated product that is N boryl butane. Right. So moreover, we have confirmed this side product that is CBC zinc boryl oxide is confirmed by say crystal structure. So we have done several stoichiometric reactions. We isolated the intermediates which are confirmed by excitation structure. Based on all these evidences, we established the reaction mechanism that goes in this fashion. Zinc hydride reaction with isocyanate, formation of this zinc formamidinate complex, which is confirmed by excitation structure. This CDC zinc formamidinate complex, when you react with HBP, sequentially, allows the formation of N-boryl formamide product and regeneration of the zinc hydride catalyst. This zinc hydride catalyst further reacts with another molecule via this reagent and after reacting with another equivalent of HBP, there is this hemiaminol product. Then this reacts with LZNH, CO bond cleavage, then that leads to the hydrodeoxidation product that is N-boryl amine and zinc boryl oxide. This zinc boryl oxide, when it reacts with another equivalent of HBP, elimination of diboryl oxide and regeneration of the zinc hydride that closes the catalytic cycle. Alternatively, this product can be obtained by this synthetic route and this product can be obtained by this synthetic route. So now I will move to the so first we concentrated by using zinc hydride, hydroboration of carbonyls and all. Then we work on hydroboration of isocyanate. Then then we move to hydroboration of pyridine. Okay, basically pyridines are aromatic in nature, whether we can de-aromatize by using zinc hydride catalyst or not. Okay, in the literature, zinc-based catalysts are known for such reactions, but there are some limitations: low selectivity, high catalyst loading, and narrow substrate score. With our zinc hydride catalyst, when you react with HBP, any heterocycle, the pyridine or isoquinoline, that leads to the 1,2 reduced product, exclusively 1,2 reduced product. On the other hand, when you treat with phenolphthalein, we got this 1,2 desilylated product. Now, heterocycles, when you treat with HBP in the presence of catalyst 1, we got this one exclusively 1,2 reduced product. Then heterocycles, when you treat with phenolphthalein, we got exclusively 1,2 monosilylated or 1,2 desilylated products. So various substrate scope have been done. Going into detail, I will focus on mechanistic studies. Okay, here also, we have done several stoichiometric reactions to understand the reaction mechanism. Zinc hydride, when you treat with this 4-methyl pyridine, we got monomeric zinc hydride complex, which is confirmed by exceptional structure. Zinc hydride, when you treat with isoquinoline, we got the CBG zinc amide complex. So this CBG zinc amide complex, when you treat with 2 parts of HBP, we got the zinc hydride and also one to reduce de-aromatized product. So all these intermediates which are confirmed by exceptional structure. And based on this, we established the reaction mechanism. The zinc hydride when reacts with isoquinoline. Okay, first this isoquinoline approaches to the Lewis acidic zinc center, formation of this monomeric zinc hydride complex. Then there will be a 1,3 hydride shift that leads to the formation of zinc amide complex. But zinc amide complex reacts with 2 parts of HBP via this intermediate 3A, and it eliminates this product and for the regeneration of this intermediate 2. This intermediate 2 reacts with 2 parts of HBP via intermediate 3B, formation of exclusively the formation of one to product and the reduction of zinc hydride catalyst. Thereby, it closes the catalytical cycle. So next we move with treatment of zinc hydride with 3-methyl quinone. We got this kind of with zinc amido complex. The zinc amido complex when we treat with phenylsilane, we got zinc hydride and 1,2 phenyl products. Here also, when we treated zinc hydride with phenylsilane, there was no reaction. Then, on the other hand, the intermediate three, when we treat with phenylsilane, we got this mixture of products in 50% NMR conversion. Then this compound 3, when we treat with phenylsilane with elevated temperature, we got zinc hydride and 1,2 bisphenol products. So based on these stoichiometric reaction, again for the hydroxylation of pyridines, so we establish the reaction mechanism. The mechanism goes in this fashion. Zinc hydride reacts with heterocyclic compound, then it leads to the monomeric zinc hydride because these heterocycles are Lewis donor that coordinate to the Lewis acidic zinc center. The dimeric molecule gets converted into monomeric zinc hydride. First step. In that monomeric zinc hydride, when it reacts with another molecule that leads to formation of zinc amide complex, then we bring 1,3 hydride shift. Then it reacts with two equivalents of phenylsilane, then it eliminates the 1,2 phenylated product and regeneration of 2 and 1,2 for monohydroxylation. We have the two products. You might have noticed one product is one monosilanated product, another one is 1,2 bisilanated product. Both these products, how they are obtained, we established that they are mechanistic evidences. One goes in this pathway, another one is separated with the zinc hydride, monomeric zinc hydride reacts with 1,2 monosilanated product via this intermediate. It forms this intermediate by a petrol bond mechanism. It goes 1,2 bisilanated product and concentration of the zinc hydride. So this is the catalytical cycle. So now we move to the where the addition of this pH, NH, OH and pH bonds to the carbodiamide. As far as the molecular zinc hydride catalysis is concerned, there are very limited reports. You see, hydroboration of carbodiamides, no reports are there. As far as hydroboration, addition of alkynes to carbodiamide, only one report is there. And as far as hydroboration of alcohol or there are no reports as far as the catalysis is concerned. Keeping that in mind, we have several carbodiamides in our hand, and the other hand we have zinc hydride catalyst also. Here we have chosen several carbodiamide molecules. When we add HBP in the presence of zinc hydride catalyst, we got N-boron formamidine in quantitative A. On the other hand, when we add a terminal alkyne or alcohol, we got propyl amidine or isourea. When you add RNH2, we got guanidine molecule. So basically, guanidine one can synthesize by using carbodiamide in the presence of zinc hydride catalyst. So here is the reaction. Carbodiamide reacts with HBP in the presence of zinc hydride catalyst 2 mole % at 70 degrees room temperature to 70 degrees depending upon the choice of CDI substrate. Then that leads to the formation of N-boryl formamidine. So here carbodiamide, if you treat with terminal alkyne, we got propyl amidine exclusively the formation of propyl amidine product. Here are the substrate scope. When you treat this carbodiamide with primary amine, we got guanidine molecule. Similarly, this carbodiamide when you treat with benzyl alcohol in the presence of zinc hydride catalyst, we got the isourea solid. So here also, in each case, we have done several stoichiometric reactions to understand the reaction mechanism. So here you see zinc hydride reacts with carbodiamide, then formation of CBG stabilized zinc formamidinate complex. At CBG zinc formamidinate complex, further we reacted with another equivalent of HBP, then we got zinc hydride and exclusive formation of N-boryl formamidine. So moreover, this CBG zinc formamidinate complex which is conformed by. Here, zinc hydride reacts with terminal alkyne, the formation of zinc acetylide complex. That zinc acetylide complex, when we treat with carbodiamide, that is isopropyl carbodiamide, there will be insertion of carbodiamide moiety into zinc acetylide that leads to this kind of intermediate that we call it as zinc propylamide zinc complex. This one further react with terminal alkyne that leads to formation of zinc acetylide and exclude to formation of products. And here zinc acetylide complex is conformed by extracritical structure. So similarly, we also did several control reactions for other catalytical studies. You can see the zinc hydride when you mix with primary amine, we got zinc anilide complex, which is also conformed by extracritical structure. And here, the zinc hydride is mixed with benzyl alcohol, we got the CBG zinc alkoxide. So here, CBG zinc alkoxide also is conformed by extracritical. So based on these stoichiometric reactions, we have established the reaction mechanisms in each case. Here, for the hydroboration of carbodiamide is concerned, zinc hydride reacts with carbodiamide, formation of this intermediate, the zinc formamidinate complex. The CBG zinc formamidinate complex, when we react with HBP, elimination of the N-boryl formamidinate product and regeneration of the zinc hydride catalyst, thereby it closes the catalytic cycle. On the other hand, the zinc hydride reacts with terminal alkyne. There will be elimination of hydrogen because this proton is acidic in nature. This hydride abstracts this proton. There will be elimination of hydrogen, formation of CBG ligated zinc acetylide complex. In this reaction, the zinc hydride acts as a free catalyst. Free catalyst means free catalyst in the catalytical reaction is the one the starting material can get converted into the actual catalyst is here, the zinc acetylide complex. This zinc acetylide complex, when it reacts with carbodiamide, the insertion of carbodiamide into zinc acetylide moiety that leads to intermediate 3. This intermediate 3, when it reacts with the terminal alkyne, there will be elimination of propyloamidine product and regeneration of the zinc acetylide catalyst. So here is the summary. We synthesized zinc 1 dimers, where the zinc oxidation state is +1. On the other hand, we isolated the heteroleptic CBG supported zinc hydride. Here you see by using zinc 1 dimer, we converted this starting material into this product, and by using zinc hydride, we have done several hydroboration and hydrogen reactions. So here are my students, Navin Satwa, Amit Kumar Sahu, Science, Sagarika, and these are PhD students, master students are Manish Patro and Sneha Malik. Most of the work done by Amit Kumar Sahu. He's presenting poster number is 19. You can stop by that poster. If you have any more queries, you can discuss with him. He's the one who had done a fantastic job, insulated, extremely air and moisture sensitive zinc 1 dimers in our lab. Not only that, by using zinc hydride as a catalyst, we established a variety of hydroboration and reactions. Interesting. And also we are grateful to DAE, NASA, HBNI, for the financial grant. This, thank you everyone for your attention. If you have any questions, I'm happy.
Thank you, Professor. Now the paper is open for the discussion. Any questions?
Hello, sir. You have used potassium potassium hydroborin for hydrate source. So why not sodium borohydrate?
Yeah. Whenever, to basically in general aspect, I'll tell you, synthesis of main group metal hydride, but there are several synthetic routes are there. Let's say you can take heteroleptic degated metal alkyl complex. In such cases, when you treat with just HDP or phenolphthalein, you can get metal hydride. Depending upon the starting material, you have to use the hydride stone. And you have to see the tolerance of your ligand with that reagent, and also energetic advantage.
There are questions?
Yeah.
Hello, sir.
When you explain about the hydroxylation of the heteroene, we discussed the deep hydroxylation and monohydroxylation, and also told that tetra bonding. So you told me that in hydroxylation product, tetra bonding is proceed. However, monosilylation, tetra bonding is not occurring. Why? Yeah, it's, depending upon the silane reagent and depending upon the catalyst. Okay, and we have done several control reactions. Based on that, we established reaction mechanism. In one case, we have and also reaction condition. Okay, one first thing is substrate. So what kind of substrate and reaction condition, and depending upon the catalyst choice. So one case, monosilylated product. In another case, 1,2-bisylated product. In the literature, people are observed, but none of them established the reaction mechanism. So that's why we have done detailed psychometric reaction to understand how these pathways are going on. In the case of monohydrosilylation as well as 1,2-bisylation. Yes. Like, is there any existence or any literature for photolytic 180? Photolytic 180. Photolytic, yeah, yeah. Yeah, right. So the three ways to treat with HCl that are responsive protonated form of planar structure. That is minimal. Yeah.
So I have one question. You put some uranium thorium system.
Okay.
So how it will behave? How it will behave? You put uranium and thorium also, some U and here.
Oh yeah. Okay. So I thought the addition of this, BH bond and CH bond and OH. Some people reported some ligands stabilize the uranium and those kind of complexes employed for that kind of catalysis reaction. Our goal was zinc is abundant biocompatible element. Okay, by using this cheaper molecular zinc hydride catalyst, we can replace that expansion function.
You're right, but mostly that is for uranium 4 compound, not the 6 compound.
Yeah.
So uranium 6 will not be active. Uranium 4 will
Some
be
of the
more
uranium 4 complexes are not.
when the compounds is part in
Then
is
you
no.
will find out some.
Uranium 4 compound, part in system of result. Okay, no more questions. So I will thank once again Professor Sarnappa. On the behalf of organizer, it is my pleasure to give you a
I would like to thank Professor Kannan for chairing this session. Would like to give a small Yeah, we are breaking for tea. We are about 38 minutes late. So let's get back to here as soon as possible. Thank you. Okay. The last one before lunch. Okay. For sure. Welcome back for the second session today. We are running late, but we'll try the best we could do. So this session is going to be chaired by Dr. P.K. Mahapatra, who was born in Cuttack, Odisha, and he did his MSc from Utkal University, Bhubaneswar in 1985. He joined the Radiochemistry Division, BARC, in 1987 after graduating from the 30th batch of BARC Training School. He did his PhD from the University of Bombay in 1994 and did his postdoctoral research at University of Mainz, Germany, between 1999 and 2000 under the Alexander von Humboldt Fellowship. His research interests primarily include separation of actinides and fusion products using novel extractants, novel solvents, and novel separation techniques. With this brief introduction, may I now invite Dr. P.K. Mahapatra to take the stage and share this session. Thank you.
Thank you for your kind introduction. I think we are running late by nearly 50 minutes. So I will request to cut down your presentation time by maybe 5 minutes each of you. So around 20 minutes presentation followed by discussion. The first speaker is Dr. Divakar Goswami, joined Bioorganic Division, Bioatomic Research Center. Up from the 47th training school batch of BRC training school, and he completed PhD in 2011. He has a large number of publications and is a specialist in organic synthesis and is targeted ligands for radiopharmaceuticals. I invite Dr. Divakar for this presentation.
So good morning to all of you. Thanks for the nice introduction. And thanks to the organizers, especially from HBNI and either side, for giving me this opportunity to talk about the works we have done in Bioorganic Division. So the title of my talk, as it appears, is Research and Development of Functional Organic Molecules. So I am working in Bioorganic Division, which comes under Bioscience Group in BRC. So I am here to give an exposure to the different activities of Bioorganic Division. And so to start with, we'll first see how Bioorganic Division looks like. So Bioorganic Division is a unique blend of organic chemists and biologists, as the name suggests, Bioorganic Division. So we are a part of organic chemists. We do a lot of synthetic work, usually demand-driven and also curiosity-driven. So we work in the field of ligands for radiopharmaceuticals. We synthesize different solvents for back and fuel cycle. We do curiosity-driven research in fluorescent sensors, green chemistry, heterocyclic chemistry, peptide chemistry, natural products chemistry. So my talk will encompass most of these things. And as we are in the interface of chemistry and biology, we have this opportunity to do a lot of interfacial things, like design and synthesis of functional organic molecules for biological applications. So I also give you a glimpse of some activities which we do at the interface. So to start with the demand-driven synthesis, we'll start with the ligands for radiopharmaceuticals. So what radiopharmaceuticals are? As you all know, that radiopharmaceuticals are a non-classical drug, where a radioactive substance like radioisotopes are attached to a ligand through a linker. And this ligand is actually targeted to the protein or organ, whatever you think. So this active compound, that is the radioisotope, is generally derived from nuclear reactors or cyclotrones. But in fact, this radioligand, this ligand part, that comes from the organic synthesis. And we actually contribute in this part. So why do we need an in-house synthesis for ligands for radiopharmaceuticals? Mostly all of the ligands are imported and are of very high cost. And these actually hampers the affordability of common people in India to use these radiopharmaceuticals. So we design, we synthesize it in-house to make it a low cost and to make it more affordable. Also, a regular uninterrupted supply of these ligands in a form of kit to the hospitals across India are very important. So we do these things, and also using this expertise of synthesizing new ligands, we can have a better understanding of the things and can derive new ligands out of this concept. So the first one is a very important success story of our division, where we could synthesize this methoxy isobutyl isonitrile ligand, commonly termed as MEB, which is radio labeled with technetium-99, and is being used. This radio pharmaceutical is being used for myocardial perfusion imaging. And every year, using this multi-step synthetic pathway, we synthesize around 5 to 6 grams of this ligand and give it to the commercial partner, BRIT, Board of Radiation and Isotope Technology. And they produce this kit, they radio level it, produce this kit, and it is supplied pan-India. And every year, we contribute for formation of around 5,000 kits, which actually serves more than 20,000 patients across India. Another one, which we have recently accomplished, is a PSMA 617. PSMA 617, when radio labeled with 177 lutetium, serves as a radiopharmaceutical for prostate cancer therapy. Because in prostate cancer, this PSMA protein is overexpressed, and we have an antigen for this. So the structure of PSMA, as you can see, is comprised of different amino acids, and the binding motif is made up of lysine and glutamine using an urea linkage. So by using multi-step synthesis, around 14 steps, getting an overall yield of around 2%, we could synthesize this, and we are supplying this ligand again to BRIT for kit formation and supply pan-India. So every year we synthesize around 200 milligram of this, which serves more, which is used for making more than 500 kits, and which is being used for around 2,000 patients pan-India. But the most important success story in this thing is that we could do this synthesis in a very low cost compared to the imported cost. And here also it is very low cost compared to the imported cost. And this could make these radiopharmaceuticals very affordable to common citizens of India. So as you can see here, this is a representative example of a therapy using our lutetium PSMA 617, and this is pre-therapy, and you can see the success post-therapy. So we have done this in collaboration with our PhD and of course RMC and BRIT. So we will have a more detailed discussion on radiopharmaceuticals tomorrow. So I am ending here. But another thing is that we have now ventured into other ligands, which are very costly and being used regularly in radiopharmaceuticals. Like PSMA 617, which I have showed earlier, it is a lutetium-177 binder and is used for a therapeutic radiopharmaceuticals. But what about the diagnosis of prostate cancer? So this prostate cancer diagnosis is generally done by this PSMA 11 ligand, and where this ligand binds is radiolabeled with gallium-68 for PET imaging, and this Hynic PSMA, which is radiolabeled with technetium-99M with SPECT imaging. Since PET is very costly affair, so we have to devise something which can be used for SPECT imaging, which is little cheaper. And so we have devised this Hynic PSMA as a ligand. Another one is this meta-iodobenzyl guanidine hemisulfate, which has also been synthesized and given to breed for radiolabeling, and probably in some months we can get the results and go for RPC approval for commercialization or clinical use. So these are the things where we have contributed as a synthetic chemist to make the known radiopharmaceutical ligands more affordable. But what about new ligands? So one of the things which we have done is, as you know, that bone metastasis is a condition which is which appears as a very painful symptom in all advanced cancers, because when cancer spreads all over the body, it is termed as metastasis, and bone is one of the things which gets affected at a very early stage. So it is very important to get an early diagnosis of bone metastasis to start an early therapy. So early diagnosis is only possible when you diagnose very small lesions in the bone. So using this, generally, a monofunctional chelator, EDTMP, is used for this purpose, where this EDTMP is radiolabeled and this phosphonate group attached to the bone hydroxyapatite. And so it gives a diagnosis of these lesions. But you see, this is a monofunctional chelator where this EDTMP is actually chelating this this radioisotope as well as attaching to the hydroxyapatite. So it happens that when it is attached to hydroxyapatite, this radiolabeling gets more labile. So this very small metastatic lesions are not possible to detect using this EDTMP ligand. So what we thought is that we'll make it a bifunctional ligand where we can attach a chelator for the radioisotope apart from the, and make this hydroxyapatite binding functionality free from the this chelator. So as we have used this DOTA derivative and this biphosphonate derivative, so this biphosphonate attaches to the hydroxyapatite, and this chelates the radioisotope. So these bifunctional chelator is more efficient in binding to hydroxyapatite on the bone surface, and it has been clinically applied to more than 25 patients. And this is a representative example of a 65-year male who have just started to get metastasis. And you can see that very small metastatic lesions can be detected by using this bifunctional chelator, and which was not possible using EDTMP. And also another thing is that EDTMP is chelated with technetium-99M, which gives you the SPECT imaging, and there was no chelator available which can be used for PET imaging. So using this DOTA as the chelator, we can use gallium-68, and this bifunctional chelator can be used for PET imaging. This increases the resolution of this imaging, and we can get a better view of the lesions and can detect very small metastatic lesions. So another thing, as I have already mentioned, that demand-driven synthesis of solvents for back-end fuel cycle. And as already discussed yesterday, that back-end fuel cycle is about managing the waste appearing from the reactors. So we have synthesized and tested different kinds of solvents with collaboration with radiochemistry division, and we have come up with many solvents starting from a butane-derived ionic liquid to some phenanthrolene ligands and also some resins. and very recently we have also done this synthesize this deep solvent from alkyl triphenyl phosphonium bromide and decanoic acid. And this beauty of this DES is that you can change this hydrophobicity or hydrophilicity of this DES by changing the alkyl chain length. Another interesting story is that this 18 crown 6 derivative, this dicyclohexyl 18 crown 6 derivative is known for strontium extraction, and this is being used regularly in DA. So we thought that why not to make it a larger scale synthesis. So we have always used in a lab scale, synthesized in a lab scale, and have given for testing. But what about the large scale synthesis? So this synthesis is as a very standard synthesis of this crown derivatives. You take these catechol derivatives and the dichloro moiety. So it is condensed to give this 18 crown 6 with these impurities. So these are only the where this one of the chloride is attached to this catechol or this non-fused things. So with collaboration with chemical engineering division, we have optimized the separation. We have synthesized this in 5 kilogram scale and has optimized different conditions using a series of columns with varied diameter, like half-inch column, 2-inch column, 4-inch column, and 5-inch column. And we could optimize that what are the different time where these impurities come and what is the different time and percentage of eluate, which will give you this this dibenzo derivative with more than 95% of purity. So this has been done up to 6-inch column with a series of 6 columns which can separate out more than 5 kilogram of this. So this process has been optimized, and this dibenzo crown has been reduced at high pressure and high temperature to give you this dicyclohexyl derivative, which this dicyclohexyl derivative is actually used for strontium extraction, and strontium is very important for producing different radiopharmaceuticals like yttrium based and all. So these are all from demand driven things. Now I'll talk about this curiosity driven like research activities that is done in bioorganic division. So we are actively engaged in organic fluorophores based functional materials, and we have devised different kind of organic fluorophores like BODP, that is a very well-known molecule, and since this has a very large extinction coefficient, very high fluorescence, and most importantly, it can be derivatized to get fluorescence of different wavelengths, like you can get up to NIR. This is a new molecule which is ICZ derived BF2 molecule. This is basically a helicene molecule, and this is dipyrrolopyrrole kind of fluorophore. And also we are using we have ventured into carbon nanodots as a organic organic materials, organic fluorescence material. So we have used most of the things for chemical or biological sensor, laser dyes, photodynamic therapy, and organic electronics and photovoltaics. So I will just go into some of the examples. This is the first example of a BODP dye, where this BODP, as you can see, if you go to this one, this BODP is a hydrophobic molecule. So if you conjugate it with glucose kind of molecules, so this forms an amphiphilic BODP dye with hydrophilic moieties. So in solution, this BODP forms aggregates, and this causes quenching of the fluorescence. So when a protein comes into the solution, it takes up these BODP molecules one by one. That is, it makes it desegregated, and so the fluorescence is back. So by this way, you can make a very good sensor for proteins. here we have used it for bovine serum albumin, and we have seen that this gives a very good NIR turn on fluorescence in presence of this bovine serum albumin. So using this method, we have also quantified human serum albumin in urine samples, which is very important to quantify in terms of in order to detect the kidney disease and heart failures. Another example is a ODP phenanthrolene moiety, where these two ODP dyes are conjugated to a single phenanthrolene part, and which was shown to be very, very specific for copper 2I. But again, this gives a turn off sensing, because when the copper is related to this moiety, so it is a kind of ligand to metal charge transfer, and it gets quenched. The fluorescence gets quenched, and as you can see, we have used these for detection of copper ions in living biological samples, like in cells, where if you put a dye, this green colored is for the ODP, where there is no copper. When the cells are treated with copper, so that this dye takes up this copper and get the fluorescence get quenched. And when again EDTA is put into this, so EDTA takes out copper from the dye and the fluorescence is back. So it is a kind of on-off-on mechanism, but again, we can use this turn-off sensor for sensing copper in biological samples. Oh, sorry. So this is another kind of indolocarbazole BF2 dyes, where these are the new examples, and we are the first to report similar kind of molecules. And these, as you can see, these are helicine molecules, and these helicine molecules, when attached to a ODP, it is twisted, and it gives a high intersystem crossing. And because of this high intersystem crossing, it can be used as a photosensitizer, and it can be used for photodynamic therapy. And we have used it for the killing of U2S cells through this PDT. So as shown, this we have also used these carbon nanodots, which were functionalized with rhodium 6G hydrazide to make it a dual pH and temperature sensor, because in presence of acid, the hydrazide rings opens up and gives a higher fluorescence. So this pH can be sensed, and in presence and when temperature is increased, increases its molecular flexibility and enhances the non-radiative decay. So this fluorescence is decreased. So it is a turn-on sensor for pH and turn-off sensor for temperature. So this is the first example of a dual sensor for detection of pH and temperature, both using a single molecule. So in green chemistry part, we are using different things like solvents, hydrophobic and hydrophilic RTILs is room temperature ionic liquid. And as you know, room temperature ionic liquid is something which is ionic, but it is liquid at room temperature. So we have also devised some solvent-free protocols for organic synthesis. We have used renewable feedstocks like amino acid sugars, and of course, catalysis is one of the major part in green chemistry. So starting from this non-aqueous solvents in synthesis, so we have utilized different room temperature ionic liquids. One of the example is this hydrophilic room temperature ionic liquid, which is a imidazolium ionic liquid. This imidazolium ring with bromide ion, so it becomes a hydrophilic one. And then it has been used as a solvent in Barbier type reaction. So in Barbier type reaction, you react an aldehyde or carbonyl compound with a allyl bromide or a gamma substituted allyl bromide, which gives you the product homoallylic alcohol. But in a single reaction, you get two different stereo centers. So this is very important reaction in terms of organic synthesis. So this was the first example where we could get where we could do it using a catalytic amount of metal. And this is the catalytic cycle. I will not go into deep. So another thing is that this product, as you can see, this is termed as a gamma adduct. So apart from this, a regioisomeric product like this alpha adduct can also be formed using a Bronsted acidic room temperature ionic. I'll take 2 minutes. And I'll just So this is another catalytic thing, green chemistry, where we have utilized this 1,3-dipolar cycloaddition of N-benzylidene immunoglycinate derived azomethanolite to beta-silyl methylene malonates catalyzed by a silver phos complex. And we have derived this selectivity, and this exoselectivity was originating from this transition state. And using this thermoflaming oxidation of the silyl, we could get a 3-hydroxyproline derivatives, which are prevalent in many natural molecules. Another thing I want to emphasize is that we have also used this eosin Y copper acetate catalyzed aerobic oxidative coupling reaction of glycine esters in the dark. So eosin Y is generally used in the using that LED things and at a excited state. But this was the first example where you could use this eosin Y at the ground state, and this redox reaction with this copper gives this glycine ester, which is getting coupled with this 1,3-diketone via oxidation followed by decarboxylation. Biocatalysis also, as you know, that biocatalysis is via enzymes. We have used different lipases for kinetic resolution of different hydroxy centers, and we have used this for synthesis of different bioactive molecules, including very highly strained microcycles and natural products. I'll skip this one. This detection and mitigation of iron overload is another thing which you wanted to discuss, but if time is not permitting, I will skip this one. This is another body dye which have been used for detection of iron in cellular systems, and mitigation of iron overload in cellular system and also been done using these desperoxamine derivatives. So apart from this, we have some spin-off technologies where we can use this body dyes, and where we have commercialized the technology of this body dyes for synthesis and for alcohol detection of alcohol in different alcoholic things. And another thing is that we have also done this technology transfer for OTBN, which is a highly imported material, and this is being used for certain group of synthesis of certain group of molecules, and it has been transferred to more for private entrepreneurs, and more are. So we have, as faculties, we have 4 chemistry faculties in BOD, and myself, Dr. Mula, who is doing this body works, Dr. Chaudhuri, who is this catalysis works, and Dr. Rajesh, who is a pioneer in making this PSMA compounds. So thanks.
Thank you, Dr. Dibakar. You have done excellent work and you have given an overview. Sorry for the short time given to you. I think you have conveyed that you are doing very important work for the department. Also, you are doing very good quality basic research. This lecture is now open for some few questions, maybe 2 or so. Yeah. Yes, please.
Yeah, I'm Purohit from NISA. This pinanthrulin dye, or copper detection. Is it copper 1 or copper 2?
Copper 2.
That's so strange actually, because the geometry of copper 2 is not tetrahedral, which might that pinanthrulin binds.
No, that is that pinanthrulin is flanked by these 2 carbonyl groups, no? So it is very specific, being very specific for copper.
Thank you.
Yeah, Dr. Divakar, nice talk. Myself, Maulik. So, actually, your de-aggregation from body protein, stop the aggregation in this protein, and then you get it. What about myself? Myself is well known for this type. Suppose you take myself.
This is forming actually myself. This amphiphilic body
is that without protein, you just take myself and expect to I'm feeling that without proteins,
yeah, maybe, but these proteins are they are actually binding to this individual group. So these body things are there. If you put some surfactants, so
in that case, can you then say that it's the same cell protein? They are giving as a surfactant,
but they are not giving you fluorescence. This is NIR.
be done.
Yeah, another question is just quick, this IL-based catalysis, what about using this for?
Yeah, that is one thing we are trying to do now, because we have just now for last 2 years we have ventured into this. And we are mainly focused in extraction part. Using this DS for
I
extraction.
think we'll have one last question.
Divakar, very nice talk, and thank you for bringing that importance of radiopharmaceuticals. So I have no question, but few comments. So first of the thing is that yes, it's a very good work that we are able to synthesize PFM, which is extremely difficult. And the joint effort taken by Bioorganic Division, Radiopharmaceuticals Division, and BRIDGE has really brought down the cost, which was per patient around 3 lakh rupees to now only 50 to 60,000 rupees. Another thing, what I want to bring it to your notice is that EDTMP, technetium level EDTMP, is never used for diagnosis. It's this analog, that is methylene diphosphate, 99 MTP. And I don't think we can have a better agent than this, because it costs only few hundred rupees to scan the patient. And as far as the PET is concerned, it is, I feel there is a product which is very established, that is sodium chloride. 18F11 sodium chloride, which is regularly used for scanning the patient.
But the problem, I think you can discuss, because you are collaborators. There is no point, you can discuss subsequently.
Sure.
I have one last, Dr. Divakar. So you have shown many cases that 100 times you have brought down the cost, whatever is imported and what you have synthesized here. So are there any patent violations, because these compounds must be protected by patents?
This synthetic route setting.
You have got separate. So how you have patented this method, whatever you have, if it is different, you can always patent it. So they are so important compound. In this, that crown is that cyclohexyl, dicyclohexyl 18 crown 6. That you have said you have synthesized 5 kg scale. So how this cost of this compares with what you are getting from imported route? Because this is a very well-known chemical, so if you are doing it so much efforts, so that cost, how much it is?
We have no exact data for cost, but it's
No, 100,
comparable.
100, I'll tell you the cost. 100 gram cost around 3 to 4 lakhs.
It should be much less than that. Definitely the cost.
So thank you very much. Thanks, Dr. Divakar. Now, next speaker is Dr. Kathi Sudarshan. He's from Radiochemistry Division, BARC. He joined Radiochemistry Division 1999. Currently, he is heading the section on the positron annihilation spectroscopy and characterization of materials. I invite Dr. Kathi Sudarshan for his lecture.
For giving me this opportunity to present our work from Radiochemistry Division. And it's not exactly my own work, but it's the work in the division on nuclear chemistry and nuclear probes, basically involving measurement of nuclear radiation directly or indirectly. So I will be dividing my talk into practically 2 parts. And to start with, let me apologize. I may have to rush through few slides because I have to compensate the time lost. So coming to the topic that I will be covering, the first part is on research activities in nuclear chemistry, where nuclear reaction mechanism is studied, and also some radiochemical separations which would aid the nuclear reaction studies and nuclear spectroscopic studies, and non-destructive studies for nuclear forensics. And the next part is material science with antimatter. And when I say antimatter, I am referring to positrons, which is antiparticle of electron, where we use that as a probe in understanding the material properties in geolytic material frameworks, polymers and catalysts and nuclear materials, etc. So I will try to give at least one example to each kind so that it would give you an overall view of the work that is being carried out in radiochemistry division. And the details probably have to be discussed later. So when you come to nuclear reactions, we do the nuclear reactions using the heavy ion beams from the different accelerators available in India and also the neutrons, which induce nuclear reactions and fission in different systems. So these are the major facilities that we use. And how do you measure the fission? So one of the ways of measuring the fission fragments is using multi-wide proportional counters, which two are there in which exactly match the angular distribution of the fission fragments that they come, and that can be used to measure the fission fragments, and especially the time of flight between the two detectors would give you the kinetic energy and hence the mass. This is the basic idea of measurement. And similarly, for the projectile-like fragments and the reaction fragments, we use, which we call it as telescope detectors or delta E detectors, which gives you different charge particles, give you a different banana type curves. So identify the radiations. These are the physical methods that we use. And what for we study is to understand the single particle effects or so-called shell closure effects in the nuclear reactions and fission. And let me say that when I'm talking about shell closure effects, the primary shell closure that we are studying in the textbook are based on the spherical nuclei. And what I'm talking about is slightly a next version of it, where you can nuclei could be slightly deformed to change the shell closure levels. So it is like more like studying the secondary effects. So in the fission mass distribution, see in this region, we expect it to give a symmetric mass distribution because you don't expect any so-called shell closure. But in this mass region, you do see a symmetrical mass distribution, which is measured using the system that I was referring in the previous slide. And you would see that for different compound nucleus mass, the heavy fragment masses are almost static at 56 neutrons, indicating that this is a deformed shell closure, which needs to be accounted for in the different nuclear models that predict the reaction cross sections and the fission fragment mass and angular distributions in various cases. So this is more like nuclear physics phenomena, but which also needs to be studied, especially to understand the besides the mass distribution, what are the different charge distribution, because the charge distribution decides our chemical properties besides the mass distribution. Similarly, in the nuclear structure effects in the nuclear reaction, I have just taken one example of carbon plus niobium reaction, where the product zirconium 90 being a spherical 50 neutron shell closure nuclei gives the nitrogen 15 yield in this bombardment much higher than the expected, because with the increase in the mass, you expect the transfer probability to reduce conventionally. And this additional nitrogen 15 when compared to nitrogen 14 indicates that there is a correlated transfer of two neutrons and a proton to the carbon from niobium, so that this shell closure is reflected in the energetics. Besides this nuclear reaction mechanisms, quite often we require different methods of chemical separation to understand the nuclear spectroscopy, because, for example, in most of the nuclear reactions, the number of products are too huge, including the fission, especially if you go to higher mass region. So when you are trying to understand the nuclear spectroscopy of one of those nuclei, the first important step is to remove the background as far as possible. So this is simple an example of where ammunition 244M is produced and a fast radiochemical separation, which is done to carry out this decay spectroscopy or they construct the different energy levels in americium 240. So it is nuclear reactions and spectroscopy both together are carried out. And similarly, this is, and quite often it is not possible always to establish your chemistry with the actual short-lived radioisotopes, which are both small in number and you are limited by time. So quite often we do with the homologs of the actual material, which we are interested in the long run. So for example, berkelium was the one which we were interested in trying to pre-concentrate and study its spectroscopy. But since berkelium is short-lived and establishing the overall chemistry process is difficult, so we try to synthesize cerium imprinted gel using BMEP and acrylic acid polymerase. And this was found to be relatively selective with respect to other fission products, and this we could use for pre-concentrating berkelium from host of fission products and study its spectroscopy. But do remember that when I'm talking about this selection, quite often we are more interested in faster separation rather than quantitative 100% separation without any impurity at all. So I would put the other way around. Probably I would be more happy with 50% separation if I can do this chemistry in 10 minutes rather than waiting for two hours and separate 100% without any impurity. Timing is more important for me in studying this rather than the quantitative separation. So most often you would see that these systems are simpler and well established, but we are trying to get to a quicker route of separation, that's it, to aid in the radiochemical studies and the nuclear structure studies. Similarly, is another example of where ammonium molybdenum phosphate based gel was prepared, where cesium-140 could, this initial kinetics was studied with long-lived isotopes of cesium-137, but actual was used for studying the spectroscopy of cesium-140. So wherever you have the 10-20 minutes half-life things where spectroscopy needs to be studied, we use methods which we first optimize using slightly long-lived isotopes and then go and apply for the shorter-lived isotopes. And this is another where shift ion and shift heavy ions are used to modify the polymers to create the channels for the ion transports, etc. So this was a study where PVDF was irradiated with different ions like silver and lithium, and the damage channels were grafted with various polymers to understand this, the damage, etc. And it was also used to uptake the americium and understand the americium uptake. Understand the americium uptake distribution, and we realized that the polymer irradiated with silver has a more surface damage and americium is more towards the surface, whereas the ones which use lithium takes the material inside. So depending on the purpose, your choice of ion irradiation would be different. And this is another where you need to assay the nuclear materials non-destructively, especially for the nuclear forensic purposes, where your idea is to not open the packet, but still be able to understand what are the contents of the material and what is the quantity of materials. So we use the methods like neutron multiplicity, gamma spectrometry to estimate and identify both the amounts as well as the isotopic ratios, especially with respect to uranium and plutonium. And different methods are used to understand and quantify, and the complexity of the method will always depend on the exact information that you are looking at. And quite often the simpler methods are used just to identify and to have a, if the case is suspicious in terms of forensics, so that the more detailed studies can be carried out further. So this is on the first nuclear chemistry part of it. And coming to the next part, which I told in the first slide, is the material science with antimatter, positrons. And positrons are antimatter to electrons. So when they are impinged in the matter, they annihilate with electrons. So the survival time of the positron in the matter or the lifetime gives the electron density, or since these positrons tend to localize in defects or where there is no material, so they give the lifetimes, give the quantification about defects in metals and alloys, free volumes in polymers, and pore size in porous materials. So finally, we measure the lifetime or the Doppler broadening of the annihilation gamma, because the positron is annihilating with the electron. So these are the two primary techniques that we use in material characterization, and the lifetime is related to the cavity in which the positronium, which is the lighter analog of hydrogen, that resides. So these are the basic techniques, but we have a host of techniques besides these two basic techniques which we use in our laboratory. And I can say that it's more or less a complete state-of-the-art laboratory with different positron annihilation spectroscopy techniques existing in radiochemistry. And the focus areas using these techniques are mostly dependent defects in thin films and multilayers, defecting engineering in oxides for catalysis and photoluminescence, defects and radiation-induced damage in alloys, which is more important in the department, and photon-induced positron annihilation for aging studies, polymer nanocomposites for understanding the free volumes and related physicochemical properties, and the liquids under nano confinement whose properties are expected to be different from the bulk, and porous metal organic frameworks. I am only covering few of them for the paucity of time, and I will try to finish. Yes. So let me start with the geolytic image frameworks, or GIF, which are analogs of structurally analogs of geolite. So the only problem, these are the porous crystalline materials, but the only problem is that the pore size that is measured and the gas separations that are expected are not really correlated. And the primary concern because by which this expected separation factors are not reached is attributed to flexibility of this pores by the method that you are using for measuring the pore size. So this flexibility means essentially the pore size is different at higher gas pressure where you are trying to separate the gas, and you cannot correlate that with the single crystal data. And any method that you use is bound to modify the pore pressure. So there is a way of looking at how to go about. And in case of positron, it is a non-invasive probe when compared to the other gas abstraction methods. So what we are trying to do is that since the positronium is formed in this network, and the positronium lifetime is directly related to the cavity size. So we use positronium annihilation lifetime spectroscopy to understand the cavity size. So for establishing that it works, we have synthesized various GIFs and compared the pore sizes calculated using positron annihilation lifetime spectroscopy with the single crystal data, and found that they are quite matching. And the intensities could be correlated with the pore size. But one more thing is that when you are talking of the gas separation, besides the crystallite cavity size, the what is at the crystal boundaries, etc., also is one of the important, because we are going to use these GIFs as films. So we can use the positron annihilation spectroscopy to study the overall pore architecture and the crystal grain boundaries, etc., using the positron beams, where we have the monoenergetic positrons. Also we can use to study them. So these two types of studies we carry out. And to just give you an example, so we have studied the compression induced changes in the porosity of graphite, where we found that even if with high pressure, though crystallinity is lost and amorphization is taking place, still a pore structure is still retained. And similarly, when we are talking about the crystal size dependent porosity, so we have synthesized graphite crystals of various sizes and found that the smaller the crystallite size, the pore aperture is reducing. And it has been reported in literature that the smaller nanocrystals show delayed gate opening. And gate opening is nothing but where the pore expands at higher pressure. People call it as gate opening. So this delayed gate opening already reported could be correlated with the cavity size determined for various crystals, because otherwise you have to correlate with the single crystal pore sizes, and it is not easy to get single crystals of various dimensions and do their crystallographic data. And the flexibility also can be tuned by changing the ligands. Instead of imidazole, if you use benzimidazole, we could prove that the pore size can be tuned using the different proportions. But when you are using two different proportions, the different proportion of the ligands were measured by NMR. Even the morphology was also changed. But at low concentration of benzimidazole, when the morphology was not changing, we tried to understand the keeping the morphology, how does the pore sizes, etc. change. And we found that the pore sizes, even after keeping the same morphology, are still different. And this, based on the different pore sizes that you have inherently, their flexibility is also different. We have developed a system where you can measure the positron lifetime under different gas pressures too, which actually mimics the practical applications. And we found that the ones which are having the lower pore size are the ones which are maximum flexible in this particular case of mixed ligand synthesized imidazole network. And our recent study showed that this so-called flexibility is again dependent on the what gas you are using, and in the mixed ligands, what are the mixed ligands and mixed metals that you are using. All the factors are also going to change the exact pressure at which this flexibility is or start. So when I'm talking of flexibility, when I apply gas pressure, I assume that since gas is applying the pore volume, positron annihilation lifetime is expected to reduce. And wherever the increase in lifetime is observed, it means that the flexibility of the networks has set in. And going to the next topic of polymers, see, the polymers have free volumes, and when you go to polymer composites, these free volumes depend on the filler polymer interactions and the type and shape, amount, everything. And these free volumes dictate many of the physicochemical properties. And to measure the free volumes in the polymers, positron electron spectroscopy is one of the well-established and the tool to go for, I would say. So we measured free volume distributions in various polymer filler composites in different various combinations. And I would just give one example where SiC nanofibers were used as the fillers. And one of the interesting things that we found is that whenever we use the nano wise type thing in the fillers, the free volume distribution was becoming bimodal distribution. Means when I'm saying bimodal or unimodal, I'm not saying that it is an assumption that all your free volume holes are assumed to be spherical when calculating this. It's definitely a model dependent one. But still, whenever you use the nanowires to as a dopants or fillers in the polymer network, you always tend to get bimodal networks, and the bimodal networks were found to be the ones that are dominating factors in some of the physicochemical properties that we have studied, from the Young's modulus to conductivities in the other systems, etc. So the shape size also matters. And I'm quickly switching to the next topic of materials where the defects do play a role. Since I have already started with saying that positrons are sensitive to defects, so we use positrons as a tool in understanding the defects in the materials of importance. So I've just taken the example of catalyst as one of the examples. Just to give an example, this is the defect evolution in europium and niobium dope seria, where you know that the trivalent ion doping enhances the oxygen vacancies, and you could see that the positron lifetime increases with europium doping, and if you co-dope with niobium, it reduces again. And similarly, to say that this is coming from this same oxygen vacancy, I have used the photoluminescence, which already that Raghavani Singh has explained these transitions, where the asymmetric transitions were high when you have just europium, and the co-doping with niobium reduces the asymmetry in the emission, or electric dipole transitions in the emission of europium, which means that the oxygen vacancies are removed if you charge match the ions, or essentially indirectly you can say that you can tune the level of oxygen vacancies by appropriate choice of the dopants. So similarly, we try to dope different trivalents itself and try to see what is the difference, the ionic radii of different trivalent is going to make difference on the oxygen vacancy concentration and hence the derived properties. And one of the important conclusions that we could draw is that the smaller ions tend to associate oxygen vacancies with them, whereas the larger ions do not get associated with the oxygen vacancies. And that non-association would give you more of Cerium 3+, and that makes it means Ceria doped with larger trivalent ions a better catalyst in the redox reactions. Means when we dope with the lanthanum, which is of larger ionic ranges, the same could be concluded with the XPS studies, corroborated with XPS studies. The other one, which I would, this is my last, probably I guess, this is my last example. So when you are trying to understand the defect spectroscopy in ion irradiated nuclear structural materials are bound to get radiation damage when they are used in the reactor, but it is a slow process. Since whatever the damage that can be caused over 30 years of reactor life can be simulated using the AV ion beams, which you call it as accelerated aging. Definitely, this will be a non-uniform distribution of defects when compared to the neutrons, but at the same time, if you can get the same displacements per atom, which we call it as DPA, the rest of the properties can be correlated. But when you use charge particle for creating an accelerated damage, unfortunately, the defects are only at the few not few micron layers from the surface. It's not uniformly distributed. So you require special techniques which would be able to analyze the defects that are not present in the entire matrix, but at the surface because of the ion implantation that we have carried out. So for this, we use positron beam, where the conventional positron studies which I have earlier described use the sodium-22 source, which has a beta spectrum as such, which probes up to 300 microns or so. So we use energy tunable positron beam, which has the energy from 0 to 20 keV only, where the implantation depth of the positrons is fixed by my energy, and I can study the defects at various depths after the ionization. So this is a typical example where helium irradiated nickel chromium alloy case is being shown, and this whatever the Doppler broadening annihilation parameter, which we call the fractional area in the central region of the Doppler broadening spectra, is fitted to different layers, and we could find that the initial layers where the implantation has taken place, the helium is always associated with the defects. So it is helium bubbles are formed in this case, and similarly different types of vacancies that are present at different depths could be correlated, and this is the one of the technique which non-destructively you can do. Before this, most of the studies and the radiation damage studies in BRC, first we do this and then go for the other TEM studies, because this after this the sample is still intact, whereas the other methods they need to etch out the layers to understand how the defects have evolved in that depth. So this is the first primary technique we go before going to the other. And these are the examples that I have, and let me acknowledge this is the contribution of 2 sections in BRC, so I have not taken everybody's name. And when I say 2 sections, it is only faculty, not the students as such. So slide courtesy is by Rahul, Chavi, and Sabyasachi for the reactions, and something. And thank you very much for your attention.
Thank you, Dr. Katish Wilson, for finishing in time. So there is time for 2 questions from the audience.
I'm pretty nice. Time ago, spectroscopy. Now, how we are determining the cavity size from the time ago?
Actually, the first from the lifetime spectra, first simply we fit it to multi-exponentials, where we get the lifetimes. Yeah, this is the slide. So this first thing what we get is the lifetimes, and the longest lived one is usually from the orthopositive. And orthopositive has an intrinsic lifetime of 142 nanoseconds, and depending on the cavity in which it is reduced from 142 nanoseconds. So what is the reduction from 142 nanoseconds is given by this equation. So that equation is based on a model, definitely, where you consider the cavity to be spherical. For the other shapes also, the equations are available, but whatever the studies that I have explained here are considering the cavity to be spherical, and using that equation, you can calculate the annihilation rate due to collisions. So that collision frequency will be high if it is a smaller cavity. So that lambda, which is the inverse of the lifetime that I am determining, is going to give the radius. So this is the equation, basic equation that I use.
What is the error bar because of assumption of a spherical cavity? And,
see, if you are in the lifetimes are in the range of less than 40 nanoseconds, the error bars are not quite huge. But the moment you go to it, say 10 nanometer cavity, angstroms to 10 nanometer cavity, the error bars are high, because the lifetime is supposed to saturate to 142 nanoseconds. So the slope is initially very sharp. So the accuracy of the determination of lifetime is quite good when you are in the, say, up to 60 nanoseconds lifetime. But the moment you go to 100 nanoseconds lifetime, the uncertainty a 1 nanosecond cause on the radius is huge there. But by the time you go to more than up to 10, 15 nanometer,
So when you are in this range, it is quite. Thank you.
If there are no more questions, we thank Dr. Kathi Sudarshan. On behalf of the organizers, it's my pleasure to present a small memento to Dr. Sudarshan. The next lecture is by Dr. Prasenjit Mal. He is an associate professor at Niger. He did his MSc from IIT Kharagpur 1999, PhD IIT Kanpur 2005, and he joined Niger in I think 2009. I request Professor Mal to give it.
Sorry. Okay. So, thank you, Dr. Mahapatra, for introducing me. And I'm just going to talk about a topic that is supramolecular catalysis in organic synthesis. Probably this term is not familiar with many of the persons here. Basically, what I'm going to talk about that it is, although it's not a well-defined term. So supramolecular catalysis means in one of the aspects that we will talk about that many reactions can be controlled by the utilization of weak agents. Although probably you have attended the talk of Professor Dr. Mathiguttar, so he has nicely demonstrated the post-phase chemistry, but here I'm just trying to understand some of the kind of physical organic chemistry aspects of how to synthesize molecules by utilization of weak agents. Okay. So what is basically supramolecular approach? So if you have these are two playing cards. If you place them on a table, it does not mean anything. But if you just align them in a particular way, so what you can say that you can get a kind of structure. This structure can be replaced by another building block. You can get a new structure. So this is how we build the supramolecule, and that is, you must say that human body is one of the most complex supramolecule existing in this universe. Probably. Okay, so we utilize various weak interactions. Okay, I'll not go in details, but only thing in this talk, I'm going to talk about few of the aspects of carbon, nitrogen, or carbon sulfur bond formation reactions, and mainly organic term I've used that is without using a metal, and one of the reagents you will be using that hypervalent iodine reagent. So these are few examples of the hypervalent iodine reagents. Now, it's a textbook chemistry that reactivity of amines and iodine. Amines are nice base, and iodine, hypervalent iodine, that okay, oxidation numbers are high. So in that cases, it is acidic in nature, and in that cases, iodine and amine it produces some exothermic reactions, and we call them as a kind of a touch foam, which is popularly school children during exhibitions we do it. Now, in this case, we are using some kind of primary amine and iodine feed. So it shows that it's a generation of very high heat, and as a result, everything gets decomposed. So it just to understand that to control the reactivity, so what you have used the explosion controller means just trying to understand the basicity of the amine, and this is the salt, sodium bisulfate. So this is nothing but acid salt because it can control. So we have the data, but I'm going in details. So as all the reactions are solid state, and ball milling chemistry basically that to do the reaction the solid state maximum contact and stress for a contact explosion. So then what you can find out that very nicely that explosion three cross reagent to coupling reactions can be performed, and we could able to synthesize some of the kind of amine. Now, our purpose, controlling the basicity of the amine in presence of acid. So again, this is a kind of another reagent, which is IBX, which also causes explosion, but this is a benzamide where you can see
the nitrogen lone pair is no longer available for this. So just introducing both these things that two amino benzamide and the IBX, we can synthesize some of the nice heterocyclic stuff. Now, this exothermic, this is the reagent we have used, that is iodobenzene and MCPVA. So this produces some sort of your iodine free region like PIDA. So in situ, again it is an explosive, but what we have shown here that this particular molecule have an acidic hydrogens which can intramolecularly control the basicity of the amine, and as a result the benzimidazole derivative could be synthesized. So this one again the mimicking, okay, not only hypervalent iodine are generated in situ, so another component like TBA, TBHP also can is the similar way the benzimidazole compound could be synthesized. Now if we just look at that any nitrogen or coupling in presence of iodine C region, it is important that we should understand the basicity of the amine. So how we can control that intramolecularly that introduces the carbonyl group, which can have a pi star antibonding orbital, so into pi star interactions or some of the solvent effect. So it is possible that amine iodine reactions can be controlled. So what it does that in presence of highly acidic nature, that is iodine C reagent and amine, it can produces a nitriniamide. This is a very short-lived intermediate, or you may say this is a kind of coordinated substrate like this, or this is an equivalent. And in this case, so this positive charge can go to the basically aromatic ring also, which okay by losing the aromatic ring current, but it's called a nitriniamide, and this is called the arbinium. So we try to understand that this nitrinium is generated. How can we utilize the nitrinium? Since the time is short, I'm not going in details about the nitrinium. Okay, but only thing what we can say that this particular using a strategy, I'll come to the mechanism in the next slide, but simple approach can be taken that amine in presence of iodine C reagent and another aromatic ring like toluene, benzene or whatever. So in that case, two of the aromatic ring could be fused together in just simple room temperature at 1 hour time in a solvents like chlorinated solvent. Mechanistically, if you try to understand that first step is the formation of a nitriniamide. This nitriniamide, depending upon the stability or depending upon the nature of the nucleophile present in the medium, so it can undergo first CC coupling and followed by again the same procedure that nitriniamide generation and followed by CN coupling. So that means one of the easiest way that one can synthesize the carbazole derivative by this approach. So the same approach we have extended to that when we do not have such easy phenyl ring. So in that cases we have shown that if the reactions are done in place of acetyl group, so in that cases there is a kind of migrations of the methyl group would be observed. So mechanism is same. Again the generation of nitrinium followed by first plus C coupling and followed by formation of an nitrinium intermediate, and then which leads to a kind of stabilization of the carbocation, which leads to the migrations of this alkyl group, and this migration of the alkyl group, and which can lead to the formation of the bond. So there are many other ways we have shown that if there is this particular tertiary butyl carbocation generated, which is a very stable carbocation generated, in that cases the removal of the group can lead to a formation of the carbazole. Even there are cases where we have shown that when the group is not that efficient for to generate the stable carbocation, in that cases we have also shown that this is the alkyl group migrations. That means we could do a simple approach to do a distal CH concentration reaction. So these are some of the approach. Not only we have seen that when the nitrinium is not stable, so there also it is possibility that the generation of the nitrinium can be done, which is looks like an anti-aromatic and endocyclic nitrinium. So these are generally unstable. Okay, which can finally lead to the cyclization of this particular molecule. So overall, if we just look at the reactivity, that means the nitrinium or carbonium. So we try to understand in terms of hard soft acid base principle that hard prefers hard or soft prefers soft. So in that case, what we see that if there is a kind of soft nucleophile, okay, and there is a hard nucleophile, so what is the difference of soft? This is the kind of biphenyl. So the electron density is distributed, but because of this methyl group for the bimecyl, that there is no communication between these two. So therefore, no electron denucleation. So therefore, it is a hard nucleophile, and this is a soft nucleophile.
So when soft electrophile is there and soft electrophile, so we see an observation of CN bond formation, and in other cases it's lead to CC bond formation reaction. Now why it is a soft and why it is hard? Because you know that because it is more reactive the reason that it is losing the aromatic ring. Otherwise, generally, okay, in the cases, so this is a better soft electrophile. Not only we have shown that in situ by choosing an appropriate solvent, that this is a regiodiversion synthesis by understanding the relative the dipole moment of the tautomer. What is that? That means that there are two tautomers can be exist in equilibrium, and these tautomeric equilibrium can be switched by choosing an appropriate solvent having a different dielectric constant. So this is the type rho acetic acid and hexafluoroisopropanol. So that starting from a one single molecule, it is possible to synthesize two different molecules. And okay, so now overall, so CN bond formation reactors. So using the hyperbaric reagent, just now I have discussed the various approaches that how the nitrogen lone pair can be stabilized, and therefore not only there are various formations of the carbozoles or any other intermolecular reactions could be part. So since we are talking about weak interactions, and I'm going to talk about some of the aspects of your carbon sulfur bond formation reactions. So this is a well-known interaction, that is the cation pi. So sulfur also forms some kind of similar kind of weak interactions, and that is SH pi. Of course, this is the pioneer of the work when Dr. Himanshu Vishal was doing PhD and also Watnagar. Okay, I'm sorry to I'm not going to pronounce properly, but so they have done the work. I forgot to mention give this reference. So now we try to understand the simple reactivity between these two molecules, that is called thiol in click. That means just simple double bond. This SH bond can be added to this double bond. There are two different fashions. One could be the Markovnikov and another could be anti-Markovnikov. By understanding that what is the driving force, we could establish that different pi-pi stacking or SH pi interactions, and which lead to normal conditions and anti-Markovnikov synthesis of this particular molecule, and then these are called the room temperature. Already you feel that what is the room temperature in which peak of winter. So this is our laboratory room temperature. Okay. So in other cases, if you use some kind of silver metal, which basically can disturb this particular orientation, and it is possible to switch from anti-Markovnikov to Markovnikov. Okay. So that also we have extended the similar condition, and we have tried to understand another point of view that out of these two combinations, by changing the conditions of the reactions in the same within this particular system, that there are different reactions or different compounds can be produced. Okay, so now we have tried to understand. Okay, recently we have kind of written the what is the mechanism that in the room temperature heat conditions this sulfur center is amphiteric in nature, so it can be used as a electron donor or electron acceptor. Okay, if this olefin is an electron deficient, so we can see that it can lead to Markovnikov, and if the olefin is a donor system, so it can lead to an anti-Markovnikov reaction. So therefore, in presence of metal ion, we see anti-Markovnikov, and in absence of anything, so this is the normal addition is to anti-Markovnikov reaction. Not only that, so this thiol in or ion basically can do the reactivity with different system by choosing an appropriate reagent. So in this case, what we have shown that amide hydrogen bond can be used for this alkyne activation, because if there is a this particular system which is a red ring, so then that amide oxygen could be protonated. But that's not happening if there is a kind of alkyne group here, so which is an electron donating. So therefore, this NH bond is available for the hydrogen bond. So we utilize this particular concept that by okay, mechanism is there in this slide. So this hydrogen bonding causing the addition to anti-Markovnikov, but when you put another amine group which is a better hydrogen bond donor, so in a better hydrogen bond acceptor, so in that cases the reactivity is switched, and it can be selectively that Z selective Markovnikov product can be synthesized. Another way we try to understand that was the internal alkyne. So if you look at the terminal alkyne, also the similar way that amide, this particular one, that during the development of the reactions, so we have found out that another quick interaction, that is it's the literature report. So it is well established that sulfur oxygen can form an interaction which can lead to a formation of different stereoselective product. That means jet selective antimarconic selective product can be obtained by understanding that the intramolecularly that some quick interactions are playing a significant role here. Not only that, after these two systems also, we have recently also developed that in a terminal alkyne and this benzene marker in terms of base, it is possible that control that 100% jet selective antimarconic compound can be synthesized. Okay, so what is that? That is basically nothing but a stereostatic synthesis in these cases. So we try to understand that what are the stereoelectronic factors, that stereoelectronic effects can play an important role. That is the solvent, also hydrogen can form an hydrogen bonding, anion solvent hydrogen bonding, that anti-pyridinal addition, and also the N sigma stabilization can lead to an 100% jet selective product. Of course, so overall, the carbon sulfur bond formation reactions we have shown there are many reactions and a couple of reviews we have written here recently that that during this is a COVID review. During COVID time, we do not have much work to do, so better to write some review. Okay, these are some of the examples, and overall you can see that we can quick interactions like carbon sulfur oxygen, different way that click chemistry, and of course I am not talked about this work, but there are many ways that we can do kind of carbon sulfur bond formation reactions, and these are the reactions we have shown that intramolecular hydrogen bonding, intermolecular hydrogen bonding can also control the stereoselective synthesis. Okay. Now, also, okay, I'm not going to discuss in detail, but only briefly I can say that other weakest interactions like halogen bonding interactions can be used to control different reactions. Okay, so in this case, what we could show that this particular molecule can show the interactions with this, that halogen bonding. So therefore, this carbonyl, this particular alpha beta unsaturated ketone system can be activated. So there will be a Michael type of addition, which can lead to a cycloacidic. Now coming to the last topic, we also recently started working on this visible light photocatalysis. So we can common is the light sources we are using, that is household lamp or fluorescent lamp or LED bulbs, different LED bulbs for doing this reaction. And this is the absorption spectra of this. In these cases, the commonly used photocatalysis are these are metal free and these are many complexes. And what is the requirement that the strong visible regions, long excitation lifetime, and stable under photolytic conditions. So this is the review we wrote. Another COVID review. So just summarizing some of the hyperblend iodine-based photocatalysts. But what our major interest here recently, we have been using this particular photocatalyst, which is nothing but a commercially available reagent. So that's always easy to use commercially available reagent. So with this, we could show that that making this oxygenation reaction to synthesize that fluoride to the ions or some cyclization reactions also could be possible, that using generation of the nitrogen chlorine bond photolytically breaking, and that chlorine radical can add and generation of fumarine type of derivative. And we could also show that thioacetylation or thioetherification reaction, and also we have shown recently that these particular reactions can be done without this is the UV, but in presence of the same photocatalyst, that this kind of reaction can be done, that will be cyclized. And also we have shown recently that this same catalyst can be used for activation of this terminal alkyne, and for the synthesis of same diethyl. With this, so recently we have just moved our interest to that using a perovskite as a photocatalyst. So this is the perovskite. Of course, I will not go in detail. The expert Dr. Subhadip Bose is here, and his talk is tomorrow morning. So probably he will be the better person to do it. So at least we can say that these are kind of materials, so maybe X3 type. Okay, so which also have kind of color tunable property and have many applications. Okay, so in this case, our focus is to understand the photocatalysis. If we just try to understand that earlier the ruthenium, these bipyridine complexes are used, and I have also shown another one. But basic understanding that depending upon this particular catalyst, like any other catalyst,
could be, and also depending upon the oxidation reduction potential of the substrate, so the electron transfer can be possible. So the electron can be donated to the substrate or the electron can be withdrawn or taken from the substrate, and therefore what can happen? So we start to follow up the reactivity. So what we expect? So this particular one, Dr. Subhadeep was prepared, and I was just kind of what to say, soappies here because I helped him to uh, give him this particular molecule from my lab, and he has put my name. Thanks to him. And okay, then journey begins that we try to understand that what's going on here. Okay. Then, okay, with the help of Subhadeep again, that we have synthesized that another perovskite molecule which is orthorhombic, and this orthorhombic molecule can, which is a very nice excited cell lifetime, which is stable under photochemical condition, and also the redox potential which are compatible, what can be used for organic transformation. So therefore, this is the these were published by Professor Onunai Samanta from Central University of Hyderabad. This is Subhadeep, and this is the last score that this work in this particular work that we have synthesized this orthorhombic perovskite, and this is the this is a very nice this cell with edge length, and also this is the photoexcited pattern, this is the process, and this is the UV that basically electrochemical pattern. So the purpose of this, after making this molecule, we did not confine our attention to making the molecule, making these materials, but this material was a very fantastic visible light photocatalysis, which could be utilized under sunlight or blue LED, which is available in our lab, and that is also synthesizing same dihaloquinones. To understand the mechanism, what we do, that we start doing the process quenching experiments to understand that there is an interactions, Then also we try to understand the importance of the visible light, that if you do the dark condition, the reaction do not proceed. And also this is kind of spectrum, not spectrum, that photograph that before and after exposing the sunlight, what are the before states and after reaction. And also this is something we understand that the electron transfer process, of course, we are not expert in EPR, but say we can utilize this concept that this is the DMPO. When there is a kind of radical, it's generated that radical, is trapped to this molecule, and you can see a very nice and clean EPR spectrum, which is a stable persistent radical. And ultimately, that we also established from this experiment as well that tempo BSP or 2,1 diphenylethylene, so which can also show that establish the radical concept. Finally, this is the mechanistically, of course, from all the material, but organic part, you can see that what by oxidation reduction potential, and we have established that this is the kind of mechanism that electron transfer fast to this substrate, and there is a generation of this radical that one adding to this molecule, and followed by the water present, the solvent or deliberately added to do that same dihaloquinones, and we have established that also then in absence of in the dry DC the reaction do not proceed, okay, and also in presence of oxygen that also kills the photocatalysis. Okay, so overall, what the important part that this one, okay, in that mainly we have tried to understand that why this particular molecule is working. Okay, it's an efficient photocatalyst. In other cases, the or the cubic perovskite which are synthesized earlier, these are not that efficient, but which is the orthorhombic one efficient. And now we're writing a couple of manuscripts that trying to understand that what exactly the factors controlling and able to come up with these ideas that how good they are in giving these perovskites and what are the photophysical properties. So overall, I think time is up. So overall, what I have shown here, that strategies to control the carbon-nitrogen bond formation reactions, which can lead to various carbon-carbon, carbon-nitrogen, or carbon-oxygen by understanding the exothermicity of this particular reaction coming to nitrogen. And also, we have talked about some of the carbon-sulfur bond formation reactions that, which will, okay, and also at the last part of my talk, we have discussed the visible light photocatalysis and importantly that cesium lead bromide perovskite, which also can be used and excite the very nice photocatalysis. So these are the kind of group members I always thank. So the perovskite was work developed by Dr. Anupam Mandra, and now this whole blue part is utilizing the perovskites to develop some photocatalysis. And these are about 10 PhD students have completed. Okay, and these are 13 MSc students. Okay, I have with all of them the work has been developed and some of the collaborators and of course Sodhi goes for this. Dr. Arinambos have helped to establish some of the NOR characteristics. Dr. Chandan Goswami will do the biological studies. Courses, some of the IIT courses would have the theory. NIT Meghalaya, Amit Pal would have the theory. And we will help some kind of conductivity studies, some materials, not in these studies with PKI and also PKI. So he was my collaborator since my postdoc days. And also he helped to develop some of the architecture, but which I have talked here. And finally, thank you all for your nice attention. Okay.
Thank you, Professor Mal, for your completing in time and also giving a very broad overview of your work you are carrying out in the research group. There is time for 2 questions from the audience.
Yeah.
Very nice talk. I have one question regarding your photocatalysis part.
Yeah.
See, for photocatalysis, anyway, TiO2 doped, TiO2 is anyway a very well-known photocatalyst in the visible region.
Yeah.
Doped one, not the original TiO2. So, I mean, how is your
But TiO2, because I have not, we have never used it, but that is can be used for the carbon dioxide reductions and that's one example. But perovskites, we try to understand mainly that there are a couple of factors that this is important that the oxidation reduction potential should be close to that compound where you can do an electron transfer or electron take. That is, and perovskites are highly, it's like a sodium chloride, it's a very highly ionic. So that stability of the perovskites in different solvents is one of the important factors we have to think about. So like TiO2 based metal complexes or something like that, if you use, you can use it in any solvent. But you have to very get particular careful choosing a solvent because any oxygenated solvent like methane and cannot do the reaction. You have to choose some non-polar organic solvents. So that is how the difference is, and that much TiO2 maybe not soluble. So if you do heterogeneous catalysis TiO2 maybe
I think the technicals what you are using and get
Yeah. So that is already we have established. This is also this before doing this. So this particular molecule has given us an idea that how to develop the photocatalyst. So this is a commercially available reagent. It's very cheap also. Just we use it and finally saw that there are a few works okay still we have developed some work and that giving you the idea that what sort of molecule like materials and
Any other question? If there are no other questions, we thank Professor Mal for excellent presentation. On behalf of the organizers, it will be my pleasure to give this small moment.
So on behalf of the organizer, the another organizer meeting here. Anyway, thank you.
So the last lecture of this session is by Dr. S. Perun Cheral Athan, and he is associate professor at NISA currently. He did his PhD in IIT Kanpur 2004. After that, he was research associate. Then he did his postdoc in Germany, and he joined NISER in 2010. So I invite you, Professor. Please complete in 20 minutes. We'll have 5-6 minutes for debate.
Thanks, everyone. Thank you for a nice introduction. And outside, I'd like to thank the organizer for giving me opportunity to discuss about some of our. Okay. Always I have a problem between the last speaker. Several conferences I had the same issue. So I don't want to, I'm just in between your lunch and chemistry. So what I do is that I will try to give broad overview about our work, 1 or 2, and then we will wind up with it, okay? So as I said, the chairperson said that 10, 15, 20 minutes, I will try to before 20 minutes, okay? in NICER, we are trying to work in the four different problems. One is that synthesizing the new class of hybrid molecules. Another one synthesis of all carbon quaternary centers and functionalized organocatalysis and harassment drug discovery. So today's presentation, I have planned to do these two topics and so why we need to develop a hybrid molecules, and the other one is that how we come up with a new idea about rational drug discovery. Okay. Before I move to this topic, we have to understand that in the nature or in biologically active molecule, almost 85% of the molecule containing the heteroatom, basically heterocycles, 85 almost. Okay, and because we want to develop any drug, the heterocycle is very important. The reason is very simple. So heterocyclic molecule, one can easily modify for the solubility, lipophilicity, or polarity, as well as you can modify with the hydrogen bonding, donor, and etc. also. And these are the important points which require for developing a drug. Because as you know, this famous ADME works on distribution, metabolism, and exertion. These all depends upon the drug. So if you want to develop any drug, so we need to modify it at later in stage. Okay. So I would like to change the topic little bit. Instead of writing hybrid molecule, what we are really interested to make a hybrid heterocyclic molecule. So one can ask the question, why we need to make hybrid heterocyclic molecule? What do you mean by hybrid heterocyclic molecule? So here, look at the structure. I have written a few heterocyclic molecules. Most of you are very familiar with one, which is I like the indole, because the Fisher discovered the Fisher-indole synthesis after that several methods, because the indole is an important core when we are in active and all. Like, indole is a very important molecule. And if you look at the other molecules, these all are biologically important molecules. So when you look at in the literature, when you want to combine these two molecules, that's what we call as a hybrid molecule. So what we want to do is that we want to make a indole fused heterocycles. Indole of fused heterocycle. That's very important. So if you look at the literature, there are not many methods are available to make these type of heterocycles. So that's the one thing. We want to develop a new strategy how to make an indole fused heterocycles. And the second one, this which I showed over here. So we have some interest about these molecules. That is my last part of the lecture. So like, heterocycle having an amine nitrile, which have a different property in medicinal chemistry. So I would like to talk about this part in later. With this brief introduction, why we need to make hybrid molecules, let me go to synthesis. So how do you synthesize basically benzoheterocycles? So very simple way to do. There are two traditional methods, which I showed over here, method 1 and method 2. So what we need to start, suppose if I want to make an indole, I have to start with aniline. Just now Prasenjit showed about it. If you take aniline and you can make a carbonyl derivative, the same thing, this is one of the methods. Or you can start with a heterocycle, say for example, pyrrole, and you can convert the benzene. These are the two traditional methods available in the literature if one can make a benzo-fused heterocycles. So, but there are disadvantages of these methods. The problem with this one is that you need to have a heteroatom containing the aryl binding. That's really difficult. Some case we can make it, but the problem with that, if you put in a substitute on this side. And the second problem within a benzo, if you take a heterocycle and construct the benzene ring over, then we have a selectivity and all, there are some other issues. So what we thought that, so we can have a molecule like this. So if you look at my retrosynthetic analysis, suppose if I can break the bond, so you can have a arene and then pentane heteroatom array. Just lying the pentane heteroatom. So this can be done with an arylation or basically arylation, heteroarylation reaction. One can easily do our job. So that's my overall strategy. So we want to develop a new strategy making a benzoheterocycles. So we found, and we have to use the percentages saved my time why we need to use iodine. He nicely explained to you. Though I am not going to discuss any of this work, but we generally use these three conditions to make a benzoheterocycles. Copper, so we have seen that Dr. Goswami talked about its importance of the copper in biological system, and nickel. These are like bioabundant and this 3D metals. It's very important metals to make the carbon heterobonds. So we generally use this one to make heterobonds. Okay. And so let me go to actually the title says we need to have a synthone, right? So if you look at this molecule, it's a very simple molecule, benzyl cyanide.
just a benzyl cyanide. If you carefully look at the benzyl cyanide, you have two different reactivity sites. Say, for example, the green ones are electrophilic centers, and then red ones are in a nucleophilic center. So one can tune the reactivity choosing appropriately bis nucleophile or bis electrophile. One can tune it accordingly. We can do the rest of the chemistry. So as I said, this is actually kind of a pentane nitrogen. One can, if you can do a Grignard addition, and then after that we can try to get a cyclist. That was my original idea when we started this project, and but that somehow did not work. So we went through in some other way. And this another slide which tells you our overall work, what we are trying to do. You see the benzyl nitrile, and then we can easily functionize with this compound. We call this is the alpha functionized benzyl nitrile. This can be done very easily. It's a very traditional way of doing things. You can take isothiocyanate, carbamide, or ester just condensation. So you get, and then if you look at now, this molecule have an additional electrophilic center. So you, if you look here, this is electrophilic center, this is the nucleophilic center, and this is also electrophilic center if you have an halogen or hydrogen also, of course, and then here you have one more electrophilic center. So you can make the various heterocycles based upon choosing a nucleophile. So if I take a bis nucleophile, you generate a first generation of heterocycle. And here, what I'm trying to say is that if you take this compound, as I already pointed out, that you have an this is electrophilic and nucleophilic center, and you can have this type of compound, then still you can make a first generation of heterocycle compound. So these are all first generation. These are all known chemistry, which I am not going to talk about. We are not worried about it. How do you make this all well established? What is not established that this part. So if you want to, as I said, the pentane one cyclization. So this comes here. You have an tetraatom, you have a bromine, you put in a metal, you can do the intramolecular cross coupling reaction to generate a first generation heterocycle. That's what we are trying to do. And then after generating the first generation of heterocycle, we can make a second generation of heterocycle. So same thing here, if generate first generation of heterocycle at 30 seconds. This part is completely ignored in the literature. So we are trying to establish this one to make a various benzoheterocycles, in particularly indole-fused benzoheterocycles. With this short introduction, and so I will talk about the first work. This was sometime long, almost like, maybe close to 7-8 years ago. This is my first student, Dr. Manoj Kumar. He started to understand that when you take this compound, basically this is the electron withdrawing group, maybe nitrile, anything. So he wants to know whether the reaction can occur within the sulfur center or nitrogen center. He wants to see the chemoselectivity. So he screened the various metals. So I don't want to go in detail, just I give the highlight of the work. So he found that a copper and 110 phenanthroline and triethylamine, and at 2-hour condition, he can try to get a benzothiophene, exclusively chemoselective, the cyclization occurs in the sulfur center, not in the nitrogen center. But in fact, I was looking for the making indole, but it turned out to be this compound. This is my first compound, and this is going to be my last compound to discuss about it. Okay, so let it be surprise. And then, he can also show that it's highly chemoselective, and it occurs only in the aryl bromine. It does not occur in the activated bromine and all. So we got exclusively chemoselective. And then we can also could show about that there is no racemation occurring during this condition. So with this, and then he has done one more work. The part of that, if you have an R1, you have the phenyl group, and using a methane sulfonic acid or maybe tripleic acid, you can make it in another type of heterocycle. If you look at, could be imagine that benzyl cyanide, one could make two beautiful heterocycle with two synthetic operation. That's the beauty of this part. Okay, and then my second student, what he thought that instead of having a sulfur, he made it in both are nitrogen atom, and he could show the reaction at much shorter time. Within 15 minutes, this reaction was over. He could make an amino indoles, true amino indole, and then he could show about the different type of R and R2 group. If you have an alkyl group, the cyclization doesn't occur. If you have a phenyl group, you can exclusively get a highly chemoselective true amino impulse. And the compounds are characterized by the X-ray crystallography. And further, he also could show about the indole-fused quinolines. So one could imagine that starting from the benzyl cyanide, we can make a beautiful benzoheterocycles. With this, I will go to the next part. So what he has done next part, so since it was like, it is going to the sulfur atom, so he protected the sulfur atom with the S-meter. And now we have two options. One is that nitrogen can react with in this bromine. On the other bromine, he used the
initially he used the copper because we know that one is the copper will work here, but he got in other way around product. He got a quinolone product, and then so almost a few cases we got the low yield and quinolone, and then later we found that copper does not do any role here. Even the base catalyst under base mediated condition, one could make a quinolone. Okay, and then you can, it is another interesting part here is that the same molecule, if you change the condition, if you use the copper and 110 phenanthroline, you can make another heterocycle. It's called a benzofuran, used quinolone might. And then under radical condition, you can make a thiophene. There's the same material, same organic compound, one can plan to make 4 different heterocycles. I'm sorry, the 3 different heterocycles, but actually we want to make a different one, and it turns out to be this compound. And with this, and he made little more complication. So what he has taken is that he has taken, since he knows that the CO1 can occur at a metal condition, so he has taken this material. And then theoretically, one would expect that formation of 4 products. And then he screened the condition. I just saw the results. In the presence of copper, exclusively getting 1 product. So he got quinolone fused benzothiophene, this product exclusively 1. And he further went to that one. To use the palladium, one can do the 2 covalent coupling. And this reaction, one can make a CCCS CN bond in sequential manner to get, again, the same compound. The yields are not that good, but still one can make it in a 1-part multi-covalent reaction. So since we are not published as yesterday, Professor Maiti said about it, so you can, if you want to see that, you put Manoj and then you can see the whole thesis in HBNI website. Okay, and the next, there was my student, what she is trying to do is that she has taken the benzyl nitrile and then he coupled with an isothiocyanate alkylation, and she made the cyclization with this nitrile to make a 4-aminoquinoline. And then if you have a fluorine atom, then one can do under basic condition, she can make another derivative of the quinoline. Okay, so the earlier case was it's a different fusion, here it is a different fusion. So we could show about it, various substrate. And the next one, what I'm trying to say about that, if you can take the beta ketonitrile in the condensation of phenyl hydrogen, you make aminopyrazole. And then again, as I said, the bromine, amine is hanging, bromine is that under copper catalyzed condition, one can make a pyrazole fused indole. Okay, again, another type of heterocycles. And the interesting thing Arpita did was that we have 2 different bromine atom. It exclusively cyclized through this side. Then you are getting another type of heterocycle. It is a imidazole fused pyrazole. So this is another type of heterocycle molecule. And of course, this could not form. We thought that this will form, but did not form. We have done several studies. We proved that this forming only this. So with this, I will go to the last part of this particular thing. And if you look at, as I said initially, the hybrid molecules are not studied much due to that unavailability. This is an indole fused triazole unit. You know the triazole is well known, biological compatible molecule, indole as well. If you look at the literature, there is only 1 report. It was in 1970. It's a very complicated method to make. And another one is 2014 came to make this indole fused triazole. So what we have done is a very simple work. We taken the benzyl nitrile and condensed with azide to make a triazole, amino triazole. And then in the presence of copper, one could make a indole fused triazole. This is all, we have not published this work. With this, I will move to the next part. The next part of the topic is that the rational drug discovery. So before I go through that, already many of you, even Dr. Goswami explained about the importance of the cancer. Okay, I don't want to give an introduction about the cancer and all, because it's well aware, everybody knows about it. So what we are interested for the molecule is that this particular core, which I started at the beginning, the 2-amino 3-nitrile benzothiophene. Okay. So when we search in the literature, we want to show some application of the whatever compound we are making. So when we searched that, we found these of this bunch of the molecule. This molecule shows the anti-angiogenic activity. So one may ask that what is angiogenesis? So angiogenesis, it's a definition. Angiogenesis basically is a formation of the new blood vessels. Okay, new blood vessels. So why we need a new blood vessels? We want to transport the oxygen to the cell. So we need to have a vessels, new blood vessels. And then this is what actually angiogenesis is a good thing is that it will actually, there are two different types of angiogenesis, angiogenesis, anti-angiogenesis. Both are good for them. Okay. And that interesting thing about this, what I didn't know much about it. Still, whatever I understand it, I'm trying to explain it. The cancer cell has a peculiar feature because the cancer cells are not ordered cells. Then it will angiogenesis process much faster. Basically, the VEGF will activate the angiogenesis. So the cancer cell will make much faster. So when you develop an anti-angiogenic drug, so basically you can stop the formation of the vessels, the blood vessels. So then it is the point is that the tumor cell does not require any oxygen, cannot go to oxygen and cannot remove the deoxygenated product. Basically it dies. That's the fundamental about the anti-angiogenic activity. If anybody can give better information, I like to learn it. Okay, and this is the idea. So when I go back to here, so when I look at the structures, if you have some similarity in this, all the structure, these are all anti-angiogenic active molecules, which I found in the literature. So if you see that amino and heterocycle, if you look at all of them almost close to our structure. So we thought that why don't we test all of them to have an anti-angiogenic activity, whether it shows any anti-angiogenic activity. That was our idea. So with this idea, so what we have done is that we have made a more than almost close to 25 molecules. And then some of them I showed here is almost like, 19 molecules are there. We send the screening to the CDRI, Lucknow. So what they found is that the molecules, I don't know, I cannot see it in there is something in gold. There are those molecules, those compounds showing activity at 10 micromolar level. So after this, there are almost close to 7-8 molecules showed activity at the low level. And then what we went to do, another level, let's say, for example, we had to go for a 250 nanomolar range. So there, these molecules shows initially very much active. And when we went for a 250 nanomolar range, we got this is only active molecule. Though these two molecules, particularly the nitro and all, show some activity, somehow they did not take this molecule to further. So what they found is that this molecule is an active molecule. And they studied the different studies. I would explain one or two. I cannot explain everything. Let me say about it. So what they have done, this slide shows about the dose dependent, the different dose concentrations. Say, for example, this is the anti-cancer drug as a standard. So it's almost like, close to this one. If you can see the bar graph, if I can see, this is your anti-cancer drug. So even our molecule shows some of the low concentration. It shows a much better activity than the actual anti-cancer drug. Okay, and then this could be easy to understand for me, particularly if you have a control. This is with the this is actually a Martel plug experiment. When you see the standard drug and our compound, almost the color was vanished. That means it's acting as an anti-angiogenic compound. And then they can found about the hemoglobin content, and still our hemoglobin content was very less. The hemoglobin less means that it is very active. That's what the meaning is here. Okay, and then if you see here, this is also standard test, and then you can see the tubulin formation was almost disappeared in this case. This is the control, and the next experiment we have in vivo studies we already done. This is the tumor, and then the standard drug as well as our compound, we reduce the tumor size. And this much only I can try to explain. Please excuse me. Maybe next time I will try to read more and try to explain to all of you, because I don't want to give bad impression and saying something wrong. Okay, and with this, these are some other studies. I'm just not going to any detail. Let me go to that. So we want to prove it, whether this molecule, how it is acting as. When you look at the VEGF anti-angiogenic activity, there are receptors. There are three important sites are there. One is that this cysteine 917, the amino residue, and as well as here there is a phenylalanine 102. These are the two important active sites. Our molecules will go and bind it. So when we have a docking experiment, there's our active molecule. In fact, the molecule I showed, the other four molecule also show the activity. Only nitro compound shows other way of binding, but this compound shows the binding, and then
it almost like how it is showing this molecule is active because of these two regions. It's already well established with this one. It's not nothing to. And with this, so we recently, last year, actually, we published this paper in collaboration with Kumar. He is our collaborator who does all biological studies. And now currently what we are looking for that, we want to make it in a phosphonate, and then we'll see that how it goes. We cannot patent it, that above compound, because although it is close to Taxol, the reason is the molecule is already out in the literature. We cannot patent it. So what we are trying to do is that we are putting a selenium and try to make a similar type of activity. With this, I will conclude it with my last slide. So what I could show today, these are overall heterocycle compound one can make it. I did not show everything. Whatever the red box were there, those only I showed it. And then basically, if you start with the benzyl nitride, and then you can imagine that this whole type of heterocycle one can make fine tuning of the choosing coupling partners. Okay, and with this, I would like to thank my students. These are the students, my graduated students, PhD. Those who are in blue, I talked to their work only. I spoken here. And this Vishwaprabha and Tirupati, they have done the medicinal chemistry work. They made all the compounds. And these are my current students. And total 17 master students communicated with me. Yes. And then these are collaborators. Kumarvel is the biological studies. Venkatesh, we have some boron chemistry. We have a collaboration with him and with Professor Nakamura from Japan. And Professor Srinivasan, we have a collaboration with AI studies and all. Luraj is our computational chemist, and Krishnan also we had some collaborative work with some polymers. With this, thank you for your kind attention.
Thank you, Dr. Perunchandran, for a nice explanation about your research activity of the research group. Is there any question from the audience?
Just what you mentioned regarding the cyclism, the cyclist is preferring one of the bromine atom. That why it is selectively preferring one bromine atom over the other. Why it is cyclized problem?
That's actually when you have the emitter to other side, the nitrogen is more electron rich bromine. So since you have a nitrogen atom, so this bromine is more electron rich as compared to. That's the reason it's cyclic others.
Other question? There are no more questions, then thank Professor and thank you for So this session comes to an end now. So we had 4 lectures, and all the speakers they have done an excellent job by sticking to the time. So I thank the organizers for giving me this opportunity to share this session. So thank you.
Okay, so we did the session, and then we thank Dr. Mahapatra for sharing the session. On behalf of the organizers, we'd like to give a small appreciation. Fine. So finally, we are breaking for lunch. We are late, but we'll try to be back by 2 o'clock for this booster session. Not 2 o'clock, 3 o'clock. Sorry, 3 o'clock. That's not possible. 3 o'clock. We come back, and then yeah. So. So this poster session that is going to be today from 26 onwards will be evaluated by a committee which will be chaired by Professor C.N. Patra of BARC. The convener is Professor T. Das from BARC. And other members in the committee are Dr. V. Krishnan, Dr. S. Perunchandran, and Dr. C.S. Purohit. So we'll meet by 3 o'clock. And we'll try to be on time for the next one. We'll start at 4:30. Before we go for lunch, if the speakers for the next session, they are ready with their slides, we can load them before lunch. That will be better for us. Poster session? Okay, we'll do it for poster session. Fine. Trying to make it. Good afternoon. Welcome back to this post-lunch session. The first we have two sessions now, and we are happy to start it on time. But before we go to this one session, what we'd like to do is that the chairman and the convener of the poster session would like to present them a small of the organizing committee. So may I request Professor C.N. Patra and Professor Tikas to please come to the steps. Thank you. So now let's move to this oral session. This oral session is going to be chaired by Dr. Sanjeev Kaur of Niger, Bhubaneswar. Sanjeev Kaur studied chemistry at the University of Burdwan and the University of Kalyan, West Bengal, India, and he received his PhD from IIT Bombay, India, in December 2005, under the supervision of Professor G.K. Lahiri. In April 2006, he moved to the Kyushu University, Japan, as a JSPS postdoctoral fellow to work with Professor Yoshinori Naruta. He joined the Niger Bhubaneswar as an assistant professor in 2009. Since 2016, he has been an associate professor at the School of Chemical Sciences, Niger Bhubaneswar. His research focuses primarily on synthesis of and application of porphyroid and metalloporphyroid-based molecules. Thank you. Now, with this short introduction, may I call Dr. Sandip to share this session.
Good afternoon, everybody. I would like to welcome you all for this session 6, and we have three speakers in this session. And its first speaker is Dr. Juhur Alam Mandal, and our second speaker is Dr. R. Kumaresan. In this occasion, I would like to introduce Dr. Juhur Alam Mandal. Dr. Mandal is a master in chemistry from the University of Burdwan, West Bengal, and joined as a scientific officer at BRC in 2002. He obtained his PhD in the field of femtocycle time resolved spectroscopy from the University of Mumbai in 2009. He did his postdoctoral research on nonlinear laser spectroscopy at surface and interfaces at Riken, Japan, under the guidance of Professor. So his research interest includes phase sensitive frequency generation spectroscopy, novel spectroscopy, etc. So, with a brief introduction, I would like to welcome Dr. Mohan. Very good afternoon. First of all, I would like to thank all the vendors for giving me the opportunity to talk. And as it is a discussion with you, I have decided to present our work in this format. First, I will briefly explain the background of it, and then I will focus on the technique, because for the surface and interface measurement, we have developed some advanced techniques here. So I will discuss about those techniques well, their strengths and weaknesses, so that you can get a clue of where this technique can be useful. If I am able to convince you with the strength of this technique, you can come up with ideas so that we can collectively grow. And that part I will demonstrate with a little bit of our results in our laboratory. So with that, so when we talk about a surface or interface, it's nothing like, for example,
For example, if you consider this kind of sample, it is nothing but a solid sample. So it is, in terms of interface, it is a solid surface with gas solid interface. It's not a hard interface. So these kind of surfaces you can monitor by surface sensitive techniques like this. But they require some stringent conditions like ultra high vacuum. Whereas liquid-liquid interface, for example, here organic and aqueous phase, here it is air and water phase. So this thin layer over here, where the air mixes with the water, so the thickness of that interfacial medium is less than an mm. And of course, it varies with the nature of the medium. So assuming the case of air water, it is just hardly 1 or 2 water in the thick, meaning it is sub-nanometer level. So in that scale, the structure and properties of water are very different. Not only water, if it is any other medium, then also the thin region is a very unique environment for chemical reaction. And our goal is to monitor the interface at the molecular level. So this is basically collectively called the macroscopic interface because it is macroscopically the surface is there and we are monitoring how the molecules are oriented, how they react. However, if you go deeper into that, if we add some solute into this glass of water like this, then these solute molecules will be hydrated over here. So we are quite frequently, we look into the properties of a solute in different solvents. For example, if we vary the solvent polarity, their absorption and emission characteristics. But at the same time, if we look into the same phenomena from the solvent perspective, then when you change the solute, how the solvent is affected. And we know that in chemistry, it is not only the solute, but the solvent also plays important role because it is eventually the solute-solvent interaction. So here our objective is to look into the immediate vicinity of the solvent. Into that, how the solvent molecules are changing. For example, if you see this figure, if it is a liquid water, for example, they are vibrating in a synchronized manner. But if you put a solute, this vibration, the synchronization is affected in its immediate vicinity. So today I am not going into that part, but this is how the molecular interface means, and I will discuss in the context of some frequency generation results which will monitor the macroscopic interface and collectively see how far these two techniques can take us. So this apparently innocent glass of water basically which represents the air-water interface is ubiquitous in nature. For example, if we look into the sea surface, then part of the water, Earth's surface is covered by water and it is basically air water. And there it is various kinds of solute molecules, ions and hydrophobes are there. And when this kind of bubble bursting takes place on the sea surface, it creates a kind of aerosol particles. So these aerosol particles also contain ions and organic molecules, and there also is a distribution of the ions and molecules at the surface of the water droplets. And there is a kind of surface chemistry involved over here. Same way, if you look into the biology, then also the biological lipid membrane water interface is a kind of bilateral border that decides what will go inside and what will come out. And hence, when we talk about the interface, this is basically the lipid water interface. So let us ask the question, what will be the character of the water or a solid molecule at the surface of it? So these are the questions we try to address by some novel techniques. So naturally the question is, how can you probe the interface? So like ordinary spectroscopy, if we put some light, what we get is transmission or emission, which we generally monitor by absorption and fluorescence spectroscopy, and some reflection will be there. But certainly this absorption or fluorescence spectrum will contain information about the interface, but that will be very, very, very weak because the thickness of the interface is sub-nanometer to nanometer range, whereas the bulk thickness is huge. So certainly this kind of linear approach will not work. So we have to do something different. And it is that if we put instead of one light beam, if we put two light beams of high intensity, then some nonlinear interaction which takes place at the surface generates a different frequency that is called the sum frequency. And this sum frequency generation involves nonlinear light matter interaction. That's why it is called nonlinear frequency. So if we are able to monitor this sum frequency, then we can get insight about the molecular information and in the interface region. So let us look into that. What is the nonlinear interaction? Little bit briefly so that we can appreciate it. So light is nothing but an oscillating electric field. So when it falls on a molecule, it creates induced dipole. So when the intensity is not so high, it is linearly proportional. But when the intensity is very high, the magnitude of the amplitude of the dipole moment is very high. And correspondingly, the induced dipole moment is a nonlinear function of the incident light electric field. And in that case, in a macroscopically, if we think, then the dipole moment per unit volume, which is called polarization, becomes a combination of first order, second order, and third order terms. And it is this second order term which leads to this kind of sampling. And the beauty is that the sum frequency generation basically takes place only at the interface. And that's how that technique is inherently interface specific. Meaning, automatically there will be no signal when the medium becomes isotropic. That is the beauty, that we do not care about how depth it is monitored. Wherever there is inversion symmetry, the signal will be generated. But it has a problem also. Then as the signal, for example, if we take a charge surface, then the signal will be generated from a thicker level. Then we cannot differentiate basically from the surface and power. So that is the weakness of this. So anyway, so if we monitor this sum frequency signal, what we observed is this kind of spectrum. So apart from the normal width stage band, which is quite broad from 3000 to 3500 here, there is an additional sharp band around 3700 centimeters, which is absent in the case of pulsar. So this shows new feature at the water surface, which is basically this water is called kind of free OH dangling at the water surface, which is facing the air. But if we go again a little bit deeper, then how this sum frequency is generated? For example, when these two light electric fields are coming, they are interacting, and because of this preferred orientation of the molecules, some frequency is generated. That is what we are detecting. Now, suppose let us change the orientation of the molecule like this. Then what we have? The sum frequency which is generated, it will be off phase by 180. So what we did here is, if we measure the intensity, we are doing the square of the electric field. So naturally, we are losing the phase information. So that means whatever I have said so far, we are not using the full potential of the nonlinear spectroscopy. So if we, instead of detecting the intensity, if we detect the electric field, then we can talk about how the molecules are oriented. So that is what basically the effort was taken in around 2007 and 2009 during that time. So this shortcoming was overcome by Professor Shane at University of California in 2009. And here he has measured the water spectrum with heterodyne detected sum frequency generation, which can talk not only about the surface water vibrational spectrum, but also the orientation of the molecules. As you can see, this green spectrum, which is having a negative signal over here because it is zero line, and here it is a positive signal. So this negative and positive indicates their orientation. And subsequently, Professor Tahada in the same year, he has further improved the configuration of the instrument and produced a very stable HDVSS spectrometer, which can record the broad spectrum like this. And based on that, we developed a phase-sensitive heterodyne detected GSMD spectrometer in BRC. And we report our first result from this setup in 2016. So as you can see here, this is the laser system which produces the femtosecond laser pulse. And then we convert it into the different frequencies. And then visible and IR, they're coming and overlapping on the sample. So this sample is basically, this is the good part. This sample is open in the atmosphere. So just like that, it is a glass of water. So the water surface we are probing. So no sample sequence. And then we are doing the heterodyny of the signal. So I am not going into the details of that, by which we can essentially monitor the electric field of the signal generated. And then these are the further analysis of the data, raw data, which gives us finally the imaginary and real Kaitou spectrum. So imaginary Kaitou spectrum, apparently it appears like something very awkward type, but you can take it for the, particularly for the students, basically IR spectrum with a sign. That way you can interpret the imaginary Kaitou spectrum. So the details are in this book chapter. I'm not going into that. Then when we measured the air-water interface, this is the spectrum we have observed, which is consistent with the previously reported by Shane and Tahara.
And this is the homodyne and this is the heterodyne. You can see there is a negative sign and positive sign, whereas here everything is positive. So based on that, now we will look into the some of the results. But before going into that, this heterodyne setup, where we are doing further analysis with the signal, but this is a homodyne setup, which is called the classical or conventional BSC setup. This setup is again, there are only 3 setups in India at present. One, of course, this is the first setup came in India, BRC, Sir HBNI lab, and they are the first person in India to publish the VSLG paper, I think 2014 or 15 in that time. And after that, we developed this heterodyne detected VSLG, which we reported in 2016, and subsequently from IIT Ropar and IIT Kolkata. So presently, there are 3 laboratories along with ours, which is basically so that can monitor the surface molecules. And now I will discuss briefly some of our results. So for example, when you are talking about the biointerface, so in the inside the cell, there is a molecule called trimethylamine N oxide, which is known to protect the cell from a kind of stress like hydrostatic stress or where the protein structure is basically gets denatured, volume strength and all those things. So this molecule helps to maintain the protein structure. And how does it do? By modifying the water structure around it. So that's why knowing the structure of water around this molecule is important. And with that idea in mind, basically, some Professor Paul Kimmer's group, they measured this TRAMO molecule, trimethylamine N oxide, and the silica water interface. And based on that, they proposed that this molecule is a very peculiar molecule. And the oxygen molecule basically faces the hydrophobic region. That means the protein surface, the oxygen part of that molecule will face the hydrophobe. And the methyl group will face the opposite way, which is quite unlikely from our conventional knowledge, because hydrophobic group is alkyl group. So naturally, they will prefer to orient towards the hydrophobic protein. However, they proposed that based on the homodyne BSC measurement. And then we did the heterodyne measurement. And here you can see, here the CH stretch of trimethylamine N oxide, it shows a negative signal. This negative signal means methyls are pointed towards the hydrophobic. So it is exactly the opposite result what they have. So this is the strength of the heterodyne technique, that apart from the homodyne, it can provide you additional information. But having said that, homodyne itself is a very powerful technique because that can probe at the molecular level upwards. Then this molecule not only protects the protein from denaturation, this also has some negative impact, which recent result has shown that this molecule helps the deposition of fat to the artery, inner wall of the artery, leading to the hardening and narrowing of artery, and which we all know, which subsequently leads to the cardiovascular disease. So we observed that in some papers they have systematically studied, particularly the biologists, and they have shown that this molecule is the culprit. So we applied that knowledge to try to understand the biophysical aspect at the membrane water, how the electrostatic will change at the membrane surface. So with that idea in mind, first we measured the pure lipids, because it is a complicated system, so we have to simplify it and measure and then put other things and try to analyze the result. And once we did the pure lipid water interface, we observed that depending on the charge of the lipid, the water molecules are orienting their hydrogens oppositely depending on the charge. Now what we are doing is, we have put the trimethylamine molecule into different lipid surfaces, and we found a kind of surprising result that when the lipid is cationic, for example, this is the strong signal from the pure lipid, and when we are putting this PMAO molecule, the signal is decreased. Whereas it is important to note that PMAO is a deuteronic molecule, that means no net charge. So we can expect that it is a neutral molecule, so hopefully there will not be any significant electrostatic, but it is not that. Whereas when it is a negatively charged lipid, not much disturbance of the signal. Whereas in the case of deuteronic, the signal is also increased. So based on that, what we propose is there is a site-specific interaction between the oxygen, negatively charged oxygen of this molecule and the positively charged oxygen polyene of the lithium molecule. So that means there is a site-specific electrostatic interaction at the liquid water interface. So
this leads to the electrical disturbance, possibly has some role in the accumulation of fats and lipids. Then another aspect of that biointerface is the basically the aggregation of neurodegenerative disorder producing peptides like alpha-synuclein. And you know that Parkinson's and Alzheimer's disease are basically these due to the deposition of the aggregated form of this kind of protein to the neuron cell surface. That is what has been observed. So our idea is that whether if we apply this EGDSM technique, can we talk something about what is happening at the membrane surface of these alpha-synuclein peptides? And here what we observed is that when the lipid is cationic, because this lipid what we are taking, because the neuron cell membrane, they are lipid basically. That's why we have taken this cationic and anionic lipid. So this peptide is actually having a negative terminal and a positive terminal, C-terminal and A-terminal. And that means there is a local domain of charge. So when we are monitoring the cationic lipid surface, we observe that there is a decrease in signal which is increasing the concentration of the peptide. And at the anionic surface also there is a decrease. So this is a bit contradictory. For example, if the cationic surface, the signal is decreasing, we can understand the cationic charge is getting neutralized. But at the anionic surface also, it is getting neutralized. That means anionic surface is also getting interacting with the lipid. That indicates this peptide, this N-terminal and C-terminal, they are interacting in a complementary nature. And that's how this initial nucleation, that means the absorption of the alpha-synuclein molecule at the liquid surface takes place, which is guided by this kind of liquid surface. And few other things in the atmospheric aspect I will discuss. For example, this one is a kind of biological lipid membrane, some pollutant molecules like perfluorinated, persistent organic pollutants. So fluorinated compounds are called ever chemicals. Once they are released in the environment, they will stay forever. So naturally, in the biocycle, they will enter in our body, and of course, the cell membrane is the initial fiber. So we try to understand again that how they interact with the cell membrane head groups and lipids, and then we observe that again it is a charge-specific phenomenon. And then here this is a very interesting example from Professor Vidinayak's group. What they have shown here is they have taken CTAB and SDS, two surfactants. So when these surfactants are present independently, then the signal is, there is a strong water signal because of the charge nature, but the CH stretch signal is weak. But when you are mixing them, even at very, very low concentration, they are accumulated at the top. And you can see there is a strong signal, the red CH stretch band, whereas the water signal is different. So it is a charge-induced adsorption at the water surface, depending on the sign of the charge. So another example, for example, the ions at the surface of water droplets. So for example, iodine in atmosphere plays important role in new particle formation and all those things. So I have narrowed down into the fact that what is the source of iodine? It is the seawater basically, and where. So these I minus and IO3 minus are the primary source of iodine. So naturally, at the sea surface, how these ions will come and interact with the surface water and other surface particles, that is what it is. And then, yeah. Then we monitor these two ions, not only two, another I3 minus also we have monitored. And IO3 minus is known that it is a very strongly structured, strongly hydrated ion. So it was thought that it will not go to the surface. So only source of iodine is mainly I minus and I3 minus. But when we measured the surface water, we found that I3 minus do disturb the water structure. That means it is going at the surface. So we propose that I3 minus is going at the surface, then why it is going at the surface, it is strongly hydrated. That's when we decided to monitor the hydration cell and what is the structure in the bulk water, how strongly they are hydrated so that eventually they are going to the surface. To study those things, basically we developed the hydration cell spectroscopy based on Raman spectroscopy and persistent analytical approach. For example, you can see this is a raw spectrum of a magnesium chloride water solution. And then we did the analysis and we found out the hydration cell of magnesium ion. So you can clearly see this is very different from the bulk water spectrum. And based on that, we proposed new water species in the hydration cell of the capacity. But anyway, this is not the focus of today's presentation, but I will apply this Raman DS SCF technique to understand the hydration of the IC minus, IOC minus, and I minus. And remarkably, we observe that hydration characteristics in the bulk is very similar to the hydration characteristics. And based on that, we propose that it is the hydration character of the ion which decides how the ion will go and where they will sit at the interface, and what will be the kind of interaction and what. Yeah, so this is what is summarized over here, and further details about even if it is not going into the top surface, if it is below the surface, what will happen. So further, somewhat we have done. So finally, here I conclude the take-home message is that HG and Raman GSSCA is a powerful combination that can provide molecular details of interfacial phenomena pertaining to biology and materials. So now it's up to, basically my idea is to present the strengths and weaknesses so that in this discussion meeting, based on the purpose of the meeting, so that you can think of if any application is possible, so please contact us and I'll be very happy to pursue some research collection. Thank you very much. And one more thing, which is the most important thing, basically, I'm very sorry that I'll there. So these are my two PhD students, Dr. Mohammed Ahmed and Subodip Roy. They are the basically workforce. It is their work which I'm presenting here. So one student, PC course, and my collaborator, PC Singh from cultivation, and of course my junior colleagues, my seniors, who strong support actually enables the problems that are seen here. Without their support, of course, the department. Thank you. I'd like to congratulate you. So this session is now open for discussion. So anybody has any queries, please free to ask.
Wonderful lecture model. Actually, I have a curiosity-driven question. Actually, you have done all the experiments at ambient temperature, right? But is it possible to do temperature dependence on frequency generation spectroscopy?
Yeah, that is a very good idea. In fact, we tried it, and the problem it was coming in whenever we try the temperature dependence, some impurity is coming out. And another problem is another important, the criticality of this experiment is a phase sensitive experiment, meaning the water surface, we consider the water at ambient temperature, it will vaporize, right? So once the water vaporizes, the height will decrease. So that will lead to phase zero. So those critical things I have not discussed. So when you increase the temperature, it will evaporate faster. So then maintaining the phase accuracy becomes very challenging. In fact, we monitor it by a sensor which can control the water level continuously during the experiment with plus minus 100 nanometers. So even then I have found that there are phase uncertainty. So to be honest, we could not conclusively do the temperature dependent experiment. That's why it's not published.
Okay, one more question. That aqueous organic interface study is always challenging, right? But is it possible to use some model to study aqueous organic?
Some model?
Model in the sense, like real organic you cannot keep, right?
Yeah.
But instead of that, you can use some kind of model where it can be extrapolated to aqueous organic.
Yeah, actually the system, whatever repeat I have used, to be honest, it is extremely simplified system. It's far from the real repeat membrane. But I do wish we can make our system a little bit more complicated so that it is close to the real system. But it is difficult. But we need to try.
Hi, I have just one question. It's a wonderful talk. So this, your heterodyne has the potential to get the orientation of the molecule. My question is, what is the spatial resolution in the XY direction? Are you measuring just one molecule or you have multiple molecules?
We have multiple molecules because that we
are they oriented with a similar fashion or it's different?
It is an ensemble picture whatever we are getting because the water surface is dynamic because molecules are continuously getting evaporated. So it is not a static surface. So whatever we are monitoring is an ensemble picture. But surprisingly, from the MD simulation, whatever picture we observe and the experimental data, they suggest that even being in dynamic equilibrium, the observed experimental results are quite favorable.
Do you think the orientation of the all molecules are more or less similar?
No. It's a net orientation.
Okay.
So not all molecules are the same.
Thanks.
I have a question before. Just continuing with this question. I said you don't need to keep it in down.
Yeah.
And then 40 degree to 20 degree, 20 degree.
Yeah, we can cool it down.
You will not have the method to memorize.
Yeah, but my point is that broader is the range that is better. Because by cooling we can go, for example, okay, 4-5 degrees.
By 40 to 55, will not form ice then.
Of course, that we can do, but you see the surface is a 1 or 2 water molecularly active. Now, 42, for example, 0 degree level. In that range, whatever change you will observe, if you can make it 100, then the whole region you can study it. Another thing is, it will, many other things will come into picture, the temperature dependence and intra-intramolecular coupling and their temperature dependence. We need to complete the whole day, the high temperature as well.
1.1. Yeah.
Yeah.
So, have you ever tried mixing water and alcohol?
Yeah, we have measures.
Is there any change in it?
Yeah, it is. For example, I can say you, for example, if you go to methanol, we inherit the alcohol. So ethanol, propanol, like that. And then kind of aggregation takes place when you cross like 3-4 carbon atoms, something like that.
No, the curiosity is about I keep the wedge number of wedge groups same.
Okay.
For example, I take 2 molecules of methanol and 1 molecule of water. 1 molar ratio. Any change in the interface?
Suppose you find a change.
Because your
what is your
wedge, the
expectation?
touching region is very broad. We don't have any information of rollness or the
Yeah,
intensity
but
of the wedge.
change, but that change, if you can say what you are expecting, then we can better put it. Of course, there will be change. And we have measured the concentration.
Yeah, I have a question. Here. Yeah. So both your anion as well as your cation showed the decrease in the intensity.
Yeah.
In a spectrum.
Yeah.
Can you elaborate on that? You couldn't spend time on it.
Yeah. So what is happening, you mean that alpha synuclein, what you are talking about, right?
The lipids.
Lipid, that alpha synuclein at the lipid interface. So alpha synuclein, it is having a C-terminal and N-terminal. So it has a positively charged domain and a negatively charged domain. And overall, it is negatively charged. So that is the protein, peptide. And now when we are monitoring the negatively charged lipid interface, so this protein as a whole is negatively charged. So it should repel from that.
Very nice presentation. I'd like to know whether can you draw any correlation with respect to Brownian motion of the solid molecules and the surface tension as a gross property, macroscopic property with respect to this type of spectroscopic state?
I feel it is Brownian motion might be difficult, but I can try to correlate about the structural change in presence of, for example, the ion and the surface tension of the water. That way we can do.
And over the small book. Our next speaker in this round is Dr. R. Kumaresan. So let me briefly introduce Dr. Kumaresan. Dr. R. Kumaresan obtained master degree from Madurai Kamraj University in the year 2002. He did PhD in the field of separation science and received doctoral degree from University of Madras. He joined IGCR in the year 2009 as scientific officer 3. He significantly contributed towards the development of process for minor actinide partitioning and subsequent radioactive wasting. His current project is on direct oxide electrochemical reduction of metal oxides. His major research interests are molten salt electrochemistry, electrometallurgy, solvent extraction, and ion exchange. He has about 35 publications in peer-reviewed journals and about 50 national and international conference proceedings. He is one of the recipients of BAE Group Achievement Award in the year 2011. He is a line member of Indian Association of Nuclear Chemists and Allied Scientists and Advancement of Chemical Sciences and Education. He is associated in conducting radiochemistry workshops in various schools and colleges. With this brief introduction, I would like to welcome Dr. Kumaresan.
Thank you. Thank you, the organizing committee, for this opportunity. The topic of my presentation is molten salt-based electrochemical preparation of metals and alloys from oxide process. As implied by this title, that I am going to discuss one of the methods for the preparation of metals and alloys. And this process involves electrochemical method, and the process uses molten salts. Okay. As all we know that metal have played a significant role in human civilization, in leading the human civilization. And the preparation of metals from ores has been known to the human kind from the time immemorial. The preparation of metals and the preparation of alloys and the preparation of pure metals has been learned by the mankind from ancient times. And this is the flow chart for the extraction of metals from various ores. And for different metals, different steps were involved. I'm not going to deal about this flow sheet. And this flow steps depends upon the reactivity of the metals. And depends upon the reactivity with metals, the steps will differ. And here, most of the in this one of the main important or most important step is the reduction of metallic compounds to metals. This is the last step. This is also called as the last step for the gaining the metal, and this is a very important step. And this metallic compound mostly will encounter species is metal oxides. And one of the good thing about this metal oxide is more amenable for the amenable free form for the reduction. So metal oxide, if it is there, it is convenient to go against the metal. So for reducing this metal oxide to metal, and we generally this rule of thumb is this follow the Ellingham diagram. I am not going to discuss in detail about this Ellingham diagram, as all we know. And in essentially, this Ellingham diagram, whatever the metals placed in the top, it can be is less stable and it can be easily reduced, and followed by the medium stable oxides, and the most stable oxides are present at the bottom of the this Ellingham diagram. And in essence, this if I want to reduce one of the metal oxide, for example, I'm telling the titanium oxide, I cannot use either of this metal from the top of the Ellingham diagram. I cannot use zinc to get the titanium oxide from titanium. I have to use whichever in the bottom of the Ellingham line. And for example, this titanium oxide can be reduced to titanium easily by either by magnesium or calcium. And this is the basic principle of this Ellingham diagram. And most of the metal preparation they used to follow from this Ellingham diagram. Anyway, I'm not going to discuss about this Ellingham diagram, but this is the basic foundation for choosing the reducing agent. And now, one of the main important of this Ellingham diagram is usage of carbon. And the carbon is frequently used for the industrial production of metals. And whoever interested in the preparation of metal, first they will follow the carbon line because it's easily available and it's too economical and well established procedures. So, as I told you, the classical example for the use of carbon is the production of iron, and this is the blast furnace. And this is from centuries that people are using this method for the preparation of pig iron from the iron ore. And another example I have given is this is a classical example. and titanium metal production from the crawl process. The crawl is the pioneer for the, he even invented this process. And this crawl process basically consists of two methods, there is two steps, sorry. And one is the carbochlorination to convert the titanium oxide to titanium chloride, and followed by the magnesium reduction. So it's a two steps reduction, sir. It's being followed in the industrial production of titanium. And here I am going to propose the new method, and which is developed in 2000, and it is a direct oxide electrochemical reduction. Next slide I will brief about the reduction. The salient feature of this reduction is as follows. The solid metal oxide cathode is directly converted to metal in this method. There is no dissolution of metal oxide in the molten salt or something else. This directly can be converted into metal. And unlike conventional chemical reduction, here there is no handing of reactive metals. For example, as I told here, we have to use the elemental magnesium for the reduction of titanium chloride to titanium. Here it is not required because it's intuitively it will be developed. And the process is relatively simple and efficient process. The process is more safe and less cumbersome compared to conventional process, and convenient method for the preparation of alloys and intermetallic compounds. That I will discuss the subsequent slides. And this is the two variants are there in this process. One is FFC Cambridge process. This is Bray, Potting, and Chen. These are the inventors from Cambridge University. That's why it is called as the FFC Cambridge process. And another variant is electrometallothermic. In this case, I have mentioned the electrocalciothermic reduction. And I will explain these steps. First of all, for this, as I mentioned, this is an electrochemical method, and it uses the molten salts. And this is the electrochemical cell. It consists of three parts, as everyone knows: anode, cathode, and electrolyte. Here you see the electrolyte is a molten salt. Here, whatever I have mentioned is the example is a molten calcium chloride. Mostly this molten salt being used for this FFC Cambridge process. Why calcium chloride? Why calcium chloride means this has the higher solubility of oxide. That's why we are using calcium chloride. And as I told you that the cathode is a metal that is oxide. And metal oxide can be any form. Here I mentioned about just like a pellet form. And you can take a granular form, a powder also you can do it. And what is the first basic requirement is porosity. You should have some porous metal oxide. Why porous metal oxide is required is in order to diffuse out this oxide ion. For this porous structure is required. And also for the molten salt can easily diffuse. For that only this porous structure is required. And anode generally graphite is used considering this economic part. And the reaction as follows. That if you see that cell, if the cell is polarized in the cathode, if I am passing the electron, there is passage of voltage, and that polarized, what happens is this metal oxide ionizes. So electrons from in the cathode, it pumps into that solid metal oxide, and it ionizes this metal oxide, and the oxide ion will release. This oxide ion has a solubility in the molten chloride, and it passes to the anode, passes towards the anodes, and there it reacts with the carbon and forms carbon dioxide or carbon monoxide. The overall cell reaction is metal oxide reacts with carbon and gives carbon dioxide. But this is the overall, I am saying about the overall chemical reaction, but effectively what is the reduction agent here is electron in the FFC Cambridge process. And one more thing to note here is this: the operating voltage is 3.1 volt. Why this is? This calcium chloride, we are giving the polarization not to decompose the electrolyte, because if you decompose the electrolyte, calcium will also liberate and chloride also will liberate. That will decompose the total system. So we have to operate the voltage is less than 3.1 volt. There is no calcium is generated. And sometimes you require the metallothermic reduction. Here even electron itself sufficient for the some of the metal oxide to metal reduction. In some cases that I will discuss later, that electrocalciothermic reduction I have mentioned here, this is important. Why? Because it's like even electron may not be sufficient to completely reduce the metal oxide. For that we have to use the electrocalciothermic reduction. Why electrocalciothermic reduction is this is institutionally produced. That's why I mentioned as electrocalcium. We are not adding anything externally calcium into that. And here the reaction is I will add calcium oxide along with the calcium chloride and apply the potential. That applied potential will allow the decomposition of the calcium oxide, wherein the calcium oxide decomposes and produces the metallic calcium on the cathode, and O2 minus will liberate, and that goes towards the anode. And final reduction is like a calcium will reduce the metal oxide and form calcium oxide. And overall cell reaction as implies here, MOO2 plus C gives MO plus CO2. And what is the reduction agent is, reducing agent is calcium. And the operating potential, cell potential is above the decomposition potential of calcium oxide and should be below the decomposition potential of calcium chloride. And once the calcium oxide is continuously consumed, I can charge once again whenever required. And this is the experimental setup. Just I mentioned here, this is the various forms of cathode we have used. One is like for R&D purpose, we used one single pellet of some 12.5 mm pellet. We dye it, and this is the acts as a cathode for our R&D studies. And this is for the uranium oxide, and this is the titanium oxide. If you have this type of higher volume of this metal oxide, we have to use this type of baskets. We will fabricate this basket and we will use as a cathode this basket. And this is the platinum anode we use for the uranium oxide reaction, and usually graphite also will be used. And this is the experimental setup. This is in this case I have mentioned about the lithium chloride melt. You see the lithium chloride melt contained in the SS anode, and this is the experimental setup. And it is very, I can just do one slide, I can discuss about this experimental setup, but it is not like so simple, because even calcium chloride drying we used to take 1 week. It is not very easy to prepare the moisture-free molten salts. And also loading the cell should be done inside the argon atmosphere box. And first work what I am going to present here is the toughest job, that is electrochemical deoxidation of thorium oxide. I am not giving as a reduction because we did not observe even the complete reduction of thorium oxide to thorium. Some reasonable level we got it, that I will discuss. And no need to introduce thorium to the nuclear community. Thorium finds immense applications in the nuclear industries. Apart from the thoria, some of metallic thorium also is also used in the fuel. For example, thorium, uranium, plutonium, thorium, uranium, plutonium, zirconium, etc. And this has more better physiochemical and nuclear and thermal properties compared to the uranium analog. And this metallic thorium conventionally is prepared by the addition of calcium. As I mentioned, that chemical reaction of thorium oxide with calcium at 1000 degree and has formation of thorium, and has some disadvantages in this process. What are the things? Handling of this excess calcium, that is the elemental form we have to handle, and whatever the slug formed in this during this that is calcium oxide, that has to be removed. That finds difficulties in this process. So we have boldly started this thorium oxide reduction with our experimental setup. It is our process, that is FFC Cambridge process. And this is the Ellingham diagram, and we can see the closeness line of this thorium oxide and the calcium oxide. And we cannot, as per this Ellingham diagram, we cannot reduce thorium oxide either by calcium or aluminum or whatever the common available reducing agents. And if you take the carbon can reduce only thorium oxide at 1800 Kelvin. So in that case, we have taken, don't have any other options other than the calcium. So here we have taken the calcium as a reducing agent. First, we did with the electron as a reducing agent. I told you the two variations. One is electrocalciothermic reduction, another one is electrothermic reduction. What I mean to say here, electrothermic reduction is only electron is access a reducing agent. So we tried with the electrothermic reduction, that is called FFC Cambridge process. And we started with different duration of electrolysis. This is a current versus time graph, and initially high current is recorded. That is usual for this type of electrolysis. There is a 3PA mechanism. One mechanism they will call a 3PA mechanism, that is called electrolyte, oxide and metal. That interface leads to this type of high current initially. After that, immediately it drops within a minute, and the constant current will be observed. This is the observation of the current versus time profile. And any variation in the current implies that there is some stage of some products are formed. That way it be indicated from the current. From the current graph, we can understand that there is no significant change in the current. It is almost constant, and that implies that there is no intermediate compounds were formed during the electrolysis. And this is the time versus potential graph. And as I told you, this is the calcium deposition potential, but you see the operating potential is less than the calcium deposition potential. So this is the experiment, and initially we did from the up to 48 hours, and this is given here. And finally, up to we have gone to the 96 hours. The photograph of 96 hours is shown here. You see the sintered thorium porous pellet, and it directly reduces to the thorium metal. It's a huge advantage of this process. And this is the evidence for this, this pathway of this reduction from 2 hours to 96 hours. And always we observe the thorium oxide. Wherever you take, you have some small peak of thorium oxide. Only 96 hours we did not observe any thorium oxide peak. And also this is a surface exciting. Bulk also we recorded. There was a very minute peak of thorium oxide was observed. And this is a SCM. This is the thorium oxide, and you see that after the reduction, you see the nodular structure. It's a typical of this process. That is like if you take this matrix contain thorium oxide and you plug out the oxygen from that, you remove the oxygen from that and leave this type of metallic structure. So you only need unique properties of this reduction process. And as I told you that 96 hours was not sufficient for this complete reduction. So we gone for the another process of the electrocalciothermic reduction. Here the electrocalciothermic reduction, we have gone for the potential of calcium. That is, calcium is generated near the cathode and the calcium reduces the metal oxides. And what this is a potential static electrolysis. There constantly we will keep the cathode potential that is above the calcium deposition potential. And see the 13 hours is sufficient for the complete reduction of thorium oxide to thorium as evident from the X-ray. But you see that metallic that surface, it contains some black coating. Then black coating generally that is after some time that is when we increase the time from 12 hours to 15 hours or 16 hours, that coating was increased. So layer was increased, coating layer. Then finally we found out that is a thorium carbide. So with the usage of graphite will lead to the thorium carbide formation in this case. But there only electron is releasing. And because, why? Because it's here the thorium carbide formation is more, is here using the calcium oxide. This calcium oxide has the tendency to absorb the carbon dioxide which is liberated in the anode. That's why this calcium oxide will form calcium carbonate. This calcium carbonate will, that carbonate ion will reduce at the cathode and forms this type of carbide formation. So subsequently we didn't probe in this experiment, and finally after that nowadays we are using platinum also, but we have to bear the loss of platinum. And this is thorium nickel intermetallic compound preparation. And this preparation, why we have taken up this process is to go for the complete reduction of thorium oxide, because as I told you in the last slide, we could not achieve it. So we thought that we put the nickel, because thorium oxide reduction is one is high thermodynamic stability of thorium oxide. We could not reduce it to complete reduction. Another one is the conductivity of the thorium, because here the electron is important for the conducting that is electron is to pump to the cathode, and there it should ionize that thorium oxide. Therefore, the metal oxide conductivity also plays a very important role. So in this case, we have added the nickel oxide to increase the electrical conductivity. How it means that if you add this nickel oxide, from the Ellingham diagram, we can understand that nickel initially reduces. So nickel oxide reduces to nickel. That way it increases the conductivity. For that reason, we have gone for this intermetallic compound, and this intermetallic compounds found some applications in the superconductivity. So we could achieve this one. The studies are in progress. The SEM was given. It's a nodular, typical nodular structure. You can see, and we are yet to publish this results. And this is a zirconium ion intermetallic compound, and it has application in the hydrogen storage material at a high pressure. And but if you substitute this one into nickel, and we can go for the at least moderate pressure application. It's a equilibrium phase diagram. And this is the line, because this range is high. So we aimed for this intermetallic compound preparation, that are Fe2. And if you go for the arc melting from liquid to solid, this is a room temperature phase. And during arc melting, as cast metal, what some of the times we will encounter other impurities also. And we have to go for the annealing. Here I will show you the results, what are the things we have obtained. And this is the prior to this reduction, we have conducted the cyclic voltammetry. This is new kind. This we have to use the metallic cavity electrode. The metallic cavity electrode will be used for the recording the metal oxide CV. It's not very easy like electrolyte when we are recording the cyclic voltammetry. And this is the calcium reduction. This is from this one. This is I'm shown in the cathodic part. Nickel oxide is a reference electrode. This is the calcium deposition. And prior to calcium deposition, two reduction peaks were observed. That is C1 and C2 in the case of thorium oxide. And the iron oxide also, you see the two reductions, reduction peaks are observed. And this is the potential versus time graph and current versus techno. As I already discussed with the thorium, it's same typical graph. And here you see that there is a changes in the current profile. So it indicates that a lot of intermediate was formed, and XRD also we recorded. And this is the SEM diagram. You see the how the profile goes and what are the intermediate formed. Best initially, as we envisaged, that iron forms they easily reduce, and perovskite, this calcium zirconate also formed, and these are the various steps involved in this type of in this reduction step. And finally, we could get the pure intermetallic compound at 48 hours, and this is the reduction part. Initially, it forms for the calcium zirconate, and iron also forms. We cannot distinguish which is forming which time. Like that's we cannot say that sharply that iron is forming at this time and it's aiding for the calcium. All the processes are occurring at simultaneously, but roughly we are divided into the several sections. Start with the calcium zirconate and the ZrFe2. Starts even at 4 hours, and final pure compound at 48 hours. And the uranium reduction, and this is already started process. This is a bulk process. We are envisaged in one of the laboratory. We constructed a laboratory, commissioned the laboratory also. This is a 200 gram scale. It's a thermic reduction. You can see that already this process was established in 2014 or something. And this is the new laboratory we have converted for this bulk production of uranium oxide using electrolithium thermic reduction. So here the various equipments installed, everything as shown here. And I'm not having any time to discuss in depth of this one. Okay, after commissioning, after this showing this experiment, I can show you. And this is one of the uranium niobium alloy also we have recently prepared. And we were aimed for the uranium 9% niobium alloy, and we could achieve reasonably. But all are in 1 pellet scale. And apart from metal, we are aiming for lithium niobate also. LiNdO2 is a cathode material for the lithium ion battery. That also we can prefer from this route. This is electrothermic reduction. From the starting material is Nb2O5, and this type of intercalation in the reaction is possible in this melt. So lithium niobate also we prepared. And final conclusion is challenges mentioned. Stringent condition for the preparation of moisture-free molten salt is mandatory in this method. And usage of graphite is economical, but product contamination, as I mentioned in the thorium, is also envisaged, and it's decrease the charge in it. So alternate anodes also continuously being probed, and further investigation is needed for the bulk production. This method is more suitable for the type of alloys because 2 metal oxide we can take instead of aiming for the 1, and 2 metal or 3 metals oxide we can take and form an alloy. And even high entropy alloy is also possible in this method. And one more good thing is the product retains the near net shape of the feedstock. And acknowledge to my laboratory members, I was initially working in the solvent extraction and ion exchange. Later I moved to this new topic, that is direct oxide electrochemical reaction. We have a few members like Sanil, Anteshwar, Sakila, Arun Kumar, and Mudivli Jayal. And thank you. Thank you.
Now open for discussion. So if you have any questions, feel free to ask.
There is no supporting impedance. Like whatever oxide ion comes, it forms calcium oxide. And calcium oxide will goes to the anode and liberates oxygen.
No, I mean, when you form your oxide during the process, like lithium metal oxide, how do you control oxygen?
Actually, we want only lithium metal in this direction. And cathode, only electrolithium lithium is generated at the cathode. And we need the decomposition of the electrolyte. For that, we are adding oxides. And the fluoride is the base electrolyte. And in that, we have added used to find.
So whatever oxides you add,
yes, that only will decompose. We used to add 1 weight %.
So, but I mean, that's what whether it forms a stoichiometry because oxygen will be good because the cathode side you have oxygen emission of.
Yeah. So sometimes initially some loss of chlorine also may be observed, and we don't know about the electrolyte chemistry. As you asked that there is always a charge imbalance will be there. Something may compensate. Sometimes even metal oxide may dissolve. That is also observed if you keep it for a long time. do you part your
Yes,
water
argon.
solved with argon?
Yes, yes, continuous argon.
So there is an oxygen pattern cycle that takes the oxygen. 3%. Any question?
Same, sir. So, thanks you.
Thank you. So if there are no more questions, then please join me in thanking Dr. Kumarasan for his wonderful. On behalf of the organizing committee, it was a pleasure to hand over this now. We give it the same thing. Thank you. We break for tea now and we'll come back at 6. 6. Yeah. बॉक्स बना के भी लिखे चल समझ
Welcome back. This is exactly 6 o'clock. This is record. We are starting on time. So this is the last session, last oral session of today, and this is going to be chaired by Dr. Jyotiranath Behera, who is an associate professor at the Smith SCS. He has obtained his PhD in 2007 from Indian Institute of Science, Bangalore, India, and then he went for postdoctoral associate in 2007, and he stayed there 2 years at the University of California, Berkeley, and then at the Lawrence Berkeley National Laboratory. He has done another postdoctoral associateship in 2009 to 2010, that is in State University of New York, Albany. His specialization is inorganic and material chemistry. Particularly, he is interested in porous magnetic materials, supercapacitors for layered composite materials, sustainable energy materials, electrocatalysts for water splitting, organic, inorganic, hybrid materials. And he has more than 70 publications in reputed peer journals. With this short introduction, may I now invite Dr. Jyotiranath Behera to take over and chair this session. Thank you.
Hello, good evening. I would like to thank our chairman, Dr. Mena, for giving me this opportunity to chair this session. So we have two speakers in this session. Both of them are my colleagues here in NICER. The first speaker is Dr. Nagendra Sarma. Just to a brief introduction about Dr. Sarma. He did a master degree from University of Delhi, and then his PhD from NCL Pune, followed by 3 years of postdoc at the University of Utah, Salt Lake City, USA. And then he joined NICER at the year 2012, and now he's currently associate professor in the department. His main research area is the chemical biologist, mostly work on amino acid and nucleic acid area. With this short introduction, I would invite Dr. Sarma to deliver his lecture, and it will take maximum 25 minutes. Good evening to all of you, and thank you, JNB, and thank you to organizer, NICER organizer plus HBNI organizer for giving opportunity to show some whatever we have done like couple of years. Title you can see, parenting of ignored molecules and not ignored natural molecules and propylon. Many people they have not heard. The students are not there, especially for first and second year. They should realize what's propylon. NS is what? Non-radioactive, non-predictable elements. This is the parenting the natural molecules, how the DAE parenting to HBNI, and they are parenting to NICER. So similarly, I'm trying to parent the one small molecules and ignore. After a few slides, we'll come to know is it really ignored or just for fun. Propylon is a beautiful molecule, if I say. Still, why the beautiful molecules will be ignored? The non-benzyl aromatic compounds. It's a chromophore. It's also fluorophore, although fluorescence intensity is weak, quantum units are weak. Native metal chelators. Natural products are metal chelating. You can imagine how it's so important. How the HBN will be happy to, or BARC will be happy if natural products are chelating the metals. Okay. And then also a lot of natural products are there. Synthesized colchicine is already in market as anti-cancer drugs. Tubulin. This recently case in Nicolo group has synthesized using the tropolons, photosynthesis. And this nothing but something is there, monomer of tropolons. Tohoku University is there, but not well explored. So many properties are there. Everything is there, but why still is not explored in literature? Why is it so? We'll go to the PubMed.
Even now, many students trying to Googling. To type the benzene aromatic compound and type the propylon, you will find the benzene aromatic compound is a 50,000 literature and propylon will get only the 1,000. What is the ratio? If this ratio database is there, definitely propylon is a ignore molecules. If these ignore molecules are there in 2012, many literature was 70-year mystery has been solved in the chemical chemistry, and that mystery was the biosynthesis of propylon. After 70 years, somebody solved the problem of the biosynthesis. And that article, that catching article attracted me to do something on propylon. Now I'm working what is he gave the introduction in nucleic acid chemistry, peptide chemistry is there. So it's, you can see the peptides almost like no fluorophore, just tryptophan is so big fluorescence, all benzenoate, DNA, all the benzenoate. So I was excited what will happen if we introduce the propylon in between. The biomolecules will be the fluorescent. The biomolecules will be the metal chelator. The biomolecules will behave like the propylon natural product. Biomolecules behave as like drug as a propylon molecules. Biomolecules behave like the anti-cancer drugs. All these things, these questions was coming in my mind. And then we started this project. Then in my lab, we started from propylon. It's not a stock exchange graph. It's our laboratory graph. We started from propylon and then we reach up to this stage. I'm happy to see the graph and always compare how the everyday sometimes the stock exchange graph is writing. So propylon, what we have done in propylon? First we synthesize amino acid, alpha amino acids, and then we synthesize the beta amino acid, and then we synthesize, also take the any peptides, put it and propylon in inside, conformation will change. So change the properties of peptide by introducing one molecule. Then we synthesize the cinnamic acid. You know how much cinnamic acid is important. So non-benzenoate cinnamic acid analogs. We synthesize the, like we are moving toward the drugs kind of thing. Antibiotic properties are there, quorum sensing inhibitors. Then we synthesize, we started from there 2012, finally we achieved the chiral amino acid having the tropolons. Then finally we also synthesize one molecule which bind with the DNA and is an opportunity to make the drugs. We didn't stop here. Due to our expertise, we synthesize the tropolon in a DNA. We synthesize all the phosphodite. Each and every phosphodite takes to 10 to 15 steps to synthesis. So we synthesize all the phosphodite and then incorporate it in DNA and we study all the physical properties and the binding abilities. Sorry. And then we also synthesize. Then I said this tropolons is a unique properties is there. If you go the body pie, this molecule is not fluorescent, but it's very famous molecule. Nobody will believe. But after going from here, do the Googling, you'll find it. But if you give the substituents, 1,000 publications are there. People are using left and right. This was another inspiring for me, and we synthesize all the body pi analogs from the tropolon in the smallest, simplest way. And then the first one was the amino one, then we functional one. If you synthesize, what is the use? If you not conjugate, because body pi dye have to conjugate with the biomolecules. And then we synthesize, if it is there, how can we go inside the cell and imaging all these things? And then again, we synthesize, if you body pi analogs, you want to make peptide, is a fluorescent, why not we can try this one? I'll check a few minutes to start from the very small journey, but it's good for the master student if these types are there. So if you wanted to synthesize a rationally designed to amino acid having the any unnatural moiety, any unnatural scaffold, or natural also. So then propylon has a beautiful property for hydrogen bonding. Why not this molecule can be introduced in the peptide and turn the property of the natural peptide structure, foldamer structure, secondary structure. Enzyme is going the far away, but at least we can reach up to the peptide levels. Then what we did, we rationally designed, but problem is that if we design these molecules, it will never like that, it's always perpendicular. So this idea is failed. The simplest way we design the molecules and synthesize this one backbone, attach the end tropolation, and then make the amino acid. After making the amino acid, the results was encouraging. We made the peptides. There was no issue. We introduced the peptide. Our first goal is there, this carbonyl group is involved in a hydrogen bonding or not. Then only we can say we can tune the structure of the peptide. First, I have to prove the propanol carbonyl is involved in hydrogen bonding or not. Then we did all the Noji-Cozy experiment, all these things, DMSO titration, and finally we proved that the carbonyl compound is this side and showing the hydrogen bonding. All data is there, you can see this paper. So finally we successfully proved that, and this was encouraging. We are going one step ahead. Then why not this one? We can make the homooligomer. So if one peptides are there, polyphenylalanine, we can make the more peptide. So this was every time we do something, encouragement will come. Then we started doing the solid phase synthesis. So remove the box, we'll get the amino acid. I never got the amino acid. I always get this compound. It's a major product. It's a fluorescent, but I was not interested. Then I removed the ester, got the acid. It is very fine. Attached the MBX. There was no issue. When I removed the TFA, last 10-year experience, I've never seen this like this reaction will show negative Kaiser test. And nobody will believe here in audience. Then it was failed. Then again finally we synthesize, just try to understand solution phase, but it's a trace amount. You cannot publish, you cannot excel. Just for satisfaction, you got something. Then you think about that after doing all these things, so a nice idea, excellent propellant, and this stage will come, a student situation will be like that. And not student situation, our situation also, but we adopted like every day we get the email, your paper has been rejected. So we are adopted all these things, so don't worry. But a student situation will be there. That time you have to parenting. That's why I was said. Not parenting the molecules, parenting the students also. Don't worry, encourage him. Let's see what's happening. Then amide bond was cleared in 20%, and we never got the amide bond. Why is it so? If tropola Bock is there, 20% TFA Bock will go and get the amine attached to the amide. Why the amide will not form? Nobody will believe here in audience. Then we treated with the 20%, we found the amide bond is breaking. And it was not for my students shocking, for me it was also. And then we have read the literature, amide bond is very much stable, it cannot break. And then even this PNA peptide, I have a lot of experience of 5 to 6 years on making the PNA analogs. And even tertiary amide bond never hydrolyzed, even in neat TFA. Forget about 20%. Then we have derived the, let's see for students' purpose, if amide bond is there, this will go there. And you see, this tautomer is well explained. For time being, just think about the reverse way. If this hydrogen is going, then what will happen? Not this nitrogen. If this is going, then ketone will form and amide bond will cleave. Just for time being, think about that. Let's say I'm telling the wrong thing. Then what happened? You go through the literature. I also went through there. The student also found, and then lot of amide bonds are cleavable. But not lot of means I'm comparing for the ratio 1:10 only. Only 15 to 16 amide bond is available in literature. Is a cleavable, non-enzymatic way. Okay, so this amide one very twisted amide, amide, all you see the ionic, and this one also we have synthesized. That was NS amide. It is hydrolyzable under 20% TFA. Then 20% TFA, they will be happy. What is the concentration? 20%, 30%, 5%, or vinegar itself has acetic acid. Then we tested, and then we found that the amide bond is very much stable with acetic acid. Sodium hydroxide, 2 equivalent sodium hydroxide, nothing is happening to amide bond, is very much stable. Can you imagine? And then only 5% TFA is enough. Whoever is doing the peptide chemistry and Bock chemistry, Bock is not cleaving, but amide bond is cleaving. Take home message is there. It is possible. And we have done it. If it is so, then we made several peptides and proved the idea amide bond was very much cleavable under the 5% TFA. Why not we can use as a protecting group? So even you want to use a Bock as a protecting group, even you can use as a this reagent also protecting group. And this is the 4 students again. So even you see the evidence is there, this amide bond is cleaving, Bock mass is still is there. It's not, I was just saying. Even you can go through the paper and find the details. Bock is still intact. This amide bond is intact. Only this amide bond is cleaving. And this was with all the amide bonds. And in the mechanism wise, this hydrogen is this one protons, alpha hydrogen involved. So I was talking about if your tautomer will go for this direction, your amide bond will be cleavable. And then the amide bond will be cleavable. Amide bond is hydrolyzed. If I not put the what is called nucleophilic solvent, what will happen? Right now I'm putting the methanol, acetic acid, and it was getting hydrolyzed. Suppose I'm not adding any nucleophilic solvent, no water, no methanol, no what, or what's called ethanol. Then we characterize the mass, we got the cyclolactone formation. The next curiosity is the how it forming. Then we synthesize not only with the Bob, other side chain, and the result was consistent. And this, in all the cases, believe me or not, we have characterized by the carbon 13. It's unique carbon 13, this carbon is there, it's confirmed, cyclolactone formation is there. Now, so what was the mechanism? Alpha proton was there, we did also TFAD and confirm it. Then this hydrogen was getting in tautomer, not the amide one, because this is getting protonated. And then ketene formation was there, and then lactone on this one. Still, sometimes I fail to convince my colleagues also, ketene formation is not there, but I am able to explain the referee. And referee was happy to my explanation and all my supporting data. Then if ketene is there, assume for time being ketene is there, can you trap it? This literature is there published in this. So just do the simple experiment. Sometimes referees suggest very nice experiment. You are claiming big thing, the ketene formation is there. Why not you can trap that ketene? And they gave the suggestion, we did the experiment and successfully we wanted these molecules and got the mass peak was there, very happy. Ketene formation, we can trap the ketene. Then I was thinking, if ketene is there, why this lactam cannot use for making the drugs? They start making the large scale. Sometimes mass data will fail. What happened? This is supposed to get this one, but we got the crystal structure this one. Because mass are same. One time I convinced the referee, lactam was forming, but when we were doing the larger scale, it was not lactam, next step is going. So it was not ignore molecules, you're doing one more extra work. Whatever you're thinking is going one ahead. So what happened? Then we synthesized the various lactam. Beautiful things in molecule. There was no issue in synthesis. You can synthesize as much as possible. 30, 40 compound we synthesized it and we found the mechanism if ketene is forming, and then again because this imine will form, lactone will form, again this again is the amide bond is there, again it will cleave and rearrange. So CATC complex formation is there, and then if any organic chemistry will get the fluorescent, sometimes ignore it, but sometimes indicators. Okay, so we use this, all the molecules are the fluorescent and the quantum is range up to the highest around the 14, 12 to 30%. With the different side chain, you can use for the bioactivity, all these things. And these molecules we have tested for the drugs, all these things. Today I'm not going to discuss. I move to the now, if alpha amino acid is cleavable, think about the beta amino acid, what will happen? So we synthesize the beta amino acid in this way, just put the hydrazine and beta amino acid, and unfortunately, this amide bond was also cleavable. But not 5% TFA, it was cleavable under 20% TFA. And then sometimes crystal structure fails. What's the crystal structure will help your failures. You are thinking something else. Students doing the mistake, they are doing the column, not getting compound, he's wasting the time. But crystal structure will tell, no, your thought is wrong. He's trying, but he's not getting. And getting something is not able to characterize. Okay, so crystal structure supported well, like this amide bond was also cleavable. So one thing will start, automatically another thing will happen. Then this amide bond was cleavable. Then we also thought now, okay, let's see, we'll attach the one propylon and tune the peptide structure. So this was literature that the Kent groups extensively they are doing the end twisted structure peptide, not up. They're doing only end related peptide. And I started non-benzenoid peptide. So if these groups are doing, why not introduce the propylon? Let's see how the structure will change. Then we introduced the propylons in terminal, and then we were successfully tune the structure of the peptide. Without propylon is the inactive peptide, there's no CD signature. By introducing them, it's showing the characteristic CD structure, the beta turn kind of thing. So propylon has ability to turn the structure of the peptide just by introducing the one unit at N terminal. Now only this is the further supporting, like we got the crystal structure, collected all the phi psi angle, Ramchandran plot, students are aware is fine. If not aware, you see this one, beta sits formation is there, alpha in this region, and alpha on this side is there for just for representation. And our molecules are showing the 4-8 is here, so beta sheet kind of thing, 4D is there. See, they're just changing the 4D and the 4E. Just changing one unit, introduce one unit, your structure has been changed. So what I was talking about, the tropolone unit, introduce the tropolone, will tune the structure of the peptide. Successfully, so far I have explained you, tropolone has been changed the structure of native peptide and just only diprotide. Then I was excited, why not? We can make the chiral amino acid. And then we synthesize by loss, what's called Hoffman reaction. You can make this diamine, walk protected tropolation, do this one, simple steps. You got the chiral structure, you got the crystal structure, very happy amino acid is formed. Once amino acid is formed, what is the great thing? Many amino acids are there. 20 amino acids there, 30 amino acids there, one more amino acid. Are you able to make the peptide? Already you have tested with the peptide bond formation with the propolone is a failure. Putting your risk on a student. You are playing there with their 5 years career. Let's see. So he is a student sometimes synthesize, and he was so dedicated. He was sometimes a student they're not honest. Not honest in sense they're smart. Any peptide bonds you are doing the chiral amino acid, don't forget to add the HOBT. If you're not forgetting the adding the HOBT, that means you are not making the amide bond. You are making the amide bond by having the racemic mixture. HOBT always minimize the racemization. But a student sir to extra डालते चलो add करते HOBT will get the product. What's wrong? I did the peptide only. Unfortunately, or I can say fortunately, when he synthesized the peptide, he got this molecule. With the HOBT, then I asked him why you done this work. No sir, this time I do with the HOBT, and he got the peptide. Very happy, amide bond will form. But what will happen? This bond is formed without HOBT. That means you are brave. See, everybody is making something. I don't know why. Whenever I'm doing something, destruction is happening. So now we are breaking the CN bond, and not only CN bond, double carbon double bonds. So we propose this mechanism, and then we propose the mechanism. This one everybody knows. Activation of this acid. After activation, propolone start playing the additional role. X factor, and then propolone will play the roles and make this ester, and this ester is for the side product urea. Sometimes side products urea has reacted with this acid and got this one, the other acid, and then amine has been released by the cleaving this one. So now we got this one. So what we are doing, we are breaking this is the asymmetric EDC. We are breaking this carbon double bond. Nobody will believe, but I have crystal structure data, and then sometimes you have to convince the referee. So if crystal is there, your job is. And then if you are doing the HOBT, peptide was formed, students are happy, my project is running fine, why not I can make more peptide, and the student, he made all the peptides and got the CD signature, very nice. Just by changing the residue, you can see the alpha helix, beta turns, so nice. Just put one molecule, chiral amino acid, you can play with the even dipeptide, you can play how the secondary structure is changing. And now next more to cinnamic acid. Cinnamic acids are their natural products. So because again, if cinnamic acid is there, why not we make the non-benzenoid cinnamic acid? So we made the cinnamic acid by using the pH activation because everybody is fashion. Your lab is not doing pH activation, that means you're not organic chemistry. This kind of trends are set up. So you have to keep it your busy, and then you have to do something, right? But I have to do something what is inspired from the nature. Don't do unnecessary, right? So cinnamic acid inspired me to make the non-benzenoid cinnamic acid. We'll see the property later. So we synthesized the cinnamic acid. We wanted to make cyclic peptide. It's under progress, and we got with the different amino acids. What's good? Different substituent. We got all around 30 to 46 examples are there. And now, if you got our goal is there again. I mean, cinnamic acid will make a pseudopeptide, and we have attached the peptide and the pseudopeptide. This is the precursor of or a scaffold of making the beta hairpin peptides. Here we can make n number of hairpin peptides. These building blocks are there. So successfully made this one. And now I'll move to the DNA part. I'll skip because I'm just skipping the peptides one. So we synthesize that. Let's see, 5 minutes are there. So introduce in DNA and synthesis part, you can see also 10 to 15 step is synthesized, nucleobase synthesis incorporated in DNA, characterized and did the melting, all this thing. So this DNA is able to incorporate in DNA or not. It's confirmed for forming a duplex. Additional part is there, it shows the pH dependent fluorescence. Single strand fluorescence is X, when form the duplex 10 times more. And it's straight. So now just introducing the one tropolone unit in DNA, you are enhancing the fluorescence of duplex structure. Then we synthesize, if this nucleoside is there, why not insert in a cells? Why not you can do the enzymatic synthesis? Then you have to make the triphosphate. Making triphosphate itself is a climbing on mountain, right? We synthesize, and then successfully synthesized, and we studied the showing the 1 minute going inside cell and showing all the activity. Okay, I'll just skip now. So synthesize one compound is showing also quorum sensing inhibiting, and very nice. We synthesize 26 compound, and few of them they are not showing. Okay. Yes, this is very important. If I miss one slide, I don't mind. Without them, we cannot do anything. They are actually you have ornaments. If they are not there, just empty bench, even lakhs or lakhs, what's called DA is giving the no meaning. They are working day and nights. And yeah, always salute them. Although sometimes we be like not happy, but without their contribution. And finally, thank you. In evening, you were here. I'm so happy.
Okay, thank you, Dr. Sharma. And we can have quick one question.
Yeah. I'll tell answer in another way. Propellant quantum is 0.005. Okay, in water. Single strand 0.1 and duplex is 2. So now you compare with the propellant. Yeah.
Okay, so if there are no more questions, let me thanks Dr. Dhanmi in thanking Dr. Sharma for his very informative and excellent talk. Thank you.
Whenever you have time, read this article.
And on behalf of the organizing committee, it's my pleasure to present a amendment for the token of appreciation to Dr. Sharma. So we'll move to the last talk this today's session. It's given by Dr. Vidro Bhag. Dr. Bhag obtained his MSc from Indian Institute of Technology, IIT Guwahati in 2007. And then he moved to University of Saskatchewan in Canada to obtain his PhD with a gold medal. Then he has a couple of postdoctoral experience. Past 2 years he spent in University of Toronto, then followed by another 2 years of postdoc at University of Amsterdam, Netherlands, and finally 1 more year postdoctoral experience at University of Bern, Switzerland. So after 5 years of postdoc, he joined in ICEP in 2017, and he's currently working as a leader app. Its research area mostly on organometric chemistry, catalysis, and green chemistry. So with this, I invite Dr. Bhag, and he's one of the young faculty in our department. So Dr. Bhag will take 2 minutes.
Thanks, Viraji, for your kind intro. Good evening, everybody. It's a pleasure to be here on this platform and presenting our research work. We started our journey a few years back, probably end of 2018, and we started exploring 2 basic reactions, catalytic oxidation and reduction. So we have focused on 2 reduction protocols, hydroxylations and transfer hydrogenation, which are easy alternative to classical hydrogenation. In addition to that, we are also focused on catalytic oxidation of different organic substrates, and we have been using base metal catalyst for both oxidation and reduction. Today, I am going to talk about base metal, copper and iron catalyzed aerobic and peroxidative oxidation of primary alcohol to sustainable and selective oxidation products. The oxidations of alcohol to the corresponding carbonyl compound or the complete oxidation to acid are among the central reactions in organic chemistry and have attracted significant attention due to their relevance in industrial fields and for the synthesis of new materials. And it has continued to attract significant attention developing new catalysts, co-catalysts, and oxidants. Let's see some of the common oxidants. Common oxidant includes small organic molecule-based reagents such as hypervalent iodine reagents and activated dimethyl sulfoxide. Here you can find few examples such as Diaz-Martin pyridinine and 2-iodobenzoic benzoic acid. There is activated hypervalent iodine reagent and corn oxidant, corking oxidant, mofate oxidant, ferric-chlorine oxidant. They belongs to the activated dimethyl sulfoxide group. Some of them are moisture sensitive and expensive. Another important one is NLE oxidation, which is mediated by TEMPO or related nitroxide reactions. Another important class of common oxidants are metal-based, mostly chromium-based oxidants or ruthenium-based oxidants. Common chromium-based oxidants are Jones reagent, Collins reagent, pyridinium chlorochromate, pyridinium dichromate, etc. Important ruthenium-based oxidants are ruthenium tetroxide, perruthenate, ruthenate ion, etc. And other important metal-based oxidant includes barium permanganate, manganese dioxide, silver carbonate, etc. So despite the formations of large amount of undesirable waste, these oxidants are still in components. Therefore, there is a need of oxidants which are environmentally friendly and sustainable. The recent trend in sustainable development led to two types of oxidants, which are aerobic oxidation and peroxidative oxidation. Aerobic oxidation utilizes air as the cheapest, most sustainable and green oxidant, and the byproducts, water and H2O, they are also green. However, pressurized oxygen cylinders are often used instead of air, and several transition metal catalysts have been developed for this purpose. The transition metal catalysts, oxidations of aerobic oxidations of alcohol, are dominated by copper catalysts. Here are some examples. Stoll group, they are the major player in the field of oxidation. This example is from Stoll group, where they utilize this copper 1 complex as catalyst, TEMPO as co-catalyst, NMI as external base, and pressurized oxygen cylinder as oxidant. Here is another example of copper catalyst. There are some important iron catalysts as well. So mostly iron 3 salts have been used in presence of co-oxidants such as TEMPO, HBNO, TMNO, etc. This brings us to the selective oxidations of alcohol. The selective oxidations of secondary alcohol to ketone is relatively easy, as the further oxidation is difficult because it involves the oxidative cleavage of the CTO. In contrast, the selective oxidations of primary alcohol to aldehyde is difficult, as aldehydes are reactive and oxidation continues to give the acid. In next few slides, I will show you the selective oxidation of a biomass-derived alcohol to an important aldehyde. The utilization of biomass for the production of value-added chemicals is important for sustainable development, and it has become a strong trend in research. The aerobic oxidations of monomeric phenolic compound to fine chemicals has attracted significant attention, particularly the aerobic oxidations of vanillyl alcohol to vanillin, which is an important aroma molecule with wide application in industry, has gained significant momentum. However, this oxidation is often not selective, and often you see a lot of byproducts, particularly vanillic acid, which is the overoxidation product, is observed in most of the cases. So I was showing the development of a copper catalyst which selectively oxidizes the phenylyl alcohol to phenyl using air as sustainable oxidant. Let's start with the ligand synthesis. We thought of using a tridentate tridentate ligand with amine arm. So the condensation reactions of this amine with 2-pyridine carboxyldehyde under reflux resulted in the formation of this heat-based imine L1 with excellent yield, and the standard reductions with sodium borohydride gave this amine NNS ligand L2. Thereafter, we focused on the metallation. The facile coordination of this ligand L1, the imine ligand, and the amine ligand L2 with copper to perchlorate resulted in the formations of two homoleptic complexes, 1A and 1B. In 1A, you can see this imine ligand is coordinated to meridonial fashion. However, in 1B, this amine ligand is coordinated to the metal in facial arrangement. Thereafter, both of the ligands were coordinated with copper to chloride. So this imine ligand was reacted with copper to dichloride, resulted in the formation of a chloride-rich dinuclear complex with non-coordinated thiether. In contrast, the very same reaction of copper 2 chloride with the amine ligand resulted in the formation of a mononuclear complex with the coordinated thiether. So here, these thiether are with amylibi, it can be on and off, and there are some literature evidences there. And all these copper complexes are characterized by standard techniques, including single crystal X-ray. Thereafter, we focused on the utilizations of these complexes or the aerobic oxidations of phenyl alcohol. So we use 5 mole% copper loading in presence of TEMPO, and we use acetonitrile as solvent. In most of the cases, people use acetonitrile as solvent for the aerobic oxidations of substituted phenyl alcohol. And we observed base catalytic activity with the mononuclear complex 2B. Thereafter, we wanted to study the performance of the catalyst in various solvents, because the solvent might have some effect on the outcome of the reaction. So here we have selected various different solvents with different dielectric constants, different polarity, as well as different coordination ability towards the transition. We have seen a nice trend of decreasing conversion of phenyl alcohol to phenylene with decreasing polarity of the solvent, with couple of exceptions like ACM and PHF, where the trend didn't follow properly. However, if we consider the coordination ability of the solvent, the trend of decreasing conversions of phenyl alcohol to phenylene, it was perfect with the decreasing coordination ability of the solvent. So in homogeneous catalysis, solvent often plays a crucial role. Sometimes it displays a coordination site, a ligand site, and then the substrate binding occurs via the displacement of this solvent. So here we have obtained good conversion to phenylene in solvents with high coordination ability, and very poor conversion in solvents with low to no coordination ability of solvent. And water, ethanol, methanol, acetonitrile are among the base solvents. And we see water was the base, and it's a green solvent. So here, this is the optimization table. I am not going to discuss it, all the inputs. So first, we wanted to see the conversion of this phenyl alcohol to phenylene in green solvent water. So please look at the first four inputs. So using 5 mole% catalyst and 20 mole% co-catalyst, in 3 hours, we obtained roughly 34% conversion in water. We doubled the time to 6 hours, the conversion increased to only 40%. We increased the time to 9 and 12 hours, there was no significant change in the conversion. So in water, we couldn't achieve the full conversion of vanillyl alcohol to vanillin. And we observed tar formation. That means the decomposition of product. And this is the indications of solubility. So what we did, we used a mixture of water and organic solvent to overcome the solubility. And we used different solvent mixture. And finally, we found out that 1-to-1 ratio of ethanol water, methanol water, acetone water among the pair. And here are a couple of optimized conditions. So complete conversions of vanillyl alcohol to vanillin was observed in roughly 20 to 24 hours by using 3 mole percent catalyst, 10 mole percent tempo in 1-to-1 acetone water or ethanol. And we analyzed these optimized conditions by using M21 green matrix. Thereafter, we proposed the catalytic cycle based on several experiments such as EPR analysis, mass analysis, and other experiments. So here is 5 coordinated pre-catalyst story, water coordinates to form this, it is A. In the first step, you see the coordinations of the water with the P coordinations of the 5 ether arm. In the next step, vanillyl alcohol, it takes part in the reactants and forms HSP, where there is a weak non-covalent interactions of this alcoholic proton with this 5 ether arm, followed by the formations of copper to alkoxy species with protonated 5 ether arm. Then tempo radical takes part in the reaction, form this species T, and this beta hydrogen transfer from this coordinated alkoxy species takes place to form this tempo H compound with the formations of compounds E, copper 1 species with coordinated carbonyl compound. And finally, oxygen reacts to release the carbonyl product with the formation of oxidized compound copper 2. So this oxidation happens by transferring one electron from copper to oxygen, and it forms copper 2, O2 radical minus species. And finally, tempo H takes part, release tempo radical H2O2, and the starting capacity. And in conclusion, we have developed air-stable copper catalyst for the selective oxidations of vanillyl alcohol to vanillin and important aroma molecules with wide industrial applications. The use of copper catalyst was advantageous as it is earth abundant in earth crust as well as the seawater and sheep. And the selective oxidation is also advantageous as it reduces the waste of valuable feedstock. And instead of using some peroxide or pressurized air, we use sustainable oxidant air. And the role of solvent was very important, particularly the coordination ability and the polarity of the solvent. And we saw the role of solvent mechanism. Then we move to the next part of the reaction, next part of the talk. So as I previously mentioned, the selective oxidations of primary alcohol to aldehyde is difficult, as aldehydes are reactive and the oxidation continues with this acid. So in next few slides, I will show you an air-stable iron catalyst which selectively oxidizes primary alcohol to aldehyde, and in a different reaction media, the same catalyst selectively oxidizes this primary alcohol to aldehyde. So already I have discussed aerobic oxidation. So I said there are two sustainable oxidation protocols. One is aerobic oxidation and one is peroxidative oxidation. I have talked about the aerobic oxidation, the copper catalyzed oxidation of vanillyl alcohol to vanillin. And in next few slides, I'm going to talk about the peroxidative oxidation. So peroxidative oxidation utilizes H2O2 or PDHP as oxidant, and the byproducts tert-butanol and H2O they are green. So there are different transition methods have been developed for this purpose. But again, copper is the major player in this field. Here you can see some examples of copper catalyst. Now I'll show two interesting examples of iron catalyst. So the first iron catalyst selectively oxidize a secondary alcohol to ketone. And the next one, it selectively oxidizes the primary alcohol to acid. Both use H2O as the oxide. In next few slides, I will show you our iron catalyst, which selectively oxidize the primary alcohol to aldehyde and acid selectively in different mediums. So let's start with the ligand synthesis. So again, this simple condensation reaction of this quinidine to carboxyaldehyde with the morpholine under reflux resulted in the formation of cycloheximine. Exilative, thereafter the standard reduction resulted in the formation of this amine in an glycan tubule. Then we thought of the metallation. Here we used iron as it is cheap, non-toxic, and not abundant metal. In fact, the most abundant transition metal and the second most abundant metal on the earth. So the facile coordinations of this NNN ligand L1 with cheap iron precursor iron chloride tetrahydride at room temperature resulted in the formation of a chloride-rich dinuclear species. We characterize it by different techniques, including single crystal texture analysis, which reveals the identity. The iron has a distorted octahedral geometry. And then we thought of using the catalytic activity of this complex. We used it for the peroxidative oxidation of primary alcohol. So our objective was to oxidize challenging unactivated alcohol, where the oxidations of unactivated aliphatic alcohol is difficult, but the oxidations of activated alcohol such as allylic and benzylic alcohol are relatively easy. So we started with the easy one, and we used complex 1 for the peroxidative oxidations of benzyl alcohol. And here is the reaction optimization. We used 2 equivalent of TBHT as oxidant. And we thought of using neat conditions because in most of the cases, solvent produce most of the waste in chemical transformation. So we used different catalyst loading of complex 1. We are not going to discuss it in detail. This is the optimized problem. So in roughly 1 hour at room temperature, we obtain complete and selective oxidations of benzyl alcohol to benzaldehyde using 0.05 mole percent of catalyst load. So this complex is a very good catalyst. It shows good efficiency with rough turnover number of 2000 per hour. This catalytic protocol, optimized position, was applied to the peroxidative oxidation of unactivated primary alcohol in hexanol, and it worked well. Then we expanded the substrate scope, and here you can see a few unactivated alcohol, allylic alcohol, and a fast various benzyl alcohol with a wide range of substituents, electron donating and withdrawing, have been selectively and successfully converted to the aldehyde, corresponding aldehyde input to activity. Thereafter, we thought of using solvent. As I said before, in catalytic reaction, often the role of solvent is ignored. In previous case, we showed the role of solvent, particularly the solvent polarity and coordination. In this project, we also thought about the role of solvent, and it might give different outcome of the case. So here we selected 4 different solvents with a wide range of polarity. So here is the dielectric constant. So we performed these peroxidative oxidations of benzyl alcohol using 2 equivalent of DBHP using 0.1 mole percent of catalyst at room temperature, roughly 30. So in DCM, we observed only 15% conversion of benzyl alcohol to benzaldehyde. If we switch from DCM to acetone, we saw the conversion increase to roughly 35%, but there was no benzoic acid. If we move to acetonitrile, we saw both benzoic acid and benzaldehyde. We use water, which is highly polar. In half an hour, it's a complete conversion of this benzyl alcohol to a good amount of benzoic acid, a small amount of benzene. So we obtained different results in different solvents with different colors. So we thought of using deep eutectic solvent with high polarity. And I am not going to talk about this optimized reaction condition. So here we use deep eutectic solvent as reaction media, and this is our base condition. So at room temperature in roughly 1 hour, we selectively convert this benzyl alcohol to benzoic acid with 0.001 more percent catalyst. So the turnover number is 100,000 per hour. So here we use this optimized condition of the peroxidative oxidation of unactivated primary alcohol in ethanol, and it worked very well. And then we extended this catalytic protocol of this substrate spinning, and various different substrates were selectively oxidized to the corresponding acid in the plate. So we proposed a mechanism based on some experimental evidence that still we need to prove a lot. So the first step involves the reactions of this iron 2 catalyst with TDHP to form this iron 3 hydroxide species and tert-butoxide radical. Thereafter, this iron 3 hydroxide species again reacts with TDHP to form this iron 3 peroxide species. There are two possible paths, path A and path B. Path A involves the reaction of the tert-butoxide radical with this alcohol to form this oxygen center or carbon center radical, which further reacts with iron 3 peroxide species to form this desired aldehyde and regenerates the iron 2 catalyst. Path B involves the formation of iron 4 oxo species from iron 3 peroxide species, and then the tert-butoxide radical reacts with the alcohol to form O or C-centered radical, and finally this O or C-centered radical reacts with the iron 4 oxo species to form the desired aldehyde with the regeneration of iron hydroxide. And now I am going to conclude on this project. So we have developed a stable iron catalyst for the selective oxidation of primary alcohol. So in neat condition, the catalyst shows the selective oxidation for primary alcohol to aldehyde, and in highly polar deep eutectic solvent, the oxidation is selective to acid. So this is the interesting examples of reaction media induced chemodivergent reactivity. So various different kind of alcohols such as activated benzyl alcohol or allylic alcohol or unactivated aliphatic alcohol or selectively oxidized either to aldehyde or acid material. And using iron is always beneficial, and it is earth abundant and cheap and non-toxic. And we use the catalyst, we recycle it several times without the loss of significant loss of catalytic activity. And the reaction media was also recycled several times. The substrate scope needs to be expanded a little bit more, and the catalytic protocol will be further applied to the oxidation of secondary. With this, I want to thank my students and postdocs. So the first project, catalytic copper catalyzed oxidation of aniline alcohol to aniline, was done by Narayan, Subrat, and Ratnakar. And Rahul and his master student Astos, they have been working on this iron project, the selective oxidation of this primary alcohol to aldehyde. And thankful to this funding agency for organizing committee to give me an opportunity to share our lecture together. And thank you all for your
Okay, thank you, Dr. Bagh. So we can have one quick questions.
nice talk. Thank you. Yeah. Okay. The thing is that we have few more iron catalysts. We have used it, we have some activities, what I don't want to discuss. But as I said, in most of the catalytic reactions, you see often people don't give importance to the role of solvent. That is not really one. Solvent plays a crucial role in different catalytic reactions. Yes. What about so your suggestion is try some other catalysts as well. But what do you want to do? Change one parameter at a time. That's our strategy. So don't play with too many parameters at a time. We might be confused. So change one parameter and see what are the effects. And then you will see other effects. Pardon me? Yeah. Yeah. Honestly, no. The chlorine doesn't have any role. But well, you can say like when you use the perchlorate, that's they are weakly bound, leaves the metal and form the homoelectric complex. And as you know, homoelectric complexes are not very good captures. They have very poor range. But chloride bound to the metal, it doesn't allow the other ligand to come to the metal to form the homoelectric complex. That can be one reason. But the most reason was it is very cheap. Copper to chloride is damaging. So we want to use some protocol which is very cheap, sustainable.
Okay, so if there are any more questions, the bag is around tomorrow, so you can all discuss. We'll stop it here. We can discuss it later. Tomorrow is around. So as a Data Group appreciation, it's my pleasure to hand over a presentation of Minto to the part. It's a great talk on this catalysis. So, come to an end of this session.
Let me give the last one of the day. Okay, so we are done for today. Couple of announcements. One is the dinner for all the outstation delegates, including students. They have been arranged outside campus today. There will be a bus leaving 7 o'clock in a minute. So, so please go and catch that bus. It will go to Bhubaneswar. This one. And second one is that tomorrow session starts at 9 and not 9:30. So please, anything else to? So that concludes the day. Thank you very much.
सर एक चाहिए इधर से खींचोगे तो पूरा आएगा ओके ये डाउन जैसे फोटो